On a quiet night in the Utah desert, Earth was hit by a single particle carrying the kinetic energy of a fastball packed into something smaller than an atom. It should not exist, not this close to us, not with the universe's speed limit standing in the way. So what fired the oh my god particle at Earth, and how do you trace a charged bullet back to its trigger when space itself bends its path? By the time one of these particles reaches Earth, its path has been revised by the Milky Way, the intergalactic web, and perhaps fields we have not even begun to map. And still the energy remains stubbornly intact, demanding an explanation that fits both the source and the journey. These particles are the only samples of extreme physics we can hold, arriving free of charge yet never free of consequence. At the highest energies, space is not empty. It is crowded with ancient light, and that light is a gauntlet. Relativity turns a gentle background into a head-on collision field, and the journey becomes as important as the launch. This is the GZK suppression, the cosmic speed limit written not on a sign but into interactions that should shave the extraordinary down to the ordinary. If we cannot watch the particle itself, we can watch what it does to our sky. When an ultra-high energy cosmic ray meets the upper atmosphere, the first impact erases the original. What remains is a cascade, multiplying and spreading, a brief storm of secondaries. From those patterns we infer the energy, the direction, and the mass, and each inference carries uncertainty that can masquerade as discovery. And once the measurements harden, the central question sharpens with them. What kind of astrophysical machine can push a charged particle into the zeta electron volt regime without losing it to radiation, escape, or self-destruction? The candidates are dramatic. Jets from active galaxies, starburst environments, newborn magnetars, and each must pass a ruthless test of size, field strength, and time. The Hillas criterion is not a theory of how acceleration happens, but it is a gatekeeper, and most objects in the universe do not fit through it. Even those that do must still aim through magnetic fog and leave enough survivors within a limited horizon to match what we observe. Some models do not accelerate at all. They begin with energy already stored, waiting to be released by rare decays or exotic relics. These possibilities carry a different kind of implication, because they would mean the particle is not just telling us where it came from, but what the universe is made of. Because whatever launched that particle did not send it for our convenience. It arrived as a fragment of a larger story, one we can read only by expanding our instruments and tightening our reasoning. If we succeed, we will identify nature's true cosmic accelerators and learn how the universe spends energy at its most extravagant scales. If we fail, we may learn something even more unsettling, that at the highest energies, the rules themselves can bend. Before we begin, let us know in the comments below where in the world you are watching from and what time it is there. Now settle in for a journey. We will follow cosmic rays from their first discovery to the modern hunt for zevatrons, and to the edge where exotic physics becomes plausible. For centuries, the sky looked calm because our eyes missed its invisible rain. The blue dome appeared empty, a serene canopy stretching overhead with no hint of what it concealed. People looked up and saw stars, clouds, the occasional comet, and they imagined a domain of stillness, punctuated only by the rare drama of falling rocks or shifting light. The atmosphere seemed like a shield, and in many ways it was, but no one suspected it was also a battlefield, crossed continuously by invisible visitors that passed through skin and stone and steel without announcing themselves or asking permission. Early observers noticed something strange happening with their instruments, something that resisted easy explanation. Electroscopes, those delicate devices with thin metal leaves that spread apart when charged and slowly collapsed as charge leaked away, were doing something they should not have been doing. Even when sealed, even when shielded from known sources of radiation, even when placed far from any radioactive material, they continued to discharge. The leaves kept falling. The charge kept disappearing into thin air, quite literally. The phenomenon was persistent and reproducible, which meant it was real, and the fact that it continued despite every attempt to isolate the instrument meant the source was not local. It was not the walls of the laboratory, not the floor, not the experimenter's hands or breath. Something in the air itself, some persistent unseen influence, was continuously stripping away electrical charge. The air carried a steady, quiet electricity that no known source could fully account for. The natural assumption was that the radiation responsible came from Earth's crust. Rocks are mildly radioactive, and it seemed reasonable that gamma rays and particles from the ground were leaking upward and ionizing the air near the surface. This was testable because if the source was terrestrial, the effect should diminish with altitude. Rise above the rocks and the signal should fade. Go high enough and the electroscope should barely discharge at all. Victor Hess decided to test this assumption in the most direct way possible, by climbing into a balloon and taking measurements at altitude. In 1912, he rose above the shielding blanket of lower air and carried his electroscopes with him into the thinning atmosphere. The experiment was not comfortable, and it was not safe in the casual sense. Balloon ascents at the time were genuine acts of physical courage, involving cold, thin air, unpredictable weather, and equipment that was often improvised and unreliable. Hess went up anyway, and he brought his instruments, and he watched them. What he found demolished the assumption. Instead of fading with altitude, the ionization rate first dropped slightly, then rose again, climbing more steeply as the balloon climbed higher. By several kilometers up, where the air had thinned enough to make breathing labored, the discharge rate in his electroscopes was higher than it had been on the ground. The radiation was not weakening with distance from Earth. It was getting stronger. The logic was simple even if the implication was startling. If the radiation came from Earth's crust, it would have to travel upward through increasing amounts of air, losing energy to that air growing weaker with altitude. But the opposite was happening. The radiation was becoming more intense as the amount of intervening rock and soil decreased, which meant the rock and soil were not the source. The source was somewhere above. Something was coming down from space and striking the upper atmosphere with enough intensity to produce measurable ionization, even at ground level after passing through kilometers of air. Hess announced his findings, and the community took time to absorb them. This was a period when physics was already experiencing a revolution, with quantum mechanics, unsettling old certainties, and relativity reshaping the geometry of space and time. Now came another intrusion from outside the comfortable boundaries of classical understanding, a persistent rain of radiation from the cosmos, invisible to the eye and unmeasured, until an Austrian physicist climbed high enough to find it. In time, the discovery earned Hess a Nobel Prize, and it gave physicists not just a puzzle but a new kind of telescope. Cosmic rays became messengers that arrived uninvited, and they carried clues about violent engines beyond Earth. The sky, which had seemed passive and readable by ordinary optical telescopes, turned out to be threaded with charged particles that brought news from places where ordinary telescopes could not look. That news was encoded not in wavelengths of light but in energy and charge and direction, and decoding it would take decades. The critical word in that last sentence is charged. Unlike photons, cosmic ray messengers carry electric charge, and that detail changed everything about how they could be used as astronomical information. A photon travels in a straight line through empty space because it carries no charge and has no magnetic moment that matters at these scales. A charged particle does not. It bends in magnetic fields, and the universe is threaded with magnetic fields at every scale. From the tangled fields within individual clouds of gas, to the organized fields of entire galaxies, to the large-scale magnetism of the intergalactic medium, charged particles navigate a complex landscape of invisible forces that continuously modify their trajectories. This means that a cosmic ray arriving at Earth does not point back to its source the way a photon does. Its path through space has been curved and recurved by every magnetic field it encountered during its journey, which may have taken millions or even billions of years. By the time it arrives, its direction tells us roughly where it came from in a statistical sense, and with increasing clarity at higher energies where magnetic deflection is smaller, but it does not give us a clean address. It gives us a blurred hint, a smudged fingerprint, a direction that requires careful interpretation before it becomes useful information. Over the decades that followed Hess, researchers built increasingly sophisticated instruments to catalog cosmic rays, their energies, their arrival directions, their rates at different energy levels. Patterns emerged from the data. Most cosmic rays were modest in energy, and the processes that produced them could be explained with familiar astrophysics. Supernova shock waves in the Milky Way could accelerate particles to the lower end of the observed range, and the numbers worked out reasonably well. The spectrum of energies followed a power law, meaning that as you looked at higher and higher energies, the number of particles fell steeply and predictably, like counting inhabitants on a mountain where the numbers drop off sharply as the altitude increases. At lower energies, the flux was generous, almost comforting in its regularity. Detectors clicked steadily as particles arrived at predictable rates. The spectrum fell like a steep hillside, meaning that each jump in energy caused an enormous drop in the number of events. This was manageable. The sources were local in cosmic terms, the acceleration mechanisms were plausible, and the physics fit together with reasonable consistency. As detectors improved, and as the technology for building large-scale instruments advanced, the spectrum stretched upward into territory that earlier instruments could barely sample. The rare high-energy end began to reveal itself event by event, each new detection opening questions about what could produce such energies and how far such particles could travel before losing them. Each step higher in the energy scale forced new theories about acceleration, about confinement within magnetic structures, and about the fundamental limits of what natural processes could achieve. The basic question hardened into a challenge that sounded deceptively simple. What can accelerate a charged particle to energies that no human machine has ever reached, and that no human machine in the foreseeable future could hope to reach? This question has a practical anchor because it is not just about cataloging exotic phenomena. It is about identifying the most extreme physical processes in the observable universe. Nature, somewhere out there, is running particle accelerators that make our most powerful colliders look like toys, and understanding what those accelerators are is one of the deepest problems in high-energy astrophysics. In laboratories on Earth, particle accelerators use electric fields to push charged particles to high energies. Radio frequency cavities impart energy in carefully timed pulses. Magnets bend the particles into circles so they can be accelerated repeatedly rather than just once. The infrastructure is enormous, the engineering is precise, and the energy scale, while impressive by human standards, is dwarfed by what cosmic ray physics demands. The Large Hadron Collider at CERN is the most powerful accelerator ever built, and it reaches center-of-mass energies of about 14 tera-electron volts in proton-proton collisions. The Oh My God particle carried estimated energies of roughly 320 exa-electron volts in a single particle, which is more than 20 million times higher per particle than what the LHC achieves. The comparison is not just dramatic, it is humbling. In space, nature must accomplish the same acceleration without wires, without radio frequency cavities, and without carefully engineered magnets. It must use shock fronts, rotating electromagnetic fields, and turbulent magnetized plasma as its circuitry. The principles are the same in outline. Charged particles in changing electromagnetic fields gain energy. But the implementation is entirely different, and the scale is vastly larger. By mid-century, particle physics had supplied a rich vocabulary for thinking about these problems, and astrophysics had identified a range of possible arenas. Supernova shock waves became the favored candidate for cosmic rays at lower energies. When a massive star collapses and explodes, it drives a shock wave into the surrounding interstellar medium, and that shock can accelerate particles. The mechanism is called diffusive shock acceleration, and it works by bouncing particles back and forth across the shock front, gaining energy with each crossing. The process is elegant in principle, but constrained in practice. For diffusive shock acceleration to work efficiently, the magnetic turbulence on both sides of the shock must be strong enough to scatter the particle repeatedly and keep it from simply escaping. If the turbulence is too weak, the particle makes only a few crossings before wandering away from the shock, and the energy gain is modest. If the turbulence is strong enough, the particle can make many crossings and accumulate substantial energy, but even this process has a ceiling set by the size of the shock and the strength of the field. Supernova shocks are impressive, but they cannot reach the ZV energies of the most extreme events. Something more extreme is needed, and finding it is one of the central quests of the story. The constraints on any acceleration mechanism are brutal because nature must pay every energy bill in the currency of electromagnetic fields and particle interactions. A particle must be trapped long enough to gain energy, yet not lose it to radiation or collisions during that confinement. This is a delicate balance. A particle gyrating in a strong magnetic field gains energy if there is an accelerating electric field component, but it also radiates energy as synchrotron radiation simply by virtue of being curved. The radiation rate grows rapidly with energy, so at the highest energies, synchrotron losses can easily outpace gains. The particle tries to climb a hill while the hill itself is eroding beneath it. If the magnetic field is too weak, the particle's gyration radius, what physicists call the Larmor radius or gyroradius, becomes larger than the acceleration region, and the particle simply escapes before gaining significant energy. The particle must be contained within the accelerating region, and the size of that region sets a hard limit on the maximum achievable energy. If the field is too strong, synchrotron losses dominate, and the energy gain is choked. There is a sweet spot, and nature must hit it. These competing constraints were formalized into what became known as the Hillas criterion, named after astrophysicist Alan Hillas, who articulated it clearly in the 1980s. In essence, the maximum energy a particle can reach in a given acceleration region is proportional to the product of the magnetic field strength and the size of the region times the particle's charge. Written as a simple inequality, the gyroradius of the particle at the target energy must not exceed the size of the accelerator. This sounds straightforward, but when you plug in the numbers for the most extreme cosmic rays, the list of objects that can even in principle satisfy the criterion becomes very short. At the highest energies, another limit loomed, written not into the acceleration physics but into the universe's own structure. Interactions with background light should drain cosmic rays over long distances, creating what was predicted to be a cutoff in the observable spectrum. That expectation, developed in 1966 by three independent groups, became a kind of cosmic speed limit, not for velocity, but for survivable energy across cosmic distances. The universe itself was placing a ceiling on what could reach Earth from far away, and the ceiling was embarrassingly low compared to what the oh my god particle apparently was carrying. The cosmic microwave background is the cooled afterglow of the early universe, the relic radiation left over from when the cosmos was hot and dense enough to be opaque. As the universe expanded and cooled, this radiation was stretched to longer wavelengths, and today it fills all of space as a nearly uniform bath of microwave photons at a temperature of about 2.7 Kelvin. To ordinary matter at ordinary speeds, these photons are irrelevant. They are too low in energy to do much of anything, but to an ultra-relativistic proton moving at nearly the speed of light, the situation is completely different. From the proton's perspective, relativity transforms the picture. The cold microwave photons appear enormously blue-shifted. Photons that would barely register in any ordinary detector are transformed by the Lorentz boost into energetic adversaries. Proton carrying energy above a certain threshold, roughly 50 to 60 exa-electron volts, sees the cosmic microwave background photons as energetic enough to trigger pion production when they collide head-on with the proton. In that interaction, the proton loses a significant fraction of its kinetic energy to the creation of new particles. The universe extracts a toll with every interaction, and the toll is paid in lost momentum. After repeated such interactions, a proton that began at extreme energy is pushed down toward lower energies. The universe is not stopping the proton. It is continuously trimming the proton's energy down toward the GZK threshold. Above that threshold, the interactions are frequent and the trimming is relentless. Below it, the interactions become rare and the proton can coast for much longer distances without significant energy loss. The threshold is a kind of cliff edge. Above it, the universe is harsh and the range is short. Below it, the universe is far more permissive. For protons well above the GZK threshold, the energy loss length, which is the distance over which the proton loses a significant fraction of its energy, shrinks to roughly tens of megaparsecs. A megaparsec is about 326 million light-years, and tens of megaparsecs in cosmic terms is essentially local. It means that the most extreme cosmic rays, if they are protons, can only reach us from within a few hundred million light-years at most. The observable universe extends for billions of light-years in every direction, but the effective horizon for the highest energy protons is a tiny fraction of that vast volume. The universe becomes small for the most energetic particles. This is the GZK horizon, and its implications are severe. It means that the sources of the highest energy cosmic rays are not distributed throughout the observable universe. They must be concentrated in a relatively small cosmic neighborhood around the Milky Way. And that neighborhood, while large by any ordinary standard, is well surveyed enough that an obvious source of extreme acceleration would likely have been noticed in existing catalogs. The absence of an obvious candidate source makes the mystery sharper, not softer. The oh my god particle, with its estimated energy of 320 exa-electron volts, sits well above the GZK threshold. If it was a proton, it should have been losing energy at a ferocious rate for any journey longer than a few tens of megaparsecs. Either its source is very nearby, or it is not a proton, or the propagation physics is somehow different from what the standard calculation predicts. All three possibilities open different doors, and none of the doors leads to a comfortable room. Still, the sky kept sending rare outliers. Event after event pushed above where the theory said the spectrum should be suppressed. The community argued about whether the suppression was real, whether the detectors were calibrated correctly, whether systematic errors in energy determination were creating artificial excesses. The debate was technical and sometimes fierce, but underneath it was the shared awareness that something was happening at the top of the spectrum that demanded either new sources or new physics, and possibly both. The hunt moved from small counters to vast arrays that used the atmosphere as a calorimeter. Instead of trying to catch the primary particle directly, which is essentially impossible given how rarely it reaches the ground intact at these energies, researchers learned to read the consequences of the primary's first collision. The air itself became the target, and the shower of secondary particles that resulted became a luminous, measurable signature spreading across tens of kilometers. In the Utah desert, far from city lights and their disruptive glow, one such instrument waited in silence on dark nights. It was called the fly's eye, and it was built to watch darkness for brief flashes of ultraviolet light produced when air showers lit up nitrogen molecules in the upper atmosphere. The name was not decoration. The design genuinely resembled the compound vision of an insect. Many small viewing elements, each with its own patch of sky, combined into a wide-angle stare that could catch the faint track of light written by a passing shower. The fly's eye was not a single telescope, but a compound creature built from clusters of mirror canisters that sampled the sky, each feeding photons into photomultiplier tubes capable of registering a few quanta of light and converting them into measurable electrical signals. Inside each tube, a photon strikes a photocathode and liberates an electron. A series of diodes multiplies that initial electron into a measurable pulse. The technique relied on detecting the faint ultraviolet fluorescence from nitrogen molecules excited as the air shower's charged particles pass through. The light is not a spotlight, but a thin ghostly glow. Air molecules briefly energized, briefly disturbed from their equilibrium, then relaxing and releasing their distress as photons. A cosmic ray never arrives as a tidy bullet striking a sensor directly. It strikes high in the atmosphere, typically at altitudes above 20 kilometers, and triggers a cascade of secondary particles that multiplies as it descends. The cascade begins with a single violent collision between the primary particle and an atmospheric nucleus. That first collision creates new particles, pions, kaons, muons, electrons, and photons, which each carry a fraction of the original energy. The secondary particles themselves then collide with more atmospheric nuclei, creating tertiary particles, and the process continues in an exponentially growing cascade that peaks somewhere in the lower stratosphere or upper troposphere before thinning as particles range out and lose energy. The shower paints a moving track of fluorescent light through the atmosphere. It is not a single flash but a line, a brief luminous trail that moves downward at nearly the speed of light. Different tubes of the fly's eye see different segments of this track at slightly different times, and the sequence of triggered pixels encodes the geometry of the shower, its angle with respect to the vertical, its distance from the detector, and the profile of how its brightness evolved as it deepened through the atmosphere. From that track, the physicists could reconstruct where the primary came from in the sky, how much total energy it carried, and hints about its composition based on how deeply it penetrated before peaking. Dugway Proving Ground in the Utah desert offered the isolation, darkness, and wide horizons that this kind of instrument demanded. The landscape is wide and spare, a stripped terrain of pale soil and distant mountains, with heat shimmering above the salt flats in daylight. At night it becomes a dark bowl and the stars feel close and numerous. In that darkness, the instruments listen for the occasional brief glow that marks an extreme visitor. On clear dark nights, operators monitored wind and electronics and waited for patterns that would not repeat. Most triggers were ordinary showers, well within the expected energy range, unremarkable but important as calibration and statistical samples. Most nights ended without a story. Yet even the ordinary carried meaning, because each event was a data point in a spectrum that stretched toward the extraordinary, and the collection of ordinary events defined the baseline against which anything extraordinary would be measured. October 15, 1991 was moonless. The desert air was cold and dry. The fly's eye watched its sector of sky, and then the darkness was written with an impossible signature. In the control room, the event did not announce itself with drama, only with data. A sequence of tubes fired in a coherent arc, and the pattern refused to look like noise. The luminous track grew, peaked, and faded in a profile that was consistent with a massive air shower, one that implied an arriving primary particle of absurd energy. The reconstruction produced a number that made experienced researchers pause. The estimated energy was approximately 320 exa-electron volts, with an uncertainty near plus or minus 90. An exa-electron volt is 10 to the 18th electron volts. The prefix is not decorative. It marks a domain where ordinary intuition breaks because the particle's kinetic energy dwarfs its rest mass energy by orders of magnitude. The particle is moving at a speed so close to the speed of light that the difference is measured in parts per billion. That scale is hard to hold in the mind, and the comparisons that physicists reach for are genuinely strange. The energy was roughly 50 joules of kinetic energy packed into a single subatomic particle. 50 joules is not cosmic by everyday standards. It is the energy of a thrown baseball, the energy stored in a compressed spring, the energy that a tennis ball carries when hit reasonably hard. But it is outrageous at the microscopic scale of a single particle smaller than an atom. When that energy is concentrated into a point, the particle becomes something for which ordinary language has no satisfying description. It is energy density beyond anything our machines can touch, in a form that passes through walls and mountains and the entire planet without noticing them. Speed was not the surprise. At these energies, the particle is already moving at 99. 9,999,999,999,999,999,999% of the speed of light. And going faster is essentially meaningless, because the difference between that number and 100% corresponds to a lag behind a photon of only nanometers over a journey of a light year. What was surprising was how much energy was concentrated in a single particle, and what that implied about the mechanism that produced it and the journey it had survived. The data implied a visitor from far away, yet the universe should have taxed such a traveler severely. If it were a proton, background radiation should have bled its energy long before arrival. The GZK calculation was clear and unambiguous about this. At 320 exa-electron volts, a proton has an energy loss length of only a few megaparsecs before it is pushed down below the GZK threshold. For the particle to arrive at Earth with that much energy, the source would have to be extraordinarily close by cosmic standards, within perhaps a few tens of megaparsecs, and there was no obvious candidate in that direction. The event arrived alone, a single strike in a sea of lesser ones. That rarity made it precious, and it also made it suspect. Statistics can be cruel at the top of the spectrum because the flux is so low that years can pass between candidates. When one event dominates a dataset, it can look like discovery depending on your mood, or it can look like a mistake. A single anomalous event can always be attributed to detector malfunction, cosmic coincidence, or subtle systematic error. The scientific culture of cosmic ray physics had learned hard lessons about the seductiveness of single spectacular events, and the response to the fly's eye detection was not celebration but controlled skepticism. The first reaction was not to publish a press release, but to check every component of the detection chain, starting with the photomultiplier tubes. A noisy channel, a mistimed pulse, or a saturated response could in principle fake a bright track. Photomultipliers are exquisitely sensitive, and that sensitivity comes with quirks. After pulsing, gain drift, and occasional electrical discharges can mimic the arrival of real light. So each tube's behavior was audited against calibration logs and compared to its expected performance characteristics. Were any tubes behaving unusually that night? Were there any anomalies in the gain settings or the timing electronics? Then came the mirrors, their pointing, and their alignment. A small error in the reconstructed shower axis can inflate the inferred energy because distance and apparent brightness are tightly coupled. If the shower is placed at a greater apparent distance than it truly was, the inferred light output must be larger to match the observed signal, and that larger light output corresponds to a larger shower, which in turn corresponds to a higher primary energy. The sensitivity of the energy estimate to geometry errors is not small, and small errors in geometry can propagate into large errors in energy. Atmosphere became the next suspect. Fluorescence depends on the composition and density of air, and the transmission of light from shower to detector depends on the scattering and absorption properties of everything in between. Aerosols, thin clouds, or humidity gradients can reduce the apparent brightness of a shower without the detector knowing about it, which means the reconstructed shower would appear fainter than it truly was, and the inferred energy would be pushed upward to compensate. Conversely, unusual clarity could also distort estimates in subtle ways. The desert can be wonderfully transparent, but even the best nights have some atmospheric variation. Even the calibration lamps and the gain settings were revisited because desert hardware drifts. The team treated the event like a crime scene, assuming nothing was innocent until it had been verified. They checked whether the absolute light scale was correct, whether the timing electronics was properly synchronized, and whether any channels behaved oddly that night. They reanalyzed the geometry, the timing fit, and the longitudinal development of the shower. They tested alternative reconstructions and explored what happened to the energy estimate under different atmospheric models and different assumptions about the shower axis. The process took months, and then longer, because extraordinary claims demand slow arithmetic and careful scrutiny. A year of detailed analysis followed, not to prove wonder, but to eliminate the possibility of mundane failure. This was not only caution but scientific culture, because cosmic ray physics had learned humility from previous episodes where exciting anomalies evaporated under close examination. The sky can deceive, electronics can lie, and the human mind is eager to see patterns where none exist. Every promising anomaly deserved skepticism proportional to its importance, and an event at 320 exa-electron volts was important enough to deserve maximum skepticism. In the end, the track held together across independent checks. The shower profile matched the expectations for a genuine hadronic cascade, and the systematics could not erase the energy scale without making other aspects of the reconstruction implausible. The uncertainties remain large, as they always do in this field, but the event refused to collapse into a trivial explanation under sustained examination. What remained was a stubborn conclusion. Something had struck the atmosphere with an energy that strained every accepted model of acceleration and propagation. The community still argued, because one event cannot build a theory, but the data survived enough skepticism to earn a name that captured its shock. It became the "Oh my God" particle, a nickname that admitted disbelief without surrendering to it. The name spread because it summarized the feeling of encountering a number that should not exist. For a moment, the formal language of physics dropped away, and the human response, raw astonishment, took its place. Scientists are people first, and occasionally the universe does something that bypasses training and speaks directly to the part of us that still looks at the sky and feels small. Now the story turned from detection to implication, and the implications were unsettling in every direction. If such a particle could reach Earth, then either its source was nearby in cosmic terms, or the assumptions underlying the GZK calculation were somehow incomplete, or the particle was not what it appeared to be. Nearby sources would need to be extreme, capable of accelerating to ZeV energies within a volume small enough to satisfy the propagation constraints. They would also need to aim their output through a magnetic maze and still leave enough survivors to produce rare but detectable events. And they would need to be somewhere we had not already identified as an obvious candidate. If sources were not nearby, then the GZK expectation was challenged, and the universe looked more transparent than standard physics predicted. That would force either new physics in the interaction cross-sections, or new particle densities, or modifications to relativity itself at extreme energies. Each of these options was more drastic than the last, and each required its own set of predictions and tests. The uncomfortable possibility lurking at the back of every discussion was that the event was not just a message about the power of distant engines, but about the limits of the models that physicists had built from decades of laboratory experiments extrapolated into extreme regimes. Perhaps the rules we trust at accessible energies are not wrong, but incomplete, and the universe was offering a glimpse of the incompleteness from beyond the reach of any machine we could build. The "Oh my God" event did not just add one data point to a graph. It threatened the boundary between what astrophysics can plausibly accelerate and what particle physics can plausibly allow. That boundary is where two disciplines meet, and where each hopes the other will supply the missing piece. If acceleration to these energies seems impossible within known astrophysics, we question the source. If propagation of such energy across cosmic distances seems impossible within known particle physics, we question either the particle's identity or the rules of propagation. The event created a problem with no clean solution, only a set of competing discomforts. It also raised a practical problem that would define the field for the following decades. How do you trace a charged messenger back to its engine when space itself scrambles its path? The atmosphere gives a luminous record, but it is a record written in fleeting ultraviolet and reconstructed through models that carry their own assumptions and uncertainties. Each event is a single sentence torn from a book we cannot yet read in full, in a language we are still learning, written in a code that the universe did not intend for our benefit. In the Utah desert, the fly's eye had done its job. It had seen something, measured something, and carefully verified that what it measured was not simply a mistake. But it left a riddle in its wake. One particle had arrived with impossible wealth and no clear return address. The desert returned to silence. The data remained, and the number kept its sharp edge, refusing to soften into something comfortable. Somewhere out there, something had performed an acceleration trick that outclassed every machine humanity had ever built or imagined building, then sent the result across a universe that by all rights should have stopped it. The particle had arrived at the edge of our atmosphere as evidence of something we could not explain, a fragment of a physics we had not yet assembled, a message in a language we were only beginning to learn to read. From here, the pursuit would widen, because one detector and one event cannot settle a cosmic argument. The next generation of observatories would be needed, and the theories they forced into the open would reshape our picture of what the nearby universe contains and what it is capable of doing. The central question remained, sharpened by that one moonless October night: what is shooting at Earth, and what kind of universe allows the shot to land? The "Oh my God" particle did not only challenge acceleration. It challenged travel, because the intervening universe is not passive, and it does not merely watch a particle pass. If the particle was a proton, the universe itself should have stopped it, or at least shaved its energy down to something the standard calculations could accommodate. The story of the GZK limit is often misunderstood even by people who know the headline. It is not a cap on what astrophysical engines can produce in principle. It is a barrier to what can survive the journey to Earth while remaining extreme. The GZK limit is less about invention and more about endurance. It is a question of whether the cosmos allows certain energy states to persist across large distances. Whatever nature builds at the source must still pay the costs of travel, and those costs are set into the fabric of space by the omnipresent relic radiation that fills every cubic centimeter of the observable universe. In 1966, three groups reached the same conclusion independently. Kenneth Greisen in the United States published his analysis showing that protons above a certain energy threshold would interact frequently with cosmic microwave background photons and rapidly lose energy. Almost simultaneously, Georgy Zatsepin and Vadim Kuzmin in the Soviet Union published equivalent results, arriving at the same prediction from a different direction both geographically and intellectually. The coincidence of timing was not entirely accidental. Both groups were responding to the same new cosmological reality. The cosmic microwave background had been detected only the year before, in 1965, by Penzias and Wilson at Bell Labs. Suddenly, the universe was not just expanding in the abstract. It was filled with a measurable, real, omnipresent field of relic photons, and that field had to be reckoned with. Before the CMB was detected, the universe could be idealized as mostly empty space punctuated by matter. After the detection, the space between galaxies revealed itself as a genuine medium, filled with ancient photons that would interact with anything passing through. The question became unavoidable. What does this photon bath do to the fastest particles? The answer, developed independently by Greisen and by Zatsepin and Kuzmin, was that it imposes a hard limit on how far the most energetic protons can travel without losing their extreme energy. The limit became known by their initials, the GZK suppression. The logic begins with a basic fact about the cosmic microwave background. The CMB fills all of space with photons at a temperature of about 2.7 Kelvin, cooled from the much higher temperature of the early universe by billions of years of cosmic expansion. These photons have been stretched by the expansion of space from the high-energy gamma rays they once were into the microwave radiation they are today. Their individual energies are tiny by particle physics standards, roughly a fraction of a millielectron volt, and in our frame of reference they are harmless. They pass through ordinary matter without effect. They do not ionize atoms, they do not drive chemical reactions, and they do not pose any risk to living organisms. They are the quietest, most ancient radiation in the universe, a thermal haze that permeates everything without interacting significantly with anything. But the population of these photons is staggeringly large. There are approximately 400 CMB photons in every cubic centimeter of space throughout the observable universe. This number is nearly uniform across vast cosmic scales. Wherever you go in the universe, the density of the microwave background is roughly the same. And that ubiquity means that any particle crossing intergalactic distances will encounter an astronomical number of these photons. Probability becomes certainty when the sample size is large enough, and the universe is patient enough to make density matter over sufficient distances. Proton traveling at ordinary speeds would find the CMB completely irrelevant. The photons would pass through or scatter off the proton without depositing enough energy to do anything interesting. But a proton traveling at ultrarelativistic speeds, near the speed of light, and carrying energies above roughly 50 to 60 electron volts, exists in a very different situation. Relativity transforms the encounter from something trivial into something dramatic. The key is the proton's Lorentz factor, the number physicists call gamma, which measures how relativistic the motion is. At 100 electron volts, a proton's Lorentz factor is approximately 10 to the 11th. This enormous number does not mean the proton is traveling vastly faster than light or even dramatically faster than a proton at lower energies. It means that the proton's relationship with time, length, and the energies of things in its environment are transformed in ways that become physically significant. From the perspective of the proton's rest frame, the universe looks completely different. The microwave photons, which are cold and feeble in our frame, appear Doppler-shifted into energetic adversaries. Photons arriving head-on are blue-shifted by a factor of roughly twice the Lorentz factor, which means their energies are boosted by a factor of billions. The microwave photons, which had energies of a fraction of a millielectron volt in our frame, appear in the proton's frame as photons with energies in the hundreds of megaelectron volts. Those are not microwaves, those are gamma rays. In the proton's rest frame, the universe is also aberrated by relativistic effects. The entire photon background, which appears as an isotropic sea of radiation in our frame, is concentrated by aberration into a narrow cone pointed ahead of the proton. Almost all the photon flux arrives from roughly the same direction, the direction the proton is headed toward. The universe's cosmic background effectively becomes a beam of radiation aimed at the proton's nose, and the energy of that beam is sufficient to trigger hadronic reactions. Specifically, the center of momentum energy of the collision between an ultrarelativistic proton and a CMB photon can exceed the threshold for pion production. A pion is a particle made of a quark and an antiquark, lighter than a proton, and it carries away a significant fraction of the proton's kinetic energy when it is created. The process is well understood from particle physics experiments. In the proton's rest frame, it is simply a photon-proton collision with enough energy to create new particles, constrained by the usual conservation laws. The physics is not exotic. What is exotic is that the conditions for this interaction arise not from an artificial accelerator target, but from the thermal background filling all of space. The specific reaction that dominates is the production of the delta resonance, a short-lived excited baryon state. The proton absorbs the energetic CMB photon and briefly becomes a delta particle before decaying. The delta can decay in two main ways, back into a proton and a neutral pion, or into a neutron and a positive pion. In either case, the outgoing nucleon carries only about 80% of the incoming proton's energy. The rest has gone into the pion and the kinetic energy of separation. Each interaction is a 20% tax, and the universe collects this tax every time the proton travels far enough to encounter another CMB photon with sufficient energy for the interaction. The mean free path between interactions, meaning the average distance a proton travels before encountering a CMB photon energetic enough in the proton's frame to trigger pion production, is roughly a few to tens of megaparsecs at energies above the threshold. This depends somewhat on the proton's energy, because higher energy protons see a larger fraction of the CMB photon population as energetic enough to react. As the proton's energy increases, more and more of the background photons cross the threshold in the proton's frame, and the mean free path shortens. Above the GZK threshold, protons interact frequently, losing energy steadily until they fall below the threshold, at which point the interaction rate drops dramatically and the proton can coast for much longer. This creates an effective horizon. Think of it as the distance beyond which a proton's energy at arrival is almost certainly below the GZK threshold, even if it started much higher. The horizon is not a wall, it is a statistical boundary. Protons can in principle arrive from beyond it, but they will have been degraded by the time they reach us, their energies trimmed down toward the threshold by repeated pion-producing encounters. The probability of arriving at trans-GZK energies from beyond roughly 100 megaparsecs is very small, and it falls further the more we push above the threshold. For the oh my god particle at 320 exa-electron volts, this horizon shrinks dramatically. At that energy, the mean free path against pion production is very short, only a handful of megaparsecs, and the probability of surviving a journey of more than perhaps 30 or 40 megaparsecs without being degraded below 100 exa-electron volts is negligibly small. The particle's extreme energy essentially writes its own return address, but in reverse, it tells us how close the source must be, rather than exactly where it is. The problem is that the nearby universe, within a few tens of megaparsecs, does not contain an obvious source of ZV cosmic rays. The region is well studied by multiple surveys in optical, radio, X-ray, and gamma-ray bands. The nearby large-scale structure is reasonably well mapped. There are no blazing active galactic nuclei sitting in the precise direction of the oh my god event's arrival. There are no known objects of sufficient power located close enough to satisfy both the GZK constraint and the directional hint from the shower reconstruction. The neighborhood that the GZK limit specifies as the allowed source region looks disturbingly quiet in every catalog we have. The neutron channel in pion production deserves a moment of attention because it introduces a subtle complication that is easy to miss. When the delta resonance decays into a neutron and a positive pion, the proton has effectively become a neutron. Neutrons are electrically neutral, which means they do not bend in magnetic fields. They travel in straight lines until they decay. The neutron's lifetime in its rest frame is about 10 minutes, but at extreme relativistic energies, time dilation stretches the effective lifetime enormously. A neutron carrying 100 exa-electron volts would have a time-dilated lifetime corresponding to a travel distance of millions of light-years before decaying back into a proton. This has interesting consequences for source hunting. A nearby source could potentially produce neutrons through the pion production channel, and those neutrons would travel in straight lines through the magnetic maze that deflects protons and heavy nuclei. They would arrive pointing directly back at their source, uncorrupted by magnetic deflection. But the range over which this works, while large by everyday standards, is still cosmically modest, and the decay products of the neutron, a proton, an electron, and an antineutrino, would then continue the journey with the proton component subject to magnetic deflection again. The straight-line portion of the journey is a brief respite before the magnetic scrambling resumes. Beyond the CMB, there are other photon backgrounds that matter for ultra-high-energy cosmic ray propagation, though they become relevant at different energies. The extragalactic background light, consisting of photons produced by stars and galaxies throughout cosmic history in the optical and infrared, provides another target population. Ultra-high-energy photons, if they form part of the cosmic ray flux, interact with these lower-energy background photons through pair production, creating electron-positron pairs and initiating electromagnetic cascades. Heavy nuclei face photodisintegration on both the CMB and the infrared background, with the dominant process depending on the nucleus's energy and mass number. The universe offers a rich menu of interaction channels at these energies, and the most extreme particles must navigate all of them. Photodisintegration of heavy nuclei follows a different pathway from pion production on protons. When a heavy nucleus is struck by a sufficiently energetic photon in its rest frame, the nucleus can be excited into a giant dipole resonance, an oscillation of protons against neutrons that results in the ejection of one or more nucleons from the nucleus. A nucleus of iron, for example, can shed a proton or neutron in each encounter, working its way down the periodic table through intermediate elements until it becomes something lighter. The stripped nucleons continue as separate particles, each carrying a fraction of the original energy. What began as an iron nucleus can arrive at Earth as a shower that looks nothing like an iron shower because the primary has become a lighter element or even a free proton or neutron. This transformation of nuclear identity in transit is one of the most challenging aspects of ultra-high-energy cosmic ray physics. It means that composition is not a fixed property of the source, but an evolving property of the particle during its journey. The particle that arrives at Earth may be genuinely different from what was accelerated at the source, and the relationship between the detected composition and the source composition depends on the details of propagation through magnetic fields and photon backgrounds in ways that are computationally intensive and model-dependent. The combined effect of all these propagation processes is to filter the cosmic ray spectrum, removing the most extreme energies from distant sources and leaving only local events at the top end. The universe acts like a frequency-dependent filter that passes lower energies from anywhere, but only allows the highest energies from nearby. The spectrum of detected cosmic rays, therefore, encodes information about the distribution of sources in space and the propagation physics, all mixed together in a way that requires careful modeling to disentangle. The suppression of the flux at the highest energies, corresponding to the GZK prediction, was the subject of intense debate in the community for years. Different experiments appeared to give contradictory results. Some saw a clear drop in the flux above roughly 50 to 60 exa-electron volts, consistent with GZK expectations. Others, particularly the AGASA experiment in Japan, reported a spectrum that appeared to remain flatter than the GZK prediction, suggesting either that the suppression was not as strong as calculated or that the detectors were measuring something different. The difficulty was partly in the energy scale. The absolute energy assignment for an ultra-high-energy cosmic ray event is not a direct measurement. It is an inference that depends on models of shower development, assumptions about hadronic interactions at energies beyond accelerator reach, atmospheric monitoring, and detector calibration. A systematic shift of even 20% in the energy scale could transform a spectrum that appeared to violate the GZK prediction into one that was consistent with it, or vice versa. At a steep power law spectrum, calibration uncertainty is existential, not merely technical. The debate was resolved, or at least substantially clarified, when larger experiments with better crosschecks provided data that was more consistent with a suppression at the expected energies. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah, both of which used hybrid detection combining surface arrays with fluorescence detectors, eventually accumulated enough statistics to show that the flux does indeed fall more steeply above roughly 60 exa-electron volts, consistent with GZK suppression. This was a quiet triumph for the 1966 calculation and for the underlying physics of proton interactions with the microwave background. But the suppression does not make the oh my god particle and events like it disappear. It makes them rarer, but it does not eliminate them. And each event that sits above the threshold demands an explanation that satisfies both the energy and the propagation constraints simultaneously. The universe may suppress the flux at the highest energies, but it still permits rare events to occur, and each occurrence is a challenge to understand. The GZK horizon also has a somewhat optimistic implication that is easy to overlook in the focus on its constraining aspects. By forcing the sources of the highest energy events to be local, it actually makes them more accessible to astronomy. If ultra-high-energy cosmic rays could arrive from anywhere in the observable universe, they would be smeared over the entire sky without directional correlation to any particular population of objects. The GZK limit concentrates the source distribution into a cosmic neighborhood that is observationally tractable. The nearby universe, within a few hundred megaparsecs, can be surveyed with sufficient detail to identify candidate source classes and test correlations with arrival directions. This is why the question of composition is so important for source astronomy. A proton at these energies retains a reasonable memory of its direction because its rigidity is high and magnetic deflection, while not negligible, is at least modest enough to preserve some directional information. If the arrival direction of a proton cosmic ray is reconstructed accurately, the backtrack direction, corrected for known magnetic fields, can point toward a region of the sky within which the source is likely to be found. Not to a specific object, but to a region that can be searched for known powerful astrophysical objects. A heavy nucleus at the same total energy has a much lower rigidity, because rigidity is proportional to momentum divided by charge, and a heavy nucleus has a much higher charge for the same total energy. Iron, with charge 26, has 26 times lower rigidity than a proton at the same energy. The deflection in magnetic fields is 26 times larger. The directional information is correspondingly more scrambled, and the backtrack region expands from a focused region to a broad swath of sky that is far less useful for source astronomy. This is why measuring composition and measuring arrival direction are deeply interconnected problems. If the primary particles are protons, directional source astronomy has a chance, at least statistically across many events. If they are heavy nuclei, the sky becomes more isotropic, and source hunting becomes correspondingly harder. The nature of the particles determines the nature of the astronomical tool, and not knowing the composition means not knowing whether the arrival directions are meaningful arrows or magnetic scramble. The uncertainty about composition at the highest energies was one of the central unsolved problems as cosmic ray physics entered the new millennium. The answer required better instruments, more statistics, and improved models of hadronic interactions in regimes beyond any accelerator's reach. These are the technical challenges that drove the construction of the next generation of experiments, each designed to address some part of the puzzle while inevitably exposing new aspects of it. The GZK limit is therefore not a ceiling that blocks understanding. It is more like a lens that focuses attention. It tells us the sources are nearby, the composition matters enormously for direction, and the propagation is rich with interacting physics. It turns the problem from an unlimited cosmic search into a constrained local puzzle, and constrained problems, while still hard, are at least tractable in principle. The universe has done us the favor of limiting the search radius, even as it has complicated the interpretation by filling that radius with magnetic fields and photon backgrounds that modify every message in transit. And so the oh my god particle, sitting at 320 electron volts with its poorly understood origin, its uncertain composition, and its arrival from a direction that points toward no obvious candidate, became not just a single anomalous event, but a template for a class of problems. The problems are about how the universe's most extreme processes leave traces that can survive the journey to Earth, and how we can read those traces accurately enough to reconstruct what created them. The dread in this chapter is not the fear that the universe is arbitrary or that the rules break down randomly. It is the more precise dread of having almost enough information to solve a problem while still missing something crucial. We know the physics of the CMB. We know the threshold for pion production, we know the energy loss rates, and we know the observed energy of the event. What we do not know is the composition, the source direction corrected for unknown magnetic fields, the detailed structure of those fields, and whether any of our extrapolated hadronic cross-sections are accurate at 10 to the 20th electron volts. Each of those unknowns is a gap between the event and its explanation, and the gaps are just wide enough to prevent a clean answer. The oh my god particle forced the field to confront all of these gaps simultaneously, and it forced the construction of instruments large enough and sophisticated enough to begin closing them. In the Utah desert, one detector had seen one impossible event. The response was to build more detectors, spread them over larger areas, and combine multiple detection techniques so that the systematics of one method could be cross-checked against the systematics of another. The next chapter in the story would be written not by a single dramatic event, but by the accumulation of statistics and the development of hybrid methods capable of reading multiple properties of each shower at once. The oh my god particle could have been a lonely glitch, a single spike in the record that never repeated, an artifact of an instrument pushed to its limits on one fortunate or unfortunate night, depending on your perspective. For a while, that possibility hung over the field like an unresolved verdict. In the early 1990s, ultra-high-energy cosmic ray physics still lived with fragile statistics because the rarest events arrive on human timescales, and human timescales are not generous when the flux at the top of the spectrum is measured in particles per square kilometer per century. The next decade would decide whether the Utah shower was an error dressed as a miracle or the first specimen in a genuinely new class of phenomena demanding genuinely new explanations. After 1991, the spectrum's top end stayed thin but provocative, like a cliff edge with a few footprints beyond it where no footprints should be. Every footprint invited a new argument about calibration, composition, and the reliability of the reconstruction methods. Few more candidates appeared in various datasets, each one forcing the same questions about travel, energy, and the missing return address. If the universe truly imposed a cutoff above a certain energy, why did the data keep whispering about exceptions, quietly and stubbornly, and just often enough to be statistically uncomfortable? At these energies, the numbers themselves become part of the drama because the units stop feeling like bookkeeping and start feeling like a physical provocation. An exa-electron volt is 10 to the 18th electron volts. A particle at 200 exa-electron volts carries macroscopic kinetic energy in microscopic form, energy that would be unremarkable if distributed across a thrown baseball, but is extraordinary when concentrated into a single subatomic particle. The contrast is not merely numerical. It points to something deeply strange about how nature manages energy at its most extreme scales. Another way to hold the comparison is this. Nature has apparently built a particle accelerator somewhere in the local universe, an accelerator far beyond anything human engineering has achieved or can plausibly achieve in the near future, and it has aimed the output at Earth. The output arrives without announcement, leaves no permanent mark, and vanishes into secondary particles within microseconds of striking the upper atmosphere. The only evidence it ever existed is a pattern of light and charged particles spread across the desert floor, and from that pattern physicists must reconstruct everything: the energy, the direction, the composition, and ultimately the identity of whatever created it. The field needed a different kind of instrument to settle the growing argument. Fluorescence detectors were powerful, but their duty cycle was severely limited. They could only operate on clear, dark nights, which in practice meant roughly a 10% duty cycle at best. The sky is not cooperative about this. Clouds arrive, the moon rises, and the instruments go blind. This limitation was not a minor inconvenience. At the very top of the energy spectrum, where events are already vanishingly rare, losing 90% of your observation time is devastating to the accumulation of statistics. There is also the question of what fluorescence detectors see versus what they miss. The ultraviolet glow produced by a shower is real and measurable, but it is faint, directional in the sense that it radiates from a track in the sky, and vulnerable to atmospheric interference in ways that are difficult to monitor completely. The atmosphere is not a calibrated instrument. It is a variable medium with winds, humidity gradients, aerosol layers, and convective structures that change on timescales shorter than a shower event. Even with careful atmospheric monitoring, using laser shots and star calibrations, there is always residual uncertainty in exactly how much light was produced by the shower versus how much was absorbed or scattered before reaching the detector. The fluorescence method is also fundamentally calorimetric, but incomplete in a specific way that matters. The telescopes measure the energy deposited into ionization and fluorescence of the air. But a fraction of the shower's energy escapes in forms that do not produce ultraviolet light. High-energy muons punch through the atmosphere and reach the ground without depositing their energy locally. Neutrinos from pion decay escape entirely, carrying energy that the fluorescence detector never sees. These invisible channels must be estimated from shower models and then added back to the visible energy to get the total primary energy. The correction is well understood in principle, but it depends on the hadronic interaction models that themselves are uncertain at the energies of interest. Japan's approach to the problem was philosophically different from the fluorescence method, and the difference reflected a deliberate strategic choice. The strategy was to sacrifice detailed event reconstruction in exchange for raw exposure. Build a huge surface array that operates continuously regardless of daylight, moonlight, or weather, and wait for the rarest showers to announce themselves by leaving footprints on the ground. If the flux at the top end is 1 particle per square kilometer per century, then the only honest response is to cover enough ground and wait long enough that the universe has no choice but to deliver samples. This was the philosophy behind AGASA, the Aquino Giant Air Shower Array, which spread particle detectors across roughly 100 square kilometers of Japanese countryside north of Tokyo. The detectors were simple in concept, scintillators that produced a flash of light when a charged particle passed through them, with the light converted to an electrical signal by photomultiplier tubes. The simplicity was intentional because simple detectors can be deployed at large scale, maintained over long periods, and trusted to give consistent results when calibrated carefully. 100 square kilometers of scintillators, running continuously for years, would accumulate exposure that a fluorescence detector could not match. The shower front arrives at the ground as a thin disk of particles, moving at nearly the speed of light, sweeping across the array in a fraction of a microsecond. The stations at the edge of the footprint trigger a few tens of nanoseconds before the stations near the core, because the shower front is tilted when the primary arrives at an angle to the vertical. The timing pattern across the array encodes the arrival direction of the primary. The particle densities at different distances from the shower core encode the shower's size, which is the proxy for energy. The geometry is elegant and the measurement is relatively robust because it does not depend on atmospheric transparency or the darkness of the night. What AGASA sacrificed was the longitudinal development profile, the information about how the shower grew and peaked as a function of depth in the atmosphere. Without that profile, composition is much harder to constrain. The surface array sees a snapshot of the shower at ground level, not the full history of how it developed from the first interaction at the top of the atmosphere to the maximum and eventual thinning at lower altitudes. Two showers with different primary compositions can produce similar ground-level footprints in some configurations, making it difficult to distinguish a proton event from an iron event on a case-by-case basis. The composition information requires statistical analysis across many events rather than individual event reconstruction. AGASA also faced uncertainties in its energy calibration that would later become central to the arguments about whether the GZK suppression was real. The energy was inferred from the particle density at a reference distance from the shower core, typically 600 meters for AGASA, and then converted to primary energy using simulations of shower development. The conversion factor depends on the hadronic interaction models used in the simulation, and those models are uncertain at the energies of interest because they extrapolate far beyond the regime where they have been validated by accelerator experiments. A systematic error in the conversion factor would shift the entire energy scale, moving events above or below the GZK threshold and potentially creating or eliminating apparent violations of the suppression. In 1993, AGASA reported a clean event near 200 exa-electron volts, and the number landed with weight that was felt across the field. It was not a marginal bump at the edge of sensitivity, and it was not reconstructed from a single photo tube track vulnerable to calibration quirks. It was a surface pattern with multiple stations firing in a coherent sequence, consistent with a genuine large air shower crossing the array. The shower footprint spread across the grid in the manner expected for a primary particle at extreme energy. The timing fit was stable across the triggered stations, and the energy estimate remained extreme even when analysts stressed the assumptions in the reconstruction. A surface array event has a particular visual logic that differs completely from a fluorescence event. Where the fluorescence method sees a track of light in the sky, the surface array sees a pattern of hits stamped onto the Earth. The earlier stations define the direction of the incoming shower. The density of particles at different distances from the core maps the lateral distribution. The total signal, integrated over the array and corrected for distance from the core, gives the energy. It is inference from a ground-level snapshot rather than a sky-level movie, but it is inference from many independent measurements rather than a single detector track, which provides a different kind of robustness. The AGASA event changed the social meaning of the anomaly, which is a real force in science even when nobody wants to acknowledge it explicitly. One impossible event can be treated as a statistical fluctuation, an instrument malfunction, or an exotic coincidence. Two events from different detectors using different methods, arriving at similar conclusions despite completely different systematic error sources, begin to look like a population. A population demands a mechanism rather than a shrug. The story shifted from whether it happened to what could possibly produce it. Yet AGASA's result did not end the GZK argument. In some sense, it sharpened the argument by raising the stakes of dismissal. The GZK suppression was built on physics that was well tested at accessible energies. The cosmic microwave background was real. The pion production cross-section at the relevant center of momentum energies was measured in accelerator experiments. The kinematics of the threshold were straightforward applications of special relativity. Dismissing the GZK prediction required dismissing well-established physics, and that is a high bar. As AGASA continued collecting events, a pattern emerged that caused increasing tension. The AGASA spectrum appeared flatter at the highest energies than the GZK prediction. The events were not just extending the spectrum by a few percent above the threshold. They were accumulating in numbers that seemed inconsistent with a strong suppression. If the GZK cutoff was as sharp as the calculation suggested, AGASA appeared to be seeing too many events above it. The excess was not overwhelming in absolute numbers because the statistics were always limited, but it was persistent enough to generate serious discussion about whether the standard propagation physics was adequate. The tension was complicated by the fact that different experiments were not all agreeing with each other. Some datasets from other arrays and from fluorescence detectors appeared more consistent with a suppression. The differences could potentially be explained by energy scale uncertainties, because if AGASA's energy calibration was shifted upward relative to other experiments, events that AGASA placed above the GZK threshold might actually be below it when measured on a consistent absolute scale. Resolving this required either a direct cross-calibration between experiments, which was technically challenging when they were located in different hemispheres, or a theoretical framework that could predict the spectrum well enough to use its shape for calibration. The energy scale question became one of the most contentious technical issues in the field. Different groups argued about the correct value of the fluorescence yield from nitrogen, the quantity that converts the measured light signal into an estimate of the energy deposited in the atmosphere. They argued about the invisible energy correction factor for muons and neutrinos. They argued about the hadronic interaction models used in shower simulations, because those models set the conversion between ground-level particle densities and primary energy for surface arrays. Each source of uncertainty was individually modest, but they combined in ways that could shift the energy scale by amounts that mattered enormously at the steep top end of the spectrum. At a power law spectrum, calibration is destiny. If the true spectrum falls as energy to the -3, a 20% upward shift in energy scale moves an event from the ordinary range into the headline range, and a 20% downward shift moves it back out. The difference between a historic anomaly and a calibration artifact can be a number that is genuinely uncertain at the level of 20%, and that is an uncomfortable situation for a field trying to determine whether the laws of physics are being violated. The community recognized that resolving the debate required instruments that could address both the exposure limitation of fluorescence detectors and the composition limitation of surface arrays, while also providing a direct cross-check between different measurement techniques applied to the same events. The solution was hybrid detection, combining a large surface array with fluorescence telescopes surrounding it so that some events would be seen simultaneously by both systems. The hybrid approach sacrificed some simplicity but gained something more valuable: redundancy. When two independent methods applied to the same event give consistent energy estimates, the confidence in that estimate grows substantially. The Pierre Auger Observatory in Argentina embodied this philosophy at the largest scale attempted up to that point. Spread across roughly 3,000 square kilometers of the Pampa Amarilla in the Mendoza province, Auger deployed 1660 water Cherenkov surface detector stations at 1.5-kilometer spacing, surrounded by 27 fluorescence telescopes grouped into 4 stations at the edges of the array. The scale was not accidental. It was the minimum needed to accumulate enough events above the GZK threshold to make statistically meaningful statements about the spectrum and the arrival direction distribution. Water Cherenkov detectors differ from scintillators in an important way that matters for composition. A cylindrical tank filled with ultrapure water and instrumented with photomultiplier tubes detects charged particles by the Cherenkov light they emit when passing through water at speeds greater than the speed of light in that medium. High-energy muons, which are penetrating particles that arrive at the ground after being produced high in the shower and traveling mostly unimpeded through the intervening air, produce a strong signal in a water Cherenkov detector because they pass all the way through the water volume. Electromagnetic particles, electrons and positrons from the shower, produce a signal that depends on their energy but is typically concentrated near the shower core. The ratio of muonic to electromagnetic signal in the water tanks carries information about the shower's muon content, and the muon content is sensitive to composition. The telescope array in Utah, which began full operation in 2008, chose a different balance point. It deployed a surface array of scintillator stations across roughly 700 square kilometers, surrounded by 3 fluorescence detector stations. The scintillator-based surface array was more similar in concept to AGASA than to Auger's Water-Cherenkov approach, but the addition of fluorescence coverage and the hybrid detection capability gave it composition sensitivity that AGASA lacked. The site in the Black Rock Mesa Desert also had the geographic resonance of being near where the oh my god particle struck, which is not scientifically relevant but is difficult to entirely ignore when writing the history of the field. Together, Auger and the telescope array were designed to approach the problem from 2 hemispheres simultaneously, covering different parts of the sky and providing complementary exposure. The southern hemisphere, observed by Auger, contained the direction of the galactic center and a rich concentration of candidate source objects. The northern hemisphere, covered by the telescope array, contained different large-scale structure and different nearby galaxy populations. Events from both observatories, analyzed with consistent methods, would eventually allow a full-sky picture of the ultra-high-energy cosmic ray arrival direction distribution. The accumulation of data from both observatories over the following decade produced answers to some questions while deepening others. The spectrum question was substantially resolved. Both Auger and the telescope array observed a suppression of the flux at the highest energies consistent with GZK expectations, though the precise energy and sharpness of the suppression remained subjects of detailed analysis. The era of AGASA's apparent excess faded as the energy scales were reconciled, partly through direct comparison of hybrid events and partly through improved understanding of systematic uncertainties. But the source question remained stubbornly open. The arrival directions of the highest energy events did not cluster obviously around known powerful astrophysical objects. The distribution was not uniform across the sky, which would indicate complete magnetic scrambling, but it was also not concentrated in tight clusters that would point clearly to individual sources. It occupied an uncomfortable middle ground, structured enough to suggest that some directional information survived the journey, but diffuse enough to resist clean identification of specific sources. Auger reported a tantalizing correlation between the arrival directions of the highest energy events and the positions of nearby active galactic nuclei in the Varon-SETI and Varon catalog, a comprehensive list of known AGN. When the correlation was first announced in 2007 with early data, it appeared strong enough to be statistically significant. The community reacted with cautious excitement. If the correlation held, it would be the first direct evidence linking ultra-high-energy cosmic rays to a specific class of astronomical objects. The excitement was genuine but measured, because the field had learned from earlier near discoveries that initial results can weaken as more data accumulate. The correlation faded as the dataset grew. When Auger applied the same analysis to events collected after the initial announcement, the correlation did not hold at the same strength. The final verdict was that there was some anisotropy in the arrival directions, and some statistical preference for the direction of the local large-scale structure, but no clean clustering around individual AGN that would constitute a discovery. The sources remained hidden behind magnetic deflection and compositional uncertainty. The composition results from Auger added another layer of complexity that was genuinely unexpected. The measurements of the depth of shower maximum, the atmospheric depth at which a shower reaches its peak particle number, showed a trend toward lighter composition at energies around a few exa-electron volts, and then a trend toward heavier composition at higher energies. This was not what simple proton models had predicted. It suggested that the composition of the highest energy cosmic rays was not a pure proton beam from distant sources, but a mixture that evolved with energy in a way that depended on the source spectrum and the propagation effects. If the composition becomes heavier at the highest energies, the implications are significant for both source astronomy and propagation. Heavier nuclei have larger charge and therefore smaller rigidity at the same total energy. They are deflected more strongly by magnetic fields, and the arrival direction information is more scrambled. The sky becomes less useful as a pointing device, and source astronomy becomes correspondingly more difficult. At the same time, heavier nuclei have a different propagation horizon because they face photodisintegration rather than pion production as the dominant energy loss channel. The GZK horizon for heavy nuclei is different from that for protons, and the relationship between arrival energy and source distance changes. The telescope array's composition results were somewhat different from Auger's, a discrepancy that generated substantial discussion. The telescope array data were more consistent with a lighter composition, closer to proton-dominated, particularly at the highest energies. Whether this difference reflected a genuine difference in the cosmic ray population observed in the northern versus southern sky, or whether it reflected systematic differences in the two experiments' shower reconstruction and atmospheric corrections, became a major focus of joint analysis efforts. The energy at which the composition appears to shift also carries physical meaning, because it corresponds to the energy below which galactic sources might still contribute significantly. The transition from galactic to extragalactic cosmic rays is expected to occur somewhere in the range of a few to tens of electron volts, where the galactic magnetic field can no longer confine particles of that rigidity. Below the transition, the cosmic ray population is dominated by galactic sources accelerated in supernova remnants and similar environments. Above it, extragalactic sources take over. The energy and character of the transition encodes information about both the maximum energies of galactic accelerators and the minimum energies of extragalactic ones. On May 27, 2021, the telescope array recorded another event that pushed above 200 electron volts, and the number again carried a shock that was both scientific and visceral. It was quickly nicknamed the Amaterasu particle, after the Japanese sun goddess, and the name carried a deliberate echo of the earlier astonishment surrounding the "Oh my God" event. The naming was symbolic, but the measurement was a hard statistical object. It was a shower reconstructed by modern methods with modern crosschecks, in the same desert that started the legend 3 decades earlier. The Amaterasu event was particularly interesting because it was reconstructed with the improved tools of the hybrid era, with better atmospheric monitoring, better understood systematic uncertainties, and a larger surrounding array that provided more stations to constrain the shower geometry. The reconstruction was therefore more reliable than the original fly's eye analysis could have been, and the energy estimate carried smaller relative uncertainty. When the analysis team announced the result, they had already subjected it to the same kind of extended internal scrutiny that had characterized the "Oh my God" events analysis, checking every plausible source of systematic error. The arrival direction of the Amaterasu particle pointed toward a region of the sky that generated immediate attention for the wrong reason. Rather than pointing toward a known powerful source, the backtrack direction indicated a region of relative cosmic emptiness, near a structure called the local void. The local void is a genuine underdensity in the galaxy distribution near the Milky Way, a region where the cosmic web is thin and galaxies are sparse. The direction was reconstructed carefully and repeatedly, and it consistently pointed away from the dense filaments and clusters where powerful astrophysical accelerators are typically expected to reside. The local void problem was not entirely new. It had appeared in earlier discussions of other extreme events. But the Amaterasu particle brought it back with renewed force and better statistics. If the particle was a proton, its magnetic deflection should be relatively modest at 240 electron volts, and the backtrack source direction should be reasonably close to the true source direction, perhaps off by a few degrees in the most optimistic magnetic field models. A few degrees is enough to shift the apparent direction from one galaxy to a neighboring one, but it is not enough to shift from the middle of a rich filament to the middle of a void. The void points back to the fundamental tension that the "Oh my God" particle first articulated. Either the source is located where the backtrack direction indicates, in which case there is a powerful accelerator hiding in a cosmic underdensity where we would not expect one, or the backtrack direction is wrong, in which case the magnetic fields are stronger or more complex than our best models suggest, or the particle is heavier than a proton, and therefore more deflected than a proton would be at the same total energy. Each option carries its own discomfort. If there is a powerful accelerator in the local void, it must be an unusual object. The void is not completely empty. It contains some dwarf galaxies, diffuse gas, and dark matter distributed in the expected hierarchical structure. But it lacks the dense environments, the massive black holes, and the powerful jets associated with the most energetic known accelerators. Finding a ZV accelerator in such a setting would require either a new class of objects or an unusual realization of a known class, and either would be a significant discovery. If the magnetic deflection is larger than expected, it means our models of intergalactic magnetic fields are substantially wrong, which has implications for many other astrophysical calculations that depend on those fields. The intergalactic magnetic field is poorly measured. Most of what we know about it comes from indirect measurements: Faraday rotation of radio waves from distant sources, the diffuse radio background from synchrotron emission, and constraints from the non-observation of extended emission around known gamma-ray sources. These constraints limit the field's strength in various ways, but leave substantial room for uncertainty, particularly in the filaments and sheets of the cosmic web, where the field might be concentrated and structured. If the particle is heavier than a proton, the deflection can be larger even within the same magnetic field models, because the rigidity at a given total energy decreases with increasing charge. An iron nucleus at 240 exa-electron volts has the same total energy as a proton at 240 exa-electron volts, but its rigidity is 26 times lower. The deflection in the same magnetic field is 26 times larger. A shift of 26 times in deflection could easily move the apparent source direction from a known filament to the adjacent void, turning an apparently inexplicable result into a geometrical artifact of not knowing the composition. The composition question therefore becomes the key that potentially unlocks the source question, and this is why modern cosmic ray physics is so focused on measuring shower properties that carry composition information. The depth of shower maximum, the muon content of showers, and the fluctuations of these quantities from event to event all encode information about whether the primary particle was light or heavy. These measurements are technically demanding and subject to systematic uncertainties from hadronic interaction models, but they are the most direct handles on composition available with current technology. For the Amaterasu event specifically, the shower development was analyzed for what it could say about composition. The depth of shower maximum was measured and compared to expectations for proton and iron primaries. The result was ambiguous in the way that single-event composition measurements always are, because the shower-to-shower fluctuations for a given composition type are large enough that a single event cannot definitively establish the mass of the primary. A proton can produce a shower that looks iron-like, and an iron nucleus can produce a shower that looks proton-like, just less frequently. The composition of a single event is always a probability statement, not a certainty. Statistical composition analysis across many events is where the real power lies, and both Auger and the telescope array have accumulated enough events in different energy ranges to make meaningful statements. The broad picture from combined analyses suggests a mixed composition at the highest energies, with some fraction of light primaries including protons and helium nuclei, and some fraction of heavier nuclei including nitrogen mass and iron mass groups. The exact fractions and how they vary with energy depend sensitively on the hadronic interaction models used to interpret the shower data, and different models give different answers. The hadronic interaction model dependence is one of the most persistent sources of uncertainty in the field. At the energies relevant for ultra-high-energy cosmic ray showers, the first interaction between the primary particle and an atmospheric nucleus occurs at a center of mass energy that dwarfs what any current accelerator can probe. The Large Hadron Collider operates at 14 tera-electronvolts in proton-proton collisions. The first interaction of a 100 exa-electron-volt cosmic ray with an atmospheric proton occurs at a center of mass energy of roughly 450 tera-electron-volts, more than 30 times higher than the LHC can reach. At these unmeasured energies, the shower simulations must rely on extrapolations of hadronic cross-sections and particle multiplicity distributions based on theoretical models that are guided by lower energy data but cannot be directly validated. The models agree with each other at LHC energies, which is reassuring but not fully diagnostic of their behavior at higher energies. Different models, named with acronyms like EPOS-LHC, QGS Jetroman 2, and SIBYLL, give systematically different predictions for the number of muons in ultra-high-energy cosmic ray showers, and the differences are large enough to affect composition interpretations significantly. The muon problem is a specific manifestation of the hadronic model uncertainty that has attracted significant attention. Across multiple experiments and analysis approaches, the measured muon content of ultra-high-energy cosmic ray showers consistently appears to be higher than what the simulations predict, even when using models tuned to LHC data. The discrepancy is not huge in absolute terms, but it is persistent and statistically significant. If taken at face value, it suggests that the hadronic physics of very high energy interactions produces more muons than our models expect, which would mean that the energy fraction going into the electromagnetic component of the shower is somewhat less than predicted. The muon excess matters for composition measurements because more muons is one of the signatures of a heavier primary. If the simulations underpredict muons for any composition, then the apparent composition derived from muon measurements will be biased toward heavier values. The extent to which the muon excess is a physics problem versus a calibration or systematic error problem is still debated. But it highlights the fact that even the interpretation of the most basic shower observables depends on physics that we cannot fully validate in the energy regime of interest. The combined picture from the two major observatories, as the second decade of the 21st century progressed, was one of genuine progress combined with genuine remaining mystery. The GZK suppression was confirmed, removing the sharpest apparent challenge to standard propagation physics. The arrival direction distribution showed hints of anisotropy, particularly a correlation with the large-scale structure of the nearby universe, suggesting that some directional information survived the magnetic maze. The composition appeared to be mixed and possibly evolving with energy, which complicated both source astronomy and propagation modeling. What remained was the central puzzle in a refined form. The most extreme events, those above 100 or 200 electron volts, continued to arrive from directions that did not obviously correspond to powerful known sources within the GZK horizon. The Amaterasu particle was the most dramatic recent example, but it was not unique. Several other events in the telescope array dataset had properties suggesting they came from the same general region of the sky, which could indicate either a single powerful source or a chance clustering of unrelated events in a low statistics sample. The chance clustering possibility is always a concern at the top of the energy spectrum because the numbers are always small. When you have 10 or 20 events in a particular energy range, a clustering that appears significant at the 2 sigma level might be nothing more than the expected fluctuation of a small sample drawn from a uniform distribution. The significance assessment requires careful statistical treatment, including corrections for the number of independent tests performed and the choices made in defining energy thresholds and angular search windows. Both Auger and the telescope array performed extensive statistical analyses of their highest energy event catalogs, testing for clustering on various angular scales and correlations with various source catalogs. Both found hints of structure at levels that were suggestive but not conclusive. Auger reported a correlation with starburst galaxies, particularly Centaurus A and the starburst galaxies NGC 4945 and M82, at a level that had some statistical significance but not enough to constitute a definitive identification. The telescope array reported a hot spot in the northern sky, a region of roughly 20-degree radius, where the flux of events above about 57 electron volts appeared elevated relative to the isotropic expectation. The telescope array hot spot, centered near the direction of the Ursa Major supercluster, generated particular interest because it persisted as more data accumulated, growing from an initial suggestive clustering into a result at the 3 sigma level of statistical significance. 3 sigma is the conventional threshold for claiming evidence of a phenomenon in physics, though it falls short of the 5 sigma threshold for a definitive discovery. The hot spot is real enough to take seriously and uncertain enough to leave room for doubt. The direction of the telescope array hot spot is more consistent with nearby large-scale structure than the Amaterasu particle's direction toward the local void, which raises the interesting possibility that different events in the same energy range might come from different source populations. The highest energy events might not all come from the same class of objects. Some might be protons from powerful AGN in nearby filaments, arriving with modest deflection and some memory of their source direction. Others might be heavier nuclei from different source environments, arriving with more magnetic scrambling and less useful directional information. The sky would then be a confused superposition of signals from multiple source populations, each with different composition, different deflection, and different propagation history. Disentangling multiple source populations from each other requires statistics that current instruments struggle to provide. The number of events above 100 electron volts in any existing dataset is counted in the tens, not the hundreds. At that level, the statistical uncertainties dwarf the signal from any but the strongest anisotropy. The next generation of instruments, being planned and in some cases already under construction, is designed to accumulate events at rates 10 to 50 times higher than current experiments, pushing the statistics into a regime where multiple source populations could be distinguished. The Giant Radio Array for Neutrino Detection, the planned upgrade of Auger with radio antennas, the extension of the telescope array to cover 2,800 square kilometers with additional surface detectors, and new instruments like POEMMA in space all represent the community's recognition that current instruments, while enormously successful relative to their predecessors, are not yet large enough to settle the source question. The universe is being patient, sending its messengers at rates that are just frustratingly low enough to keep the answer tantalizingly out of reach. Multi-messenger astronomy added a new dimension to the search strategy in the years following the initial gravitational wave and neutrino detection announcements. The idea that ultra-high-energy cosmic ray sources might also produce detectable neutrinos and gamma rays is well grounded in physics. When protons at extreme energies interact with matter or radiation near their source, they produce pions that decay into neutrinos and gamma rays, in addition to the observed cosmic rays. If a source is powerful enough to produce detectable cosmic rays, it might also be detectable in high-energy neutrinos by IceCube at the South Pole, or in very high-energy gamma rays by Cherenkov telescope arrays. The neutrino connection is particularly compelling because neutrinos, being electrically neutral and only weakly interacting, travel in straight lines through magnetic fields and are not deflected at all. A neutrino detected by IceCube pointing back toward a known powerful AGN, or a starburst galaxy, would provide directional information that the corresponding cosmic ray cannot provide. If the cosmic rays and neutrinos come from the same source, the neutrino can point to the source, and the cosmic ray can tell us about the acceleration and propagation. Together, they provide more information than either alone. IceCube has detected a diffuse flux of high-energy neutrinos at energies from hundreds of tera-electron volts up to a few peta-electron volts, with a spectrum consistent with astrophysical production rather than atmospheric contamination. The origin of this diffuse flux is itself an open question, but it tells us that hadronic processes involving proton interactions and pion production, are occurring somewhere in the universe at energies approaching the ultra-high-energy regime. Some of the same sources that produce the IceCube neutrinos might also contribute to the cosmic ray flux at lower energies, and the most extreme accelerators might bridge both populations. The connection between IceCube's neutrino events and specific astrophysical sources has been tentative but suggestive. A correlation between the highest energy IceCube events and the positions of active galactic nuclei and blazars has been reported at levels that require more data to confirm definitively. Seyfert galaxies and starburst systems have been proposed as neutrino sources based on both theoretical arguments and observational hints. Each new multi-messenger connection, even when statistically modest, contributes to a growing picture of which source populations are energetically capable of the hadronic processes needed to produce both neutrinos and cosmic rays. For ultra-high-energy cosmic rays specifically, the neutrino connection becomes relevant through the cosmogenic neutrino signal. When the highest energy protons interact with the CMB during propagation, the pions they produce decay into neutrinos with energies in the exa-electron volt range. These cosmogenic neutrinos, also called GZK neutrinos, are a guaranteed prediction of the standard propagation scenario. If the highest energy cosmic rays are protons, and if they originate at cosmological distances, there must be a flux of exa-electron volt neutrinos produced along their path to Earth. The expected cosmogenic neutrino flux depends sensitively on the composition and source distribution of the highest energy cosmic rays. A proton-dominated composition from sources at high redshift would produce a relatively large cosmogenic neutrino flux. A heavy nucleus-dominated composition from nearby sources would produce a much smaller flux, because heavy nuclei produce fewer pions per unit distance, and because nearby sources give the pions less distance over which to accumulate. Measuring or constraining the cosmogenic neutrino flux is therefore another way to constrain the composition and source distance distribution of ultra-high-energy cosmic rays, complementing the direct shower measurements. The current upper limits on the cosmogenic neutrino flux from Augur and from the ANITA balloon experiment over Antarctica already constrain some model families. Pure proton models with sources distributed uniformly through large cosmological volumes are disfavored by the combination of the observed cosmic ray spectrum and the non-detection of a large cosmogenic neutrino flux. The constraints push toward models with either heavy composition, nearby sources, or sources that evolve differently with redshift than the simple uniform distribution would suggest. The multi-messenger picture is therefore already providing guidance even though no definitive source identification has been made. The guidance is statistical and indirect, ruling out some model families while leaving others viable, narrowing the space of plausible scenarios without yet identifying the correct one. This is how science works at the frontier, not by sudden revelation but by systematic elimination, each measurement removing some of the remaining possibilities and reshaping the space within which the answer must hide. The answer to what produces the oh my god particle and its relatives will almost certainly not come from a single spectacular event or a single breakthrough measurement. It will come from the convergence of multiple lines of evidence, better composition measurements from improved shower diagnostics, larger arrival direction statistics from expanded arrays, multi-messenger coincidences from coordinated neutrino and gamma-ray observations, and improved models of both the acceleration physics and the propagation through magnetic fields. The convergence will be slow and iterative, with each result informing the next experiment's design and the next model's predictions. But the question itself remains as sharp as it was in 1991, because the physics behind it has not changed. Something in the nearby universe accelerates charged particles to energies that strain our understanding of what astrophysical processes can achieve, then sends them across a cosmos threaded with ancient light and tangled magnetic fields. The particles arrive carrying the kinetic energy of thrown baseballs, concentrated into single atomic nuclei, as evidence of a physics that is extreme enough to be genuinely humbling. The oh my god particle and the Amaterasu particle are not anomalies to be explained away. They are data points at the extreme of a distribution that the universe keeps producing, event by rare event, year after patient year. They are demanding not just an explanation but a framework, a coherent picture of where the energy comes from, how it survives the journey, and what it means that nature can do this at all. That framework is what the next generation of instruments and theories is being built to provide. Now the story must move from detection and propagation to acceleration, because knowing that something is extreme does not explain how it got that way. The GZK limit tells us the sources must be nearby. The arrival directions tell us something about where in the nearby universe those sources might be hiding. But neither of these tells us what the sources are, and the what is where the physics becomes most challenging and most interesting. To accelerate a particle to ZV energies, nature must solve an engineering problem that dwarfs anything human civilization has attempted. The problem has both a scale component and an efficiency component. The accelerating region must be large enough to contain the particle long enough to reach the target energy. The fields must be strong enough to impart energy faster than the particle loses it to radiation and collisions. The environment must be stable enough, or at least structured enough, that the particle's trajectory brings it repeatedly into contact with the accelerating mechanism rather than simply escaping. The Hillas criterion is the starting point for any serious discussion of astrophysical acceleration. It was articulated by Alan Hillas in 1984, and while it is simple in form, it encodes a profound constraint. The maximum energy a particle of charge z can reach in an accelerating region of size r, threaded by magnetic field b, is roughly proportional to z times b times r times the speed of light. In other words, the product of field strength and size sets the energy ceiling, and a particle with higher charge has a higher ceiling at the same field and size. The criterion comes from a simple physical argument. To accelerate a particle to a given energy, the accelerating region must be large enough to contain the particle's gyration orbit at that energy. A particle gyrates in a magnetic field with a radius proportional to its momentum divided by its charge and the field strength. If the gyration radius exceeds the size of the accelerating region, the particle escapes before it can be accelerated further. Setting the gyration radius equal to the accelerating region size and solving for the maximum energy gives the Hillas criterion. This is not a detailed theory of how acceleration happens. It says nothing about whether the acceleration is by shocks, by magnetic reconnection, by rotation-driven electric fields, or by some other mechanism. It is purely a geometric and electromagnetic constraint, a necessary condition that any successful accelerator must satisfy, regardless of the mechanism. It is the minimum bar, not the maximum aspiration. When Hillas plotted the known and proposed astrophysical objects on a graph of field strength versus size, with lines of constant maximum energy overlaid, the picture was illuminating and slightly depressing. Objects that could in principle reach ZV energies were few and exotic. Gamma-ray bursts, certain types of active galactic nuclei with powerful jets, and millisecond pulsars or magnetars were among the candidates capable of satisfying the criterion. More ordinary objects like supernova remnants, which are the favored sources for the lower energy cosmic ray population, fell comfortably below the ZV line. Satisfying the Hillas criterion is necessary, but not sufficient for ZV acceleration. Even objects that have large enough size and strong enough fields must also accelerate efficiently, meaning they must impart energy faster than the particle loses it. At the highest energies, the dominant energy loss mechanism during acceleration depends on the environment. In a region with strong magnetic fields, synchrotron radiation becomes significant because any charged particle following a curved path in a magnetic field radiates. The synchrotron power scales as the square of the particle's energy and the square of the magnetic field strength, which means it grows ferociously fast as energy increases. For protons, synchrotron losses are less severe than for electrons at the same energy, because protons are nearly 2,000 times more massive, and the synchrotron power scales inversely with mass squared. This is why protons are considered better candidates for acceleration to extreme energies than electrons. But at ZV energies, even proton synchrotron losses become significant in the strongest magnetic field environments, and the requirement that the acceleration rate exceed the loss rate places additional constraints on the field strength and geometry. In environments with dense photon fields, photopion production becomes a loss mechanism during acceleration as well as during propagation. A proton being accelerated within an AGN jet or near a starburst region is surrounded by photons from the jet itself, from the accretion disk, from the surrounding starburst activity. These photons are much more energetic than the CMB, and in the proton's rest frame, they appear even more energetic. The threshold for pion production is reached at lower proton energies when the target photons are more energetic, which means that protons being accelerated in photon-rich environments start losing energy to pion production before they reach the energies that the Hillas criterion might otherwise allow. This is a cruel irony of astrophysical acceleration. The most powerful and luminous objects, the ones that generate the strongest fields and largest sizes, are also the ones with the densest photon environments. The very conditions that make them attractive as accelerators also make them more effective at destroying what they create. A powerful AGN jet, for example, is threaded with the jet's own radiation field plus the radiation from the accretion disk and the surrounding galaxy. The photon density can be high enough to limit the maximum achievable proton energy to values below what the Hillas criterion alone would suggest. Heavy nuclei face additional complications in photon-rich environments. While they have higher charge, and therefore a higher Hillas criterion ceiling at the same field and size, they are vulnerable to photodisintegration by the same photon fields that cause pion production in protons. A heavy nucleus can be photodisintegrated by photons at the source before it even leaves the accelerating region, reducing it to lighter fragments that then face their own propagation challenges. The optimal mass for ultra-high energy acceleration and survival is not obvious and depends sensitively on the specific source environment. Active galactic nuclei remain the leading class of candidate sources despite these complications, and they qualify for this status based on their sheer power. The centers of some galaxies host supermassive black holes with masses ranging from millions to billions of times the mass of the Sun. When these black holes are actively accreting material from a surrounding disk, they can generate luminosities exceeding the combined output of trillions of stars, powered by the conversion of gravitational potential energy into radiation and kinetic energy. A fraction of this power can go into driving relativistic jets of plasma that extend from the immediate vicinity of the black hole outward to distances of hundreds of kiloparsecs or even megaparsecs. These jets are the most powerful continuous energy sources known in the universe, and they satisfy the Hillas criterion comfortably for ZV acceleration in the most powerful examples. The jet plasma carries magnetic fields, moves at relativistic speeds, and contains shocks and turbulence that can act as acceleration sites. Particles caught at a shock in a relativistic jet can be accelerated by the diffusive shock mechanism, gaining energy with each crossing of the shock front. The relativistic motion of the jet provides an additional boost, because in the jet frame, the CMB appears as an energetic photon background from the forward direction. But in the observer's frame, the particles emitted by the jet can appear more energetic than their values in the jet frame. The most prominent active galactic nucleus within the GZK horizon is Centaurus A, a radio galaxy located at a distance of roughly 4 megaparsecs from the Milky Way. Centaurus A is the closest powerful radio galaxy to Earth, and it has been a favored candidate source since the earliest days of ultra-high-energy cosmic ray astronomy. It hosts a supermassive black hole of approximately 55 million solar masses and drives powerful radio jets that extend for several kiloparsecs. The galaxy has been observed across the entire electromagnetic spectrum, from radio waves to very high-energy gamma rays, and it shows evidence for particle acceleration on multiple scales. The Pierre Auger Observatory has reported a mild excess of ultra-high-energy cosmic ray events in the direction of Centaurus A and the more general CEN, a region of the sky, at a level that is consistent with a contribution from this source, but not definitive enough to claim a discovery. The excess, if real, would be consistent with Centaurus A acting as one of the sources of the highest energy cosmic rays reaching Earth. Its proximity means that even heavy nuclei might survive the journey without complete disintegration, and the jet's power is certainly sufficient in principle to satisfy the Hillas criterion for ZV energies. But Centaurus A is not the only candidate, and and focusing exclusively on it would miss the broader landscape of possibilities. Faranoff-Riley type II radio galaxies, which are characterized by edge-brightened radio lobes and powerful terminal hotspots, where the jet terminates against the intergalactic medium, are particularly attractive because their hotspots satisfy the Hillas criterion easily, and the particle densities and photon fields there may be less destructive than in the jet interior. The extended radio lobes, spanning hundreds of kiloparsecs, are magnetized structures that could also act as acceleration sites for particles with large gyration radii. Blazars, which are AGN with jets pointed nearly directly toward Earth so that the emission is Doppler boosted and we see deep into the jet, represent a different geometric realization of the same underlying physics. Their extreme apparent luminosities and the detection of very high-energy gamma rays, and in some cases high-energy neutrinos, make them energetically compelling candidates. The Blazar TXS 506+056 generated significant excitement when it was associated with a high-energy neutrino detected by IceCube in 2017, providing the most direct evidence yet that AGN jets produce high-energy hadronic interactions. Whether blazars also contribute to the ultra-high-energy cosmic ray flux is not established, but the neutrino connection makes them serious candidates. Galaxy clusters, which are the largest gravitationally bound structures in the universe and contain both magnetic fields and relativistic plasma, have also been proposed as acceleration sites. Accretion shocks at the boundaries of galaxy clusters, where infalling intergalactic gas decelerates and heats up as it joins the cluster atmosphere, can be large enough to satisfy the Hillas criterion for ZV energies if the magnetic field at the shock is sufficient. The field in the intracluster medium is measured to be in the range of tenths to a few microgauss, and cluster scales are tens of megaparsecs, which gives a Hillas product that is marginally sufficient for ZV proton acceleration in the most optimistic scenarios. The cluster accretion shock scenario is attractive because clusters are common and broadly distributed across the cosmic web, which might help explain why the arrival direction distribution of ultra-high-energy cosmic rays appears to roughly follow the large-scale structure of the local universe, without obviously clustering around specific individual objects. If many clusters contribute to the flux at some lower energy, and only the most powerful or closest ones contribute at the very highest energies, the resulting sky distribution might look like what is observed, broadly correlated with large-scale structure, with some excess in directions of known powerful systems, but without sharp peaks at specific sources. Starburst galaxies represent a qualitatively different kind of candidate because their acceleration is distributed rather than centralized. In a starburst galaxy like M82 or NGC 253, the rate of star formation is dramatically elevated, leading to a corresponding elevation in the rate of supernova explosions. Individual supernovae are not efficient enough to reach ZV energies, but their collective effect can be more powerful. When many supernova remnants overlap in time and space, their combined shock structure can create a much larger turbulent magnetized volume than any individual remnant. The superwind driven by the collective supernova activity can also accelerate particles as it flows out of the galaxy and sweeps up the surrounding intergalactic medium. M82, at a distance of roughly 5 megaparsecs, is close enough to be within the GZK horizon for a range of energies and compositions. It is detected in very high-energy gamma rays by imaging atmospheric Cherenkov telescopes, confirming that particle acceleration to at least tera-electron-volt energies occurs there. Whether the same environment can push particles to ZV energies depends on the details of the magnetic field strength and the scale of the turbulent region, and the estimates are uncertain enough that M82 cannot be definitively confirmed or excluded as a ZV source. Gamma-ray bursts represent the most extreme transient events known in the universe, and their brief but ferocious energy release makes them natural candidates for the highest energy acceleration. A gamma-ray burst releases in seconds the equivalent of the sun's entire lifetime energy output, primarily in the form of a fireball of photons and relativistic plasma. The internal shocks within the fireball and the external shock, as the fireball decelerates against the interstellar medium, can potentially accelerate particles to ZV energies if the conditions are right. The field strengths in the fireball can be enormous, and the sizes of the emitting regions, while small, can be compensated by the extreme Lorentz factors of the outflow. The difficulty with gamma-ray bursts as ultra-high-energy cosmic ray sources is timing and direction. Gamma-ray bursts are transient events lasting from fractions of a second to hundreds of seconds, and they occur at cosmological distances on average. The cosmic rays they produce would be deflected by magnetic fields and arrive at Earth as a diffuse isotropic contribution spread over long time periods after the burst, without any temporal or directional correlation with the gamma-ray signal. Even if gamma-ray bursts are the dominant source class, we could not identify them through arrival direction analysis because the cosmic rays lose all temporal information during their long journey through magnetic fields. Magnetars and millisecond pulsars represent yet another class of candidates, approaching the problem from a different angle. A newly formed magnetar, which is a neutron star with an extraordinary surface magnetic field of perhaps 10 to the 15 Gauss, can spin down rapidly as it converts its rotational kinetic energy into electromagnetic radiation. The rotating magnetic field drives a wind of charged particles that can be accelerated to extreme energies as the wind is confined and eventually escapes from the nebula surrounding the neutron star. The Hillas criterion can be satisfied because the field strength near a magnetar is enormous, even though the size scale is small. The magnetar scenario has a particular feature that makes it interesting for composition studies. The acceleration near a neutron star is occurring in an environment where the plasma is composed of material from the stellar interior and surrounding fallback material. The composition of that material is expected to include heavy nuclei produced in the nuclear burning of the progenitor star and in the neutron-rich environment of the immediate post-collapse phase. Acceleration from such an environment would naturally produce a mixed or heavy composition, which is at least qualitatively consistent with what some experiments see at the highest energies. The newborn magnetar scenario also has a natural explanation for the rarity of ZV events. Not all neutron stars form with the extreme magnetic fields of magnetars, and even among magnetars, the conditions needed for efficient ZV acceleration are not guaranteed. The event rate of relevant magnetar births in the local universe is uncertain but potentially consistent with the observed ultra-high-energy cosmic ray flux if only a fraction of newborn magnetars contribute effectively. The diversity of candidate source classes reflects the genuine uncertainty about what astrophysical process dominates at the highest energies. Each class has theoretical arguments in its favor and observational hints supporting it, and none has been definitively established as the dominant source. The situation may be further complicated by the fact that the highest energy cosmic rays might not come from a single dominant source class, but from a mixture of different populations contributing at different energies and in different directions. Sorting out this mixture requires progress on multiple fronts simultaneously. Better composition measurements would reduce the uncertainty in rigidity and therefore in the interpretation of arrival directions. Larger statistics of high-energy events would improve the sensitivity to anisotropy and clustering. Multi-messenger coincidences between cosmic rays, neutrinos, and gamma rays would provide additional constraints on the source environments. Improved models of extragalactic magnetic fields, potentially informed by future measurements from LOFAR and the Square Kilometre Array in radiopolarization, would reduce the uncertainty in backtracking from observed arrival directions to source positions. The acceleration question also connects to fundamental particle physics in ways that are not always obvious. At ZV energies, the interactions of cosmic rays with matter and radiation probe physics at center-of-mass energies that are decades beyond current accelerator reach. If there are new physics phenomena at those energy scales, they could affect both the acceleration and the propagation in ways that might be observable. Lorentz invariance violation, which would modify the energy-momentum relation for particles at extreme energies, could raise or lower the effective GZK threshold. New particles or interactions could open new propagation channels or close existing ones. These possibilities are not mainstream physics, but they are not completely dismissed. The GZK limit relies on Lorentz invariant kinematics to set the threshold for pion production. If the transformation properties of the proton's momentum and energy differ from the standard prediction at extreme values of the Lorentz factor, the threshold energy for pion production would shift. A shift large enough to move the threshold above the energies of observed events would make the GZK suppression much weaker and would allow protons to travel much larger distances without significant energy loss. The oh my god particle and the Amaterasu particle would then be consistent with sources at much greater distances, which would relax the requirement for a nearby powerful accelerator. Testing Lorentz invariance at the energies relevant for ultra-high-energy cosmic ray propagation is extraordinarily difficult because the deviations from standard behavior, if they exist, are expected to be tiny corrections to the fundamental dispersion relation, growing with some power of energy divided by the Planck scale. The Planck scale is 10 to the 19th GeV, which is 15 orders of magnitude above the LHC energy, and about 4 orders of magnitude above the energies of the most extreme cosmic rays. Even at the oh my god particle's energy, the ratio of the particle's energy to the Planck scale is only about 10 to the minus 4, suggesting that any Planck-suppressed deviation would be extremely small. Nevertheless, the propagation distances involved are so enormous, and the number of background photon encounters so large that even tiny modifications to the threshold energy could have cumulative effects that might be observable in the spectrum. Some analyses of the GZK threshold and the spectrum have been used to place constraints on Lorentz invariance violation parameters, contributing to the broader effort to test fundamental symmetries at the highest available energies. The cosmic rays become a tool for particle physics experiments at energies no accelerator can reach. This dual role of ultra-high-energy cosmic rays, as both astrophysical messengers and particle physics probes, gives the field a unique position at the intersection of two disciplines. The astrophysics community cares about where they come from and what that tells us about the most extreme objects in the universe. The particle physics community cares about how they behave and what that tests about fundamental physics. Both communities share an interest in making the measurements more precise and the interpretations more robust. The field's central challenge, as it has always been, is working backward from a sparse dataset of shower observations to a rich three-dimensional reality of sources, fields, and particles. The backward direction is always harder than the forward direction. Given a source and a set of field models, one can simulate the propagation and predict the observed distribution. Given the observed distribution, inferring the source distribution and field structure is an ill-posed inverse problem with many solutions that fit the data within uncertainties. Progress on this inverse problem requires both more data and better physics inputs. The more data requirement drives the construction of larger experiments. The better physics inputs requirement drives measurements of hadronic interactions at the LHC and future higher-energy colliders, theoretical work on magnetic field evolution in large-scale structure simulations, and observational campaigns to map the intergalactic magnetic field more directly. The problem is hard enough that progress requires contributions from many disciplines working in parallel, and the solution, when it comes, will draw on all of them. The oh my god particle sits at the center of this web of connected problems, having initiated a decades-long investigation that has grown from a single event in a Utah desert to a global effort involving multiple observatories, thousands of researchers, and collaborations spanning 6 continents. It forced questions that were not being asked clearly before 1991, and it gave the field a benchmark that every theory and every instrument must confront. The particle itself is long gone, its energy dissipated into a brief shower of secondaries that swept across the Utah salt flats and left their signals in the fly's eyes electronics before disappearing into the ground and the air and the long history of detections that followed. But its implications persist, as sharp and demanding as they were on that October night, asking what the universe is capable of and whether we have the instruments and the understanding to find out. The atmosphere is our laboratory, and it is a laboratory we did not design and cannot modify, working in conditions we cannot fully control, using processes we cannot completely simulate. The primary cosmic ray almost never reaches our instruments intact. At ultra-high energy, the first collision happens far above the ground, often higher than commercial flight paths, and the original particle is effectively erased in that first violent encounter. What we detect instead is a fast-evolving cascade written into air, light, radio, and ground signals, a translated version of the original message that requires careful interpretation to yield the information we seek. The translation is imperfect in ways that matter. Every step from the original primary particle to the final recorded signal introduces assumptions, models, and uncertainties that accumulate into the systematic errors that dominate the field's most important debates. Understanding those uncertainties is not a technical footnote to the real story. It is the real story, because the difference between discovering new physics and misidentifying a calibration error depends entirely on how well those uncertainties are understood and controlled. When a primary cosmic ray enters the top of the atmosphere, it is traveling at a speed so close to the speed of light that the distinction is operationally meaningless for most purposes. The particle carries its enormous energy in the form of relativistic kinetic energy, and that energy will be distributed across the atmosphere in the microseconds following the first collision. The atmosphere at that moment becomes both the target and the detector, and the shower it produces is the only evidence we will have of what arrived. The first collision occurs at an altitude that depends on the primary's cross-section for interaction with atmospheric nuclei. Protons interact with characteristic cross-sections that have been measured in accelerator experiments up to LHC energies and must be extrapolated beyond. Heavy nuclei interact at somewhat higher altitudes on average because their larger nuclear radius presents a bigger geometric cross-section to the first atmospheric target. The height of the first interaction fluctuates from event to event according to a statistical distribution because quantum mechanics makes individual interactions probabilistic even when the average behavior is predictable. That first interaction is a catastrophic event on the nuclear scale. The primary particle, whether a proton or a heavy nucleus, strikes an atmospheric nitrogen or oxygen nucleus with a center of mass energy that dwarfs anything achievable in a laboratory. The collision creates a spray of secondary particles, pions, kaons, nucleons, and other hadrons produced by the strong nuclear force, along with photons and leptons from their subsequent decays. The number of secondary particles produced in the first interaction scales roughly with the logarithm of the center of mass energy, so the first collision creates a few dozen to a few hundred particles carrying fractions of the primary's energy. The secondary particles then propagate through the atmosphere, interacting again when they have traveled roughly an interaction length through the air. The charged pions, which are the most abundantly produced secondaries, can either interact hadronically before decaying or decay into muons and neutrinos before interacting. The competition between these two fates depends on the pion's energy. High-energy pions tend to interact before they can decay because their time-dilated lifetime gives them a long decay length, but their interaction length in air is shorter than that decay length at the energies relevant for ultra-high-energy showers. Lower-energy pions are more likely to decay before interacting, and the decay products include muons that can survive to reach the ground. Neutral pions decay almost immediately into pairs of photons on timescales of about 10 to the minus 16 seconds, much too short to travel any significant distance through the atmosphere before decaying. Each neutral pion therefore contributes 2 high-energy photons to the shower. Those photons then initiate electromagnetic subshowers through pair production and Bremsstrahlung. A high-energy photon converts into an electron-positron pair in the electric field of an atmospheric nucleus, and each member of the pair then radiates further photons through Bremsstrahlung as it decelerates in the atomic electric fields. This alternating process of pair production and Bremsstrahlung creates an exponentially growing electromagnetic cascade until the particle energies fall below the critical energy, where ionization losses start to dominate over radiation losses. Below the critical energy, particles lose energy primarily by ionizing air molecules rather than by creating new particles. Ionization losses are continuous and relatively gentle rather than catastrophic, and they deplete the shower gradually rather than causing further multiplication. The shower therefore reaches a maximum number of particles at a depth where the average particle energy equals the critical energy, and then it begins to thin as more particles fall below the threshold for further multiplication than are created by the remaining high-energy component. The depth of this maximum, denoted Xmax and measured in grams per square centimeter of air traversed, is one of the most important observables for cosmic ray physics because it carries information about the primary particle's nature. A primary that interacts first high in the atmosphere, such as a heavy nucleus with its large interaction cross-section, will reach shower maximum earlier in terms of depth compared to a primary that penetrates deeper before its first interaction. On average, lighter primaries penetrate deeper and reach maximum at a greater atmospheric depth. This average behavior is only part of the story because the fluctuations around the average are equally informative. For a pure proton primary, the depth of the first interaction fluctuates substantially from event to event because the first interaction point follows a Poisson distribution in terms of the number of interaction lengths traversed. Since the first interaction largely sets the depth of the subsequent shower development, this fluctuation propagates into a wide distribution of Xmax values for proton showers. For a heavy nucleus like iron, the first interaction occurs in a superposition of many independent nucleon-nucleon collisions happening nearly simultaneously, and the statistical averaging across 56 nucleons significantly reduces the fluctuations. Iron showers have a narrower Xmax distribution than proton showers, centered at a smaller average depth. Measuring the mean and width of the Xmax distribution across a population of events therefore provides statistical leverage on the average composition. If the measured mean Xmax matches proton expectations and the distribution is wide, the data favor a light composition. If the mean is smaller and the distribution is narrow, the data favor a heavy composition. Mixed compositions produce intermediate values that can in principle be decomposed into fractions of different mass groups, though the decomposition requires careful modeling and becomes degenerate if the mass fractions are not well constrained by additional observables. The fluorescence detector is the primary instrument for measuring Xmax because it can track the longitudinal development of the shower through the atmosphere as a function of depth. As the shower descends, the fluorescence light produced by nitrogen excitation traces the number of charged particles at each depth, and the resulting longitudinal profile directly shows where the shower peaked. Peak is identified by fitting a functional form to the measured profile, typically a Gauss-Hill's function that describes the rise and fall of the shower with depth, and the fitted maximum is extracted as Xmax. The measurement requires careful atmospheric monitoring because the fluorescence light is absorbed and scattered between the shower and the detector. Aerosols scatter light, and molecular scattering rarely scatter light at rates that depend on the wavelength and the atmospheric conditions. Both Auger and the telescope array deploy extensive atmospheric monitoring systems, including laser shots at known energies that probe the transmission along lines of sight from the detector to the shower, and cloud monitoring systems that track the presence of obscuring clouds. The atmospheric corrections are applied event by event, and their uncertainties contribute directly to the systematic error on Xmax measurements. The photon yield from nitrogen fluorescence, which is the fundamental quantity that converts a measured light signal into an estimate of the number of charged particles in the shower, has been measured in laboratory experiments and in dedicated airborne experiments. The yield depends on altitude through the air pressure and temperature dependence of the collisional deexcitation processes that compete with fluorescence emission. The most accurate measurements of the fluorescence yield have reduced this systematic uncertainty substantially, but it remains a contribution at the level of several percent to the overall energy scale uncertainty. Rayleigh scattering from molecular oxygen and nitrogen is well understood from first principles because the molecular density profile of the atmosphere is measured by weather balloons and well characterized as a function of altitude and season. This contribution to the systematic error is smaller and better controlled than the aerosol contribution. The aerosol burden varies on timescales from hours to days, depending on weather patterns, dust intrusions from desert regions, and other atmospheric phenomena. Monitoring it continuously and accurately requires a sophisticated atmospheric instrumentation suite that has been developed and refined over the operating lifetime of both major experiments. Surface arrays measure a different and complementary set of shower observables. The signal in each detector station records the local density of shower particles at a specific location and time. From the pattern of signals across the array, the shower geometry is reconstructed. The core location where the shower axis intersects the ground, the arrival direction from the timing pattern, and the shower size from the lateral distribution of particle densities. The energy is then inferred from the signal at a specific reference distance from the core, chosen to minimize the sensitivity to shower fluctuations and composition. For the Pierre Auger Observatory's Water-Cherenkov detectors, the reference distance is 1,000 meters from the shower core, and the quantity extracted there is called S, 1,000, the signal in vertical equivalent muons per square meter. This quantity is then converted to primary energy using a calibration derived from hybrid events, where the same shower was observed by both the surface array and the fluorescence detector. The fluorescence measurement provides a calorimetric energy estimate that is more directly related to the primary energy, and the relationship between S, 1000, and the fluorescence energy calibrates the surface array's energy scale. This cross-calibration between surface array and fluorescence is one of the most important methodological advances of the hybrid era. It transfers the calorimetric accuracy of the fluorescence measurement to the large exposure of the surface array, which operates with much higher duty cycle. The resulting combined energy scale is better controlled than either method alone, and its systematic uncertainty is constrained by the consistency between the two independent measurements. Disagreements between the surface array and fluorescence estimates for the same event expose systematic errors that can then be investigated and reduced. The telescope array uses a similar hybrid approach with its own cross-calibration procedure, but the scintillator-based surface detectors respond differently to shower particles than Auger's Water-Cherenkov tanks. Scintillators have a roughly equal response to electromagnetic particles and muons in terms of deposited energy, while Water-Cherenkov detectors are more sensitive to muons relative to electromagnetic particles because muons penetrate the water volume and deposit their energy continuously, while electromagnetic particles are absorbed quickly at the water surface or near it. This difference in detector response means that the two experiments are sensitive to different mixtures of shower components, and comparison of their results for the same shower population can in principle provide information about the muon content. The muon content of ultra-high-energy cosmic ray showers has emerged as a particularly important and somewhat troubling observable. Muons are produced primarily in the hadronic component of the shower from the decay of charged pions and kaons. The total muon number in a shower is therefore related to the hadronic multiplicity of the first interaction and subsequent interactions, as well as to the branching ratio between neutral pion production, which feeds the electromagnetic component, and charged pion production, which eventually feeds the muonic component. The problem, which has been called the muon puzzle or the muon deficit problem, is that the measured muon content of ultra-high-energy cosmic ray showers consistently exceeds what the shower simulations predict. The excess is typically at the level of 30 to 50%, meaning the showers produce about 1:3 to 1. 5 times as many muons as the simulations expect for any reasonable primary composition. This excess has been observed independently by multiple experiments using different detection techniques and different shower reconstruction approaches, which makes it unlikely to be simply a calibration error. The muon puzzle has deep implications because muon number is one of the primary handles on composition. If the simulations systematically underpredict muon numbers, then compositions inferred from muon measurements are biased. The apparent heavy composition seen in some analyses could be partly or entirely a reflection of incorrect hadronic physics rather than a genuine dominance of heavy nuclei in the cosmic ray beam. Alternatively, the muon excess could indicate new hadronic physics at the extreme energies of the first interaction, something genuinely different about how quarks and gluons interact at center of mass energies beyond the LHC reach. The LHC has contributed to understanding this problem by providing measurements of hadronic interaction properties at the highest currently achievable energies. The totem experiment measured the proton-proton total cross-section and elastic scattering at 13 tera-electron volts, and various LHC experiments measured particle production in the forward region relevant for cosmic ray shower modeling. These measurements have been incorporated into the latest versions of the hadronic interaction models used in cosmic ray simulations, and the updated models do produce somewhat more muons than their predecessors, but the improvement is not sufficient to fully close the gap with observations. The muon excess is reduced but not eliminated by the LHC-tuned models. The theoretical explanations for the remaining muon excess span a range of possibilities. Some proposals invoke a modified ratio of neutral to charged pion production at extreme energies, perhaps related to the formation of quark-gluon plasma states in the initial collision. Others invoke enhanced production of rho mesons at the expense of pions, since rho mesons decay differently and can enhance muon production relative to neutral pion production. Some proposals involve more radical changes to the hadronic interaction picture, such as enhanced multiplicity or different energy dependence of the cross-section at extreme energies. Whatever the resolution of the muon puzzle turns out to be, it illustrates a general principle that becomes increasingly important as the field pushes toward higher energies and better precision. The interpretation of cosmic ray observations cannot be fully separated from the particle physics of hadronic interactions at energies beyond laboratory reach. The two fields are entangled in a way that requires progress in both simultaneously. Cosmic ray physics needs hadronic interaction models to interpret showers, and those models need testing against new energy regimes that only cosmic ray physics can access. The relationship is circular but not vicious, as long as both sides acknowledge the uncertainties clearly. Radio detection has emerged over the past decade as a promising complement to the established fluorescence and surface array methods, adding a third independent technique that has different systematic errors and can operate in conditions where other methods fail. When a shower develops in the atmosphere, the geomagnetic field exerts a force on the positive and negative charges in the shower that deflects them in opposite directions, creating a time-varying current that radiates coherently at radio frequencies. There's also a contribution from the time-varying charge excess in the shower front, as electrons are knocked out of air molecules and positrons annihilate, creating a net negative charge moving downward with the shower. The radio emission from cosmic ray showers is coherent below roughly 100 MHz, meaning that the contributions from different parts of the shower front add constructively rather than randomly. Coherent emission is enormously more powerful than incoherent emission. The power scales as the square of the number of emitting particles rather than linearly, which means the radio signal from a high-energy shower can be detected over distances of kilometers with modest radio antennas. The threshold energy for radio detection with practical antenna spacings is around 100 peta-electron volts, which is below the ultra-high-energy range, but not by an enormous factor. Radio detection offers several attractive features for cosmic ray physics. Radio antennas can operate continuously regardless of weather and daylight, with a duty cycle approaching 100%, similar to surface arrays but unlike fluorescence detectors. They are relatively inexpensive compared to fluorescence telescopes, which means they can potentially be deployed over large areas without prohibitive cost. The radio signal encodes information about the three-dimensional structure of the shower in a different way from fluorescence or ground particle measurements, providing complementary composition sensitivity. The radio signal's dependence on shower development and on the geomagnetic geometry means that careful analysis of the radio pulse shape and polarization can provide X-max measurements with resolution competitive with fluorescence detectors, while operating continuously. Several experiments including AERA at Auger, Tunkarex in Siberia, and various smaller arrays have demonstrated the feasibility of radio detection and developed the reconstruction techniques needed to extract shower parameters from radio waveforms. The technique has matured from a proof of concept into a tool that provides genuinely useful physics results. The Pierre Auger Observatory has incorporated an ambitious radio upgrade called Auger Prime that deploys surface-mounted radio antennas alongside the existing Water-Cherenkov detectors. Each surface detector station will be equipped with a scintillator panel on top and a radio antenna above that, measuring 3 different aspects of each shower at each station simultaneously. The scintillator is more sensitive to the electromagnetic component of the shower and less to muons, while the Water-Cherenkov detector is relatively more sensitive to muons. The ratio of signals between scintillator and Water-Cherenkov at the same location provides additional composition information on an event-by-event basis without requiring full longitudinal profile reconstruction. The Auger Prime upgrade also extends the energy threshold for composition-sensitive measurements by improving the single-station signal-to-noise ratio and adding the radio measurement for the largest showers. The goal is to accumulate composition-resolved statistics in the energy range above 50 exa-electron volts at a rate sufficient to test the anisotropy hypotheses that have been building from the first decade of Auger operations. If the arrival direction distribution of light proton-like events differs from that of heavier iron-like events at the same energy, it would provide powerful evidence that the two composition groups originate from different source populations, and the anisotropy of each group would carry separate information about the respective source distributions. The telescope array is pursuing a parallel expansion called T-Ax4, which will quadruple the detector area by deploying additional scintillator stations over a 2,800 square kilometer footprint. The expanded area targets the northern sky hotspot that the existing array has identified, covering it more uniformly and accumulating statistics at a rate that should resolve whether the excess is a genuine source concentration or a statistical fluctuation. T-Ax4 also adds radio antennas at selected stations to develop radio reconstruction capabilities compatible with those at Auger, allowing eventual cross-calibration of radio-based composition measurements between the two hemispheres. Space-based detection represents the most ambitious extension of the observational program, offering the possibility of collecting cosmic ray showers from orbit using telescopes pointed downward at the atmosphere rather than instruments deployed on the ground looking upward at the sky. A space-based fluorescence detector looking down at the atmosphere from an orbital altitude of several hundred kilometers can observe an enormous footprint, potentially millions of square kilometers, which would give it an exposure that dwarfs even the largest ground-based arrays. The challenge is achieving sufficient sensitivity and resolution from orbit to reconstruct the shower energy and direction with the precision needed for physics analysis. POEMMA, the probe of extreme multi-messenger astrophysics proposed for a NASA mission, would deploy 2 space telescopes in a formation orbit, providing stereofluorescence coverage of cosmic ray showers, and also searching for radio signals from ultra-high-energy neutrinos interacting in the Antarctic ice or the lunar regolith. The stereo baseline would allow geometric reconstruction of shower trajectories with better angular resolution than a single telescope could achieve, reducing the systematic uncertainty on arrival directions. The enormous exposure would accumulate events at the highest energies at rates sufficient to test anisotropy models with high statistical power. GMUSO, the Extreme Universe Space Observatory on the Japanese experiment module of the International Space Station, has demonstrated the feasibility of detecting atmospheric fluorescence from orbit with a smaller instrument. The EUSO SBB-2 balloon-borne version tested the detector technology and reconstruction algorithms at stratospheric altitude. The lessons from these Pathfinder missions are being incorporated into the design of the full space observatory, which would need to achieve stringent requirements on optical efficiency, background rejection, and atmospheric monitoring to deliver reliable physics results from orbit. The atmospheric monitoring challenge is particularly acute for space-based observation because the fraction of the observed atmosphere that is clouded or otherwise disturbed is larger for a wide-field instrument looking at a large footprint than for a ground-based instrument looking at a limited sky volume. Cloud identification from orbit requires either dedicated cloud monitoring instruments or analysis techniques that can identify and reject obscured events using the shower data themselves. Both approaches are being pursued, and the resulting systematic uncertainties on the energy scale and efficiency estimates are subjects of active research. Beyond the direct detection of charged cosmic rays, the atmosphere also becomes a detector for neutrinos and gamma rays in ways that are relevant to the multi-messenger picture. Ultra-high-energy neutrinos interacting in the atmosphere produce showers that are distinguishable from hadronic cosmic ray showers by their deeper penetration and different shower profile, because neutrinos interact very weakly, and their first interaction occurs much deeper in the atmosphere than a primary proton or nucleus. The Auger Observatory has searched for such deeply developing events in its dataset and derived upper limits on the flux of ultra-high-energy neutrinos that constrain the cosmogenic neutrino models. The non-detection of cosmogenic neutrinos is itself a result because it rules out model families that would predict a large flux. Specifically, models with pure proton composition and sources distributed uniformly at cosmological distances predict a cosmogenic neutrino flux that should have been detected by Auger if the model were correct. The absence of detection pushes toward models with either heavy composition, nearby sources concentrated in the local universe, or sources that do not evolve strongly with redshift. Each of these alternatives has implications for source identification and acceleration physics. Future neutrino detectors with sensitivity at exa-electron-volt energies would significantly tighten these constraints. The IceCube Gen 2 upgrade, which would expand the instrumented volume of the IceCube Neutrino Telescope by roughly a factor of 8, would improve sensitivity to high-energy astrophysical neutrinos and potentially detect the cosmogenic flux if it is at the level predicted by optimistic models. The RNOG experiment, deploying radio antennas in the ice at Summit Station, Greenland, and the proposed grand array of radio antennas across large areas of terrain target the cosmogenic neutrino flux at the highest energies where the existing constraints are weakest. The connection between cosmic ray sources and gamma ray sources adds another layer to the multi-messenger picture that both constrains and enriches the interpretation. When cosmic rays are accelerated in environments with sufficient density of matter or radiation, the pion production that occurs during acceleration produces gamma rays as well as neutrinos through neutral pion decay. The gamma ray emission from a cosmic ray source therefore carries information about the target density and the accelerated particle spectrum. Observations by the Fermi Gamma Ray Space Telescope, the MAGIC and HESS and VERITAS imaging atmospheric Cherenkov telescopes, and the HAWC and LHASO Water Cherenkov gamma ray arrays have identified hundreds of sources of high-energy gamma rays and are beginning to connect them to potential cosmic ray accelerators. LHASO in particular, the Large High-Altitude Air Shower Observatory in Tibet at an altitude of 4,400 meters, has detected a collection of ultra-high-energy gamma ray sources within the Milky Way at energies exceeding a peta-electron volt. These P-vatrons, as they have been called, are sites of particle acceleration within our galaxy reaching at least peta-electron volt energies, demonstrated by the detection of gamma rays at those energies. P-vatrons are not ZV accelerators, but they demonstrate that nature can build galactic particle accelerators far beyond what simple supernova shock models easily predict, and understanding how they work may illuminate the mechanisms relevant at even higher energies in extragalactic sources. The Cherenkov Telescope Array, currently under construction at sites in Chile and the Canary Islands, will provide a major improvement in sensitivity for very high-energy gamma ray astronomy. Its Its extended energy range from tens of GeV to hundreds of TeV or beyond, and its improved angular resolution and collecting area will allow more precise identification of the emission regions within extended sources and more accurate measurement of the spectral cutoffs that reveal the maximum energies of accelerated particles. If a source is accelerating protons to ZeV energies, the resulting cascade of gamma rays from neutral pion decay and subsequent electromagnetic processes should be detectable at lower energies, where the flux is higher, providing a multi-wavelength signature of the acceleration process. The combination of all these observational tools, surface arrays, fluorescence detectors, radio antennas, space telescopes, neutrino detectors, and gamma-ray observatories, represents an unprecedented experimental capability that would have been unimaginable when Victor Hess climbed into his balloon in 1912. The question of what creates ultra-high-energy cosmic rays is being approached simultaneously from many directions, with each instrument providing a different facet of the answer, and each facet constraining what the others can mean. But the answer itself remains elusive because the tools, while powerful, are still limited by statistics at the highest energies where the fundamental questions are most acute. The rate of events above 100 exa-electron volts is 1 particle per square kilometer per century, which means that even a detector array covering 1,000 square kilometers accumulates only 10 events per year at that energy and above. Building the statistics needed to identify sources and test composition models at these energies requires either much larger arrays or much longer operation times, and ideally both. The shower reconstruction techniques, while vastly improved since the fly's eye era, still carry systematic uncertainties that are large enough to affect the most important physics conclusions. The hadronic interaction models, while constrained by LHC measurements, still extrapolate into unknown territory for the first interaction of the highest energy events. The magnetic field models, while improving as new radiopolarization surveys accumulate data, still leave substantial uncertainty in the backtracking from arrival direction to source direction. Each of these limitations is an active research problem, and progress on each contributes to narrowing the space of viable explanations. The atmosphere, our accidental laboratory, is a generous and frustrating partner in this investigation. It is generous because it makes shower detection possible across huge areas with relatively modest instrumental investments. It is frustrating because it introduces atmospheric variability that must be monitored continuously, hadronic physics uncertainties that cannot be avoided, and a translation process from shower to primary that is always indirect and model-dependent. Working with it requires constant vigilance and careful validation, and the best results come from comparing multiple methods applied to the same events rather than trusting any single technique. The technical apparatus of shower detection, reconstruction, and composition measurement is not background to the central story. It is the central story in a very practical sense, because the physics questions are only as well posed as the measurements that constrain them. Every claim about the energy spectrum, the arrival direction distribution, or the composition must be understood in the context of the systematic uncertainties that limit its precision. And every proposed explanation of the origin of ultra-high-energy cosmic rays must be consistent with what the measurements actually say, rather than with an idealized version of the measurements that would be more convenient for the explanation. The oh my god particle is a perfect illustration of this principle. Its energy of 320 exa-electron volts carries an uncertainty of about 90 exa-electron volts, which is roughly 30%. That uncertainty is not a minor technical detail. It is the difference between an event that challenges the GZK limit modestly and one that challenges it dramatically. It is the difference between requiring a source at 20 megaparsecs and requiring one at 5 megaparsecs. It affects every conclusion drawn from the event, and the conclusions would look different if the energy were at the low end of the range rather than the central value. Modern events like the Amaterasu particle are reconstructed with smaller relative uncertainties thanks to improved techniques and better atmospheric monitoring, but the absolute uncertainty at 240 exa-electron volts is still tens of exa-electron volts. And the directional uncertainty, which determines how close to the local void the true arrival direction must be, includes contributions from shower geometry reconstruction and from the statistical noise in the timing pattern across the array. The error circle on the arrival direction is a few degrees, and a few degrees at cosmic distances corresponds to a spatial uncertainty of many megaparsecs in the transverse direction. So the void direction is a central value, not an exact result, and the uncertainty on that central value is large enough to encompass alternative directions that point toward the edge of a nearby filament or toward a background AGN that was not properly accounted for. The mystery is real, but it is bounded by uncertainties that make a definitive statement premature. What the Amaterasu particle tells us is that this direction and energy combination is possible and apparently real, not that the source is definitely in the void, rather than in the surrounding structures. This kind of precision about imprecision is essential for understanding what cosmic ray observations actually constrain and what they leave open. The temptation to overinterpret individual events is strong, particularly for events at the very top of the energy spectrum, where each one feels like a message from physics at its most extreme. But overinterpretation leads to theories built on sand, and the field has learned from experience that apparent discoveries at the level of one or two events often become less significant as more data accumulate. The honest position, and the scientifically productive one, is to treat each extreme event as a constraint rather than a revelation. The oh my god particle constrains the source and propagation models in specific ways. The Amaterasu particle adds additional constraints that are partly consistent with the earlier event and partly independent. Together with the statistical information from the full spectra and arrival direction distributions of both Auger and the telescope array, they define a set of requirements that any successful model must satisfy. The model that satisfies all of them simultaneously, while remaining consistent with astrophysical observations in other wavelengths and with particle physics in the laboratory, will be the answer to the central question. Finding that model is the work of the coming decades, and it will require the next generation of instruments, improved hadronic interaction measurements at future colliders, better maps of extragalactic magnetic fields, and continued theoretical development of the acceleration and propagation physics. The atmosphere will continue to be our laboratory, imperfect and irreplaceable, and the showers it generates will continue to be the primary evidence from which we reconstruct the universe's most extreme processes. The universe's accelerators must be identified not just by what they can produce in principle, but by whether they can actually deliver extreme particles to Earth in numbers consistent with what we observe. This distinction between what is theoretically possible and what is observationally required separates the serious candidates from the merely dramatic ones. Nature does not reward imagination without constraint, and the constraints on ultra-high-energy cosmic ray sources are severe enough to eliminate most of the astrophysical objects we know about. To approach the source question systematically, it helps to think about what the observations require, and then ask which known or plausible objects can meet those requirements simultaneously. The requirements come in several categories. The maximum achievable energy must reach the observed values. The efficiency of acceleration must be high enough that energy is not immediately radiated away. The environment must be transparent enough that the accelerated particles can escape, and the source must be located within the GZK horizon for the relevant composition and energy. Each requirement filters the candidate list, and the intersection of all of them is small. The energy requirement is the most fundamental and the most dramatic. To produce a particle at 320 exa-electron volts, the accelerating electromagnetic field must do work on the particle at a rate sufficient to push it past all the radiation and interaction losses, while it is still within the accelerating region. This is not just about the Hillas criterion, though the Hillas criterion is necessary. It is also about the balance between acceleration rate and loss rate, which depends on the specific field geometry and particle trajectory in a way that the Hillas criterion does not capture. In the most optimistic models, where every pass through the acceleration region is fully efficient, the Hillas criterion tells us the minimum requirements. For a proton at 320 exa-electron volts, we need B times R in certain Gaussian CGS units to be at least a few times 10 to the 24th, which in practical terms means a field of a microgauss over a megaparsec scale, or a milligauss over a kiloparsec scale, or a Gauss over a parsec scale. These combinations are realized in different astrophysical environments, and the Hillas plot places different object classes in different regions of the field size parameter space. Galaxy clusters sit at large size but relatively weak field, around a microgauss over tens of megaparsecs. They are marginal for ZV proton acceleration, possibly adequate for the largest and most magnetized clusters, but not for typical ones. AGN jets sit at moderate size and moderate to strong field, with conditions that vary enormously along the jet from the highly relativistic inner regions near the black hole to the slowly moving outer lobes. The inner jet within a few parsecs of the central engine has the strongest fields but the smallest size, while the outer lobes have weak fields but extend for hundreds of kiloparsecs. The product of field and size varies along the jet, and the maximum is achieved at different points in the jet structure, depending on how the field evolves with distance. Magnetars represent the other extreme, fields of 10 to the 15 Gauss over sizes of kilometers, giving a Hillas product that technically satisfies the ZV criterion for iron nuclei, though the detailed acceleration physics in the magnetar wind nebula is more complex than the simple criterion suggests. The newborn magnetar scenario invokes the early phase of neutron star formation when the field is strongest and the spin-down luminosity is highest, and the accelerating region is the expanding wind nebula that forms as the magnetar spins down. The particles must escape the nebula before they encounter too many high-energy photons from the magnetar's own luminosity, which is a tight constraint on the efficiency of the escape. Gamma-ray bursts occupy their own special position in the Hillas diagram because their Lorentz factors introduce a boost that effectively expands the accessible energy range. In the rest frame of the ultrarelativistic fireball, the local field can be enormous, and the local size is sufficient, and the corresponding particle energy in that frame might only be modest. But in the observer's frame, the Lorentz boost amplifies the energy by the fireball's Lorentz factor, potentially reaching ZV energies for fireball Lorentz factors of several hundred and reasonable field and size parameters. The challenge for gamma-ray burst acceleration is getting particles out of the fireball without losing them to the intense radiation field, and detailed models must address this escape problem carefully. The efficiency of acceleration matters enormously for whether a candidate source can reach observed energies. Consider shock acceleration, specifically because it is the most developed theoretical framework for astrophysical acceleration and the one most directly applicable to the candidate sources. In diffusive shock acceleration, a particle gains energy on each cycle of crossing the shock front from downstream to upstream and back. The energy gain per cycle is proportional to the shock velocity, and the escape probability per cycle is also proportional to the shock velocity for non-relativistic shocks. The power loss spectrum that results from this process, with a spectral index that depends on the compression ratio of the shock, is one of the great theoretical successes of cosmic ray physics. For ultra-high energy acceleration, the shock must be accelerating efficiently under conditions where synchrotron losses are not negligible. A particle with energy E in a magnetic field B radiates synchrotron power proportional to E squared times B squared. The acceleration rate depends on the shock velocity and the diffusion coefficient for the particle in the turbulent field ahead and behind the shock. Setting the acceleration rate equal to the loss rate gives the maximum energy at which the particle can be maintained, and for conditions realistic for AGN jets and supernova remnants, this maximum is often below what the oh my god particle requires. In relativistic shocks, the situation is more complicated because the standard diffusive shock acceleration theory must be modified. A particle crossing a relativistic shock front gains much more energy per crossing than in a non-relativistic shock because the velocity difference across the shock is a large fraction of the speed of light. This makes relativistic shocks potentially much more efficient accelerators per crossing, but the physics of particle scattering in relativistic shock environments is less well understood than in the non-relativistic case. The diffusion coefficient in relativistic turbulence and the resulting confinement time of particles near the shock are subjects of active theoretical and computational research. Magnetic reconnection has received increasing attention as an alternative or complementary acceleration mechanism, particularly in the context of relativistic jets and pulsar wind nebulae. In magnetic reconnection, oppositely directed magnetic field lines are driven together and reconnect, converting magnetic energy into kinetic energy of the plasma and into particle acceleration. The process can create large localized electric fields that accelerate particles efficiently in a way that is not limited in the same way as shock acceleration. Models of particle acceleration in reconnection layers predict hard power loss spectra extending to high energies, with cutoffs set by the conditions in the reconnection region. Reconnection acceleration is particularly relevant for gamma-ray bursts and for relativistic AGN jets because these environments are expected to have strongly magnetized plasma, where reconnection is a natural energy release mechanism. The jets of radial-out AGN are inferred to be magnetically dominated near the central engine, and the instabilities that develop as the jet propagates can trigger reconnection events that accelerate particles efficiently. Whether these events can produce particles at ZV energies depends on the magnetic field strength, the size of the reconnection region, and the particle's ability to remain in the acceleration zone long enough to reach extreme energies. Stochastic acceleration, in which particles gain energy through repeated random interactions with magnetized turbulence rather than through ordered acceleration at a single shock or reconnection site, is another mechanism that may contribute at extreme energies. In a turbulent magnetized medium, particles can gain or lose energy in each interaction with a turbulent fluctuation, and if the turbulence is properly configured, the net effect can be a gain that persists long enough to reach high energies. Second-order Fermi acceleration, named because the energy gain scales as the square of the velocity of the scattering centers, was historically considered too slow to be relevant, but in relativistic turbulence, the process can be significantly faster. The interplay between multiple acceleration mechanisms in a single source environment makes the theoretical problem considerably more complex than considering each mechanism in isolation. In a powerful AGN jet, the particle might first be accelerated by the initial shock at the jet base, then undergo stochastic acceleration in the turbulent jet body, then be further accelerated by a termination shock when the jet hits the intergalactic medium, and finally confined in the magnetized lobe while losing energy to synchrotron and inverse Compton. The maximum energy achieved in this compound environment depends on which stage is the bottleneck and how efficiently the particle moves from one stage to the next. The escape of accelerated particles from the source environment is often the limiting factor rather than the acceleration itself. In dense radiation fields near an AGN or within a starburst region, the particle can undergo pion-producing interactions during acceleration that drain its energy faster than the acceleration can replenish it. The optical depth for pion production within the source depends on the photon density, the particle's energy, and the size of the source region. For the most luminous AGN, the central region near the black hole can be so photon-rich that it is effectively opaque to the highest energy protons, limiting the energy that can escape to values below what the Hillas criterion alone would allow. This is why heavy nuclei are considered attractive from the source escape perspective. Below the energies where photodisintegration becomes important, heavy nuclei do not produce pions in photon fields because the relevant threshold is higher than for protons. A heavy nucleus can, in principle, escape a photon-rich environment at energies where a proton of the same total energy would be stopped by pion production losses. But once outside the source and propagating through intergalactic space, the heavy nucleus faces photodisintegration on the cosmic infrared and microwave backgrounds, which can fragment it into lighter components and change both its energy and its charge. The tension between escaping the source environment and surviving propagation defines the operating range for each type of particle from each type of source. A proton from a photon-rich AGN might not escape at ZeV energies, but could escape at tens of electron volts. An iron nucleus from the same environment might escape at ZeV energies, but could be disintegrated to lighter elements during propagation, arriving at Earth as an intermediate mass nucleus or even as individual nucleons. The observed composition at Earth, therefore, reflects not just what sources accelerate, but what survives the combined gauntlet of escape from the source and propagation through intergalactic space. Centaurus A, as the closest known powerful radio galaxy, has been analyzed in detail as a potential ZeV accelerator. The radio lobes of Centaurus A extend roughly 60 kiloparsecs from the central galaxy and contain magnetic fields estimated at several microgauss. The product of field and size gives a Hillas criterion satisfied for proton energies up to roughly 10 electron volts, below the ZeV range, but already at the highest energies where Auger has claimed a correlation. The inner jets and the hotspots where the jet terminates against the intergalactic medium have much stronger local fields and could in principle reach higher energies, though detailed models are needed to assess the acceleration efficiency and escape conditions in those specific regions. The giant lobes of Centaurus A also act as reservoirs that confine cosmic rays for extended periods, allowing gradual escape and potentially contributing to the cosmic ray flux at intermediate energies over timescales of billions of years. If Centaurus A has been active for a sufficiently long time, and if cosmic rays can be stored in the lobes before eventually diffusing out, the total energy injected could be substantial. The contribution to the observed flux at Earth depends on the injection spectrum, the confinement time, and the distance, all of which have significant uncertainties. Virgo A, also known as M87, is another nearby powerful radio galaxy at a distance of about 16 megaparsecs. It hosts one of the most massive known supermassive black holes, with a mass of roughly 6.5 billion solar masses, and its jet has been resolved at radio and optical wavelengths down to scales of a fraction of a parsec from the central engine. The jet of M87 was associated with a high-energy neutrino detection candidate in the IceCube data, though the association was not statistically definitive. M87 is within the GZK horizon for intermediate and heavy nuclei, and its jet power and magnetic field structure make it a plausible ZV accelerator. The difficulty with M87 as a source for the oh my god particle, or the Amaterasu particle specifically, is directional. M87 sits in the Virgo cluster region of the sky, which is not aligned with the arrival directions of those specific events within the uncertainty estimates. However, magnetic deflection could shift the apparent arrival direction substantially, particularly for heavy primaries, and a significant contribution from M87 to the overall ultra-high-energy cosmic ray flux is not ruled out by the directional observations. The Fornax cluster, another nearby concentration of galaxies containing the radio galaxy Centaurus B and other active systems, has been proposed as a source region contributing to the Auger excess in the southern sky. The Centaurus region of the sky, which contains Centaurus A and also the Centaurus cluster at a distance of roughly 40 megaparsecs, shows some excess in the Auger dataset at the highest energies. Whether this excess is dominated by the nearby Centaurus A specifically, or by a broader contribution from the Centaurus region, is difficult to determine given the angular resolution limitations and the number of events available. Beyond individual source identification, the large-scale anisotropy of ultra-high-energy cosmic rays, meaning the correlation between arrival directions and the distribution of matter in the local universe, provides a way to test source models statistically without identifying individual sources. If the sources trace the distribution of galaxies, or AGN, in the local universe, the cosmic ray flux should be anisotropic in proportion to the local density gradient, with a dipole pointing roughly toward the overdense region of the local large-scale structure. Both Auger and the telescope array have detected a dipole anisotropy in the arrival direction distribution of cosmic rays above about 8 exa-electron volts, at a level of about 6% amplitude, and pointing roughly toward the direction away from the galactic center and toward the overdense local large-scale structure. The amplitude and direction of the dipole are consistent with expectations for extragalactic sources that trace the matter distribution within a few hundred megaparsecs, providing evidence that the ultra-high-energy cosmic ray flux is indeed of extragalactic origin, and that the sources are distributed broadly through the local large-scale structure, rather than concentrated in a single point source. The dipole signal becomes weaker, and its direction becomes harder to determine at the highest energies, where statistics are most limited, but it is consistent with the picture of a source population that follows the matter distribution, which includes both the nearby galaxy clusters and the more extended filamentary structure of the cosmic web. This supports the interpretation that the sources are a broad class of astrophysical objects distributed through the local universe, rather than a single dominant source at a specific location. The challenge of identifying individual sources within this broad distribution is compounded by the fact that the sources may be intermittent rather than steady. An AGN that was active 1 million years ago might have produced a burst of ultra-high-energy cosmic rays that are still reaching Earth today, because the travel time from a source at tens of megaparsecs is tens of millions of years, and the magnetic deflection extends the path length further. The source might look quiet today in electromagnetic observations, while still contributing to the cosmic ray flux from its past activity. Transient sources like gamma-ray bursts are an extreme version of this intermittency, where the emission lasted seconds or minutes, but the cosmic ray signal spreads over millions of years of arrival time due to magnetic dispersion. This temporal aspect of the source problem adds a dimension that is easy to overlook, but has real consequences for source identification. When we look at the sky in electromagnetic wavelengths to find candidates corresponding to the highest energy cosmic ray arrival directions, we are seeing the sources as they are now. But the cosmic rays we are detecting may have been produced when the sources were in a different state, possibly much more active, possibly in a burst that has long since ended. The electromagnetic sky and the cosmic ray sky are temporally offset by the propagation time, which for sources at tens to hundreds of megaparsecs ranges from tens to hundreds of millions of years. This mismatch between the cosmic ray arrival time and the emission time is not a fatal obstacle, but it is a real complication. It means that transient or variable sources cannot be identified through temporal coincidence with the cosmic ray arrival, only through directional coincidence with the region where they were active at the relevant time in the past. For steady sources like continuously active AGN, the temporal offset does not matter because the source looks the same now as it did in the relevant past. But for episodically active sources, the identification requires knowing something about the history of the source's activity, which is often not well constrained by available observations. The theoretical frameworks for connecting source properties to observed cosmic ray spectra and composition have become increasingly sophisticated over the past decade, incorporating propagation through realistic magnetic field models derived from cosmological simulations of structure formation. These simulations track the evolution of the cosmic web, including the magnetic fields that are generated by dynamo processes in forming galaxies and clusters, and spread through the intergalactic medium by galactic winds and AGN outflows. The resulting field configurations are used to propagate cosmic rays from candidate sources to Earth, predicting the spectrum, composition, and arrival direction distribution that should be observed if the assumed source population is correct. The simulations show that even modest intergalactic magnetic fields along the cosmic web filaments can produce significant deflections for heavy nuclei at ZV energies, potentially explaining why the arrival direction distribution is relatively diffuse despite the GZK horizon constraint. If the sources are concentrated along filaments, and if the filaments themselves channel the cosmic ray paths by their magnetic structure, the observed distribution could reflect both the source distribution and the magnetic guidance rather than simple straight-line propagation from source to Earth. This picture of magnetic guidance along cosmic web filaments is speculative in detail but physically motivated. The filaments of the cosmic web are the densest structures in the universe after clusters and groups, and they contain both the majority of the baryonic matter outside of clusters and the strongest magnetic fields outside of clusters and galaxies. A cosmic ray propagating from a source in one filament to Earth in another filament might follow a winding path guided by the filament geometry, arriving with an apparent direction that reflects the geometry of the cosmic web rather than pointing back to the source. The observational signature of such magnetic guidance would be an anisotropy that is correlated with the large-scale structure of the cosmic web, particularly with the filamentary distribution of matter, rather than with individual point sources. The dipole observed by Auger and the telescope array is at least partially consistent with this picture, pointing roughly toward the overdense local large-scale structure. But distinguishing guidance along filaments from simple isotropic propagation with a source distribution that follows matter density requires better angular resolution and much larger statistics than current data provide. The theoretical and observational efforts described in this section represent the state of the art in understanding what produces ultra-high-energy cosmic rays and how those particles reach Earth. The picture is richer and more nuanced than the simple question of what fires the "oh my god" particle might suggest, because the answer involves a complex interplay of acceleration physics, propagation through magnetized space, interaction with the relic radiation background, and observation through an imperfect atmospheric detector with its own systematic limitations. What remains clear is that whatever the sources are, they must be among the most extreme astrophysical environments in the observable universe. The energy scale of the "oh my god" particle and its relatives is not a small extrapolation from what we understand. It is a leap into territory where our best models of acceleration and propagation are tested at their limits and sometimes appear to fail. The universe is doing something extraordinary, and the extraordinary nature of the phenomenon demands extraordinary evidence before any single explanation can be accepted. The evidence is accumulating, slowly and carefully, event by event and analysis by analysis. The next generation of instruments will bring a factor of 10 or more improvement in statistics at the highest energies, combined with better composition sensitivity and more complete sky coverage. The multi-messenger connections will deepen as neutrino and gamma-ray observatories improve their sensitivity and expand their catalogs of detected sources. The hadronic physics uncertainties will narrow as LHC measurements continue and as future high-energy colliders push the directly measured range upward. At the end of this process, which will unfold over the coming decades, we should know the answer to the source question with a confidence that current data cannot provide. We will know whether active galactic nuclei are the dominant source class, or whether starburst galaxies, magnetars, or something more exotic provides the ZV acceleration. We will know whether the composition at the highest energies is predominantly light, heavy, or mixed, and how it evolves with energy in ways that constrain both the source spectrum and the propagation. we will know whether the GZK horizon is indeed limiting the observable source region in the way the standard calculation predicts, or whether some modification of the propagation physics is needed. And possibly, if we are fortunate, or if the universe is generous enough to send us sufficiently clear signals, we will know whether the oh my god particle and the Amaterasu particle were telling us something not just about extreme astrophysics, but about the fundamental rules of physics in a regime we have never directly probed. The possibility that the rules bend at the highest energies is not mainstream physics, but it is not dismissed, and the evidence that would establish or refute it is within the reach of the observatories being built and planned today. The quiet night in the Utah desert in October 1991 opened a question that is still open more than 3 decades later. The question has grown richer and more precise with each year of effort, and the tools being brought to bear on it are more powerful than anything the fly's eye era could have imagined. But the question itself, at its heart, remains the same. What fired that particle at Earth, and what does its survival tell us about the universe we live in? The search for the sources of ultra-high-energy cosmic rays is ultimately a search for the universe's most extreme natural laboratories, places where physics operates at scales and intensities that human civilization cannot reproduce and may never be able to reproduce. But identifying the sources is only part of the story, because even if we knew exactly where every ultra-high-energy cosmic ray came from, we would still face the deeper question of how nature manages to concentrate so much energy into a single particle, and what that concentration tells us about the fundamental rules governing matter and energy at their most extreme. That deeper question connects cosmic ray physics to particle physics in ways that go beyond the hadronic interaction models discussed earlier. It connects to questions about the nature of space and time, about whether the symmetries we take for granted at accessible energies hold at energies 100 million times higher, and about whether the universe contains forms of matter or energy that we have not yet detected in any laboratory. These connections are not speculative in a loose sense. They are specific, testable predictions that arise from specific theoretical frameworks, and the data from ultra-high-energy cosmic ray experiments provide genuine constraints on them. The most conservative of these deeper questions concerns the behavior of quantum chromodynamics at extreme energies. QCD is the theory of the strong nuclear force, and it governs how quarks and gluons interact to form protons, neutrons, pions, and the other hadrons that dominate cosmic ray shower physics. At the energies relevant for ultra-high-energy cosmic ray first interactions, QCD is operating in a regime where the density of gluons in the interacting nuclei may be so high that new collective phenomena emerge. The color glass condensate is a theoretical framework describing this high-density gluon regime, and it predicts modifications to particle production that could affect shower development in ways that differ from conventional models. If the color glass condensate or similar high-density QCD effects are relevant at cosmic ray energies, they could partly explain the muon excess observed in ultra-high-energy showers. In the CGC framework, the initial state of the colliding nuclei is dominated by a dense coherent gluon field rather than the individual parton distributions assumed in conventional models. The collision of two such fields produces particles differently from individual parton-parton scatterings, with potentially different multiplicities, different particle type ratios, and different rapidity distributions. The muon content of the resulting shower could be enhanced relative to conventional predictions if the CGC collision produces more charged pions and fewer neutral pions, or if it produces them in different kinematic distributions. Testing QCD in this high-density regime is one of the goals of forward physics measurements at the LHC and at potential future higher-energy colliders. The very forward region of proton-proton and proton-nucleus collisions at the LHC, where particles carry large fractions of the beam momentum and where the parton densities are highest, is where CGC effects are expected to be most prominent. Measurements from the LHCF experiment, which detects neutral particles in the very forward region, and from the totem experiment, which measures the total proton-proton cross-section and elastic scattering, provide constraints that can be incorporated into cosmic ray shower models. The connection between forward LHC physics and cosmic ray shower modeling is a genuine and productive interface between two fields that have historically been somewhat separate. Improving this connection requires dedicated measurements in kinematic regions that were not the primary focus of the main LHC experiments and that require specialized forward detectors. The effort is worthwhile because the uncertainty in hadronic interaction models at cosmic ray energies is currently one of the dominant systematic errors in composition measurements, and reducing it would dramatically improve the interpretability of both the muon puzzle and the X-max distributions. Beyond conventional QCD, there are more exotic possibilities for new physics that could manifest in cosmic ray observations. Supersymmetry, which postulates a symmetry between fermions and bosons that would double the particle content of the standard model, predicts the existence of new particles that could be produced in ultra-high-energy cosmic ray interactions if their masses are in the appropriate range. The lightest supersymmetric particle, if it is stable and weakly interacting, would escape the shower and carry away energy invisible to the detector, effectively increasing the invisible energy fraction and modifying the apparent shower development. Microscopic black holes are predicted by theories with extra dimensions to be produced in particle collisions at energies above the fundamental Planck scale of the higher dimensional theory. If extra dimensions lower the fundamental Planck scale from its four-dimensional value of 10 to the 19th GeV to something in the range of a few TeV, then microscopic black holes could be produced at LHC energies and certainly at cosmic ray energies. A microscopic black hole produced in the first interaction of a cosmic ray with an atmospheric nucleus would decay via Hawking radiation into a democratic distribution of all particle types, producing a shower with very different characteristics from a conventional hadronic shower. The signature would be a large multiplicity of secondaries with roughly equal energy sharing among all particle species. These exotic scenarios can in principle be tested by looking for anomalous shower development patterns that differ systematically from both the proton and iron expectations of conventional models. A microscopic black hole shower would be distinguishable by its much higher multiplicity per unit energy and by the isotropic decay products in the black hole's rest frame. No such anomalies have been clearly observed, which places constraints on the cross-sections for exotic processes at cosmic ray energies, though the statistics are limited and the constraints are not always stronger than those from accelerator experiments. The question of Lorentz invariance at extreme energies has been discussed already in the context of the GZK threshold, but it deserves more careful treatment because the implications are profound and the observational tests are genuinely constraining in ways that complement laboratory tests. Lorentz invariance is the symmetry underlying special relativity, the principle that the laws of physics take the same form in all inertial reference frames and that there is no preferred rest frame in the universe. It has been tested with extraordinary precision at low energies and at LHC energies, and it has always held to better than the experimental sensitivity. At the Planck scale, many theories of quantum gravity predict that Lorentz invariance might be violated because the discrete structure of spacetime at the Planck length would provide a preferred rest frame for propagating waves. The violations are expected to be suppressed by powers of the particle's energy divided by the Planck energy, which makes them undetectably small at any energy accessible to laboratory experiments. But at the energies of ultra-high-energy cosmic rays, which are a factor of 100 million above the LHC, but still 4 orders of magnitude below the Planck scale, the suppression might be small enough that cumulative effects over long propagation distances become observable. The most directly testable consequence of Lorentz invariance violation for cosmic ray physics is the modification of the GZK threshold. The threshold for pion production in proton-CMB photon interactions is set by the requirement that the center of momentum energy exceeds the pion mass. In standard relativity, this threshold is determined by the invariant mass of the initial state, which is fixed by the proton and photon 4 momenta. If Lorentz invariance is violated, the energy-momentum relation for the proton or for the photon might differ from the standard dispersion relation by a small correction term proportional to a power of the energy divided by the Planck scale. Such a modification would change the effective threshold energy for pion production. Depending on the sign of the Lorentz invariance violation parameter, the threshold could be raised or lowered. If the threshold is raised, cosmic rays that would normally produce pions can propagate without energy loss up to higher energies, and the GZK horizon extends to larger distances. This would make it easier to explain the existence of extreme events like the oh my god particle without requiring sources within a tight GZK volume. The constraints on Lorentz invariance violation from cosmic ray physics come primarily from the observed spectrum and from the GZK suppression. If the threshold is shifted far enough upward that the suppression disappears, the spectrum should not show a cutoff at the expected energy. The observation of a spectrum suppression, consistent with standard GZK expectations by Auger and the telescope array therefore places limits on how much the threshold can be shifted, which translates into limits on the Lorentz invariance violation parameters. These limits are competitive with some laboratory tests and probe the Planck-suppressed regime in a way that no other current measurement can. The constraints become even tighter when combined with gamma-ray observations. A different set of reactions, specifically the threshold for very high-energy photons to pair produce on lower-energy background photons, is also sensitive to Lorentz invariance violation. The TV photons detected from blazars by imaging atmospheric Cherenkov telescopes must traverse extragalactic distances without being absorbed by pair production on the extragalactic background light. The fact that these photons are detected constrains the pair production threshold, which in turn constrains Lorentz invariance violation parameters from the photon sector. Combining cosmic ray and gamma ray constraints tests different combinations of the Lorentz invariance violation parameters and provides a more complete picture of the allowed deviation from standard relativity. A conceptually different class of new physics scenarios involves the possibility that ultra-high-energy cosmic rays are not conventional particles accelerated from rest to extreme energies, but are instead decay products of massive relic particles from the early universe. In this picture, often called top-down models, as opposed to the bottom-up acceleration models discussed so far, the energy does not need to be acquired through acceleration in an astrophysical environment. Instead, it was stored from the beginning in the rest mass of a super-heavy particle that was produced in the very early universe and has survived to the present day. The appeal of top-down models is that they bypass the acceleration problem entirely. If there exist particles with masses in the range of 10 to the 22nd to 10 to the 24th electron volts, comparable to or exceeding the energies of the most extreme cosmic rays, then the decay of such particles would naturally produce secondary particles at those energies. The secondaries would include quarks and gluons that fragment into pions and other hadrons, which then decay into protons, neutrons, neutrinos, and photons. The spectrum of the decay products would be determined by the fragmentation physics and the particle's mass, not by an acceleration mechanism. Superheavy relic particles of this kind arise naturally in certain theoretical frameworks. Grand unified theories predict the existence of topological defects such as cosmic strings and magnetic monopoles that could have been produced in phase transitions in the very early universe when the gut symmetry was broken. These defects store enormous amounts of energy in their mass and in the topological structure that maintains them, and they can release that energy through various processes including annihilation, collapse, and radiation. The resulting particle injection spectrum can in principle reach the ZV range if the defect mass or tension is sufficiently large. Cosmic strings are one-dimensional topological defects, lines of trapped false vacuum energy that would have formed at gut-scale phase transitions if such transitions occurred with the right topology. They carry enormous linear energy density, proportional to the square of the gut symmetry breaking scale, and they can radiate energy by oscillating, colliding, and forming loops that eventually shrink and release their energy in particles and gravitational waves. A network of cosmic strings threading the universe would continuously produce particle emission at the highest energies, with a spectrum and flux determined by the string tension and the evolution of the string network. Magnetic monopoles are point-like topological defects that carry magnetic charge, predicted by gut symmetry, breaking in essentially the same theoretical context as cosmic strings. A monopole-antimonopole pair can annihilate and release their combined rest mass as secondary particles. If the monopole mass is in the ZV range, the annihilation would produce secondaries at those energies. The problem with monopoles as a dominant source of ultra-high-energy cosmic rays is the monopole number density, which must be large enough to produce the observed flux without contradicting the Parker bound from galactic magnetic field stability and other astrophysical constraints. Superheavy dark matter particles represent another top-down candidate that is perhaps more theoretically motivated in the modern context. If dark matter consists partly or entirely of particles with masses in the range of 10 to the 22nd to 10 to the 24th electron volts, their annihilation or decay could produce ultra-high-energy cosmic rays. Unlike conventional WIMP dark matter, which has been the dominant paradigm for decades, and which predicts dark matter masses in the GV to TV range, superheavy dark matter would be produced by gravitational mechanisms in the early universe and would not require the typical weak interaction annihilation cross-section. The production of superheavy dark matter through gravitational particle production, which occurs when the expansion rate of the universe changes rapidly as it transitions from inflation to radiation domination, is a well-studied mechanism that naturally produces particles with masses up to the inflaton mass scale. If this mechanism is responsible for some component of the dark matter, the superheavy particles would be clustered in the dark matter halos of galaxies and clusters, and their annihilation or decay would produce ultra-high-energy cosmic rays concentrated toward the directions of nearby dark matter overdensities. The observational signature of superheavy dark matter decay would differ from bottom-up acceleration models in several important ways. The spectrum of secondaries from the decay would be harder than the GZK-modified spectrum from distant sources, because the decay products are produced locally with no propagation losses. The arrival direction distribution would correlate with the dark matter distribution rather than with the galaxy or AGN distribution, pointing toward the galactic center, the galactic halo, and nearby clusters where dark matter is concentrated. The composition of the arriving particles would reflect the fragmentation spectrum of the superheavy particles' decay rather than the acceleration environment, and it would include a larger fraction of photons and neutrinos relative to hadrons than conventional sources. The large photon fraction is particularly diagnostic because photons at extreme energies interact with background radiation fields and cascade electromagnetically, producing a shower signature that is distinct from hadronic showers. A primary photon at ZV energies would produce electromagnetic pair conversion and bremsstrahlung, much like the electromagnetic component of a hadronic shower, but without the muonic component from hadronic interactions. The depth of shower maximum for a photon primary would be greater than for a proton primary at the same energy, and the muon content would be dramatically suppressed. Searches for photon primaries in the Auger and telescope array datasets have set upper limits on the photon fraction at high energies, and these limits constrain the contribution from super-heavy dark matter scenarios and other top-down models. Current upper limits on the photon fraction at energies above a few electron volts are at the level of a few percent, meaning that photons can comprise at most a few percent of the total flux at those energies. This strongly disfavors simple top-down models that predict a large photon fraction, and it pushes the superheavy dark matter and topological defect scenarios into regions of parameter space where the photon fraction is suppressed by propagation effects or by the decay physics. The constraints will tighten further as Auger and the telescope array accumulate more statistics and as improved shower analysis methods are applied to the existing datasets. Neutrino primaries represent another exotic possibility that is constrained by shower profile measurements. A neutrino interacting in the atmosphere would produce a shower starting much deeper than a hadronic primary because neutrinos interact only weakly. The shower would be nearly horizontal or at a large zenith angle because the large slant depth of atmosphere available at large zenith angles provides enough material for the neutrino to interact. The shower would also be very young at the ground, with a large electromagnetic component and few muons because there has been less time for the hadronic component to develop. Auger and the telescope array search for deeply starting showers at large zenith angles as a signature of neutrino interactions. The non-detection of such events at the expected rate for standard model neutrino interactions at ZV energies places constraints on the flux of ultra-high-energy neutrinos, as discussed earlier. It also constrains scenarios where the oh my god particle was a neutrino rather than a hadronic primary, because the shower profile of the detected event was consistent with a hadronic shower developing at a typical depth, not with a deeply starting neutrino interaction. The interplay between exotic physics scenarios and conventional astrophysical sources makes the interpretation of ultra-high-energy cosmic ray data a delicate exercise in hypothesis testing. The data must be consistent with any proposed model, and the model must make specific predictions that can be tested against the data. Simply invoking an exotic process to explain an anomalous event is not sufficient. The exotic process must predict the right energy spectrum, the right arrival direction distribution, the right composition, and the right associated fluxes of neutrinos and photons, all simultaneously and consistently. This requirement for simultaneous consistency across multiple observables is powerful precisely because it is hard to satisfy. Most exotic models predict specific combinations of observables that differ from conventional astrophysical models in ways that can be tested as statistics improve. The photon fraction limit is one of the most constraining tests, and it has already eliminated some of the simplest exotic scenarios. The neutrino flux limits provide complementary constraints. The arrival direction distribution and its evolution with energy test whether the sources follow the matter distribution as expected for conventional extragalactic sources. The composition evolution with energy tests whether the source spectrum and propagation models are self-consistent. Building a complete and consistent picture requires all of these tests to be applied together, and it requires the uncertainties in each test to be understood and quantified carefully. This is why the field emphasizes cross-calibration between experiments, systematic uncertainty estimation, and the development of analysis frameworks that can incorporate all available observables into a unified inference. The goal is not to find the single observation that settles the question, but to accumulate enough independent constraints that only one family of models remains consistent. The exotic physics scenarios, while constrained, are not yet eliminated, and they motivate searches for specific signatures that would conclusively establish or rule them out. The most decisive test for super-heavy dark matter would be the detection of an anisotropy correlated specifically with the dark matter distribution rather than the baryonic matter distribution. Since dark matter is not perfectly traced by visible matter, there are regions where the dark matter density is high but the visible galaxy density is low, and vice versa. If ultra-high-energy cosmic rays come from dark matter decay, the anisotropy would point preferentially toward dark matter concentrations, even when those concentrations do not correspond to luminous galaxies. The galactic center region is the strongest dark matter overdensity accessible to Earth-based observations, and it is also the brightest gamma-ray and neutrino source in the sky, partly from conventional astrophysical processes and partly potentially from dark matter annihilation. The Pierre Auger Observatory, located in the southern hemisphere, has good coverage of the galactic center region, and searches for an excess of ultra-high-energy cosmic rays from that direction provide a test of the galactic dark matter decay hypothesis. The current data show no statistically significant excess from the galactic center that would indicate dark matter decay, but the statistics are limited and the constraints are not yet definitive. The Milky Way halo is another dark matter concentration that should produce an anisotropy correlated with its distribution if dark matter decay is contributing significantly. The halo signal would manifest as a large-scale anisotropy proportional to the dark matter density profile, integrated along each line of sight, with higher flux from directions through the center of the halo and lower flux from directions toward the outer halo or through voids in the halo structure. The expected amplitude of this signal depends on the dark matter mass and lifetime, and current upper limits on the galactic halo contribution from ultra-high-energy cosmic ray data place some constraints on super-heavy dark matter models. Combining cosmic ray anisotropy measurements with direct dark matter detection experiments and with collider searches for new physics provides the most complete constraints on exotic scenarios. Direct detection experiments searching for WIMP dark matter are sensitive to masses in the GV to TeV range, far below the super-heavy regime, but future experiments sensitive to higher masses through different detection strategies, combined with cosmic ray constraints from Auger and the telescope array, can bracket a much wider range of dark matter parameter space. The possibility that ultra-high-energy cosmic rays are connected to some aspect of quantum gravity, whether through Lorentz invariance violation, microscopic black holes, or some other Planck-scale physics, motivates a research program that extends well beyond cosmic ray physics itself. Quantum gravity is the outstanding unsolved problem in theoretical physics, and it is expected to modify the laws of physics at the Planck scale in ways that are not yet understood. The cosmic ray observations provide a window into physics at energies that are many orders of magnitude above any laboratory measurement, and while they are still far from the Planck scale, they provide the best available test of some quantum gravity predictions. String theory, loop quantum gravity, and various other approaches to quantum gravity make different predictions about how Lorentz invariance might be modified and at what energy scale. The predictions are not always specific enough to be directly tested, because the theoretical frameworks allow a wide range of parameters that must be fixed by additional input. But some predictions are specific enough to be constrained by cosmic ray data, and those constraints contribute to the broader program of testing quantum gravity proposals with every available observational tool. The search for exotic physics in cosmic ray data is not a fringe activity driven by desperation to explain anomalous events. It is a legitimate and well-motivated scientific program that uses the highest available energy observations to test fundamental physics in regimes that laboratory experiments cannot reach. The oh my god particle and its relatives are genuinely extreme in the literal sense, and extreme observations deserve to be interpreted with an open mind that includes both conventional explanations and well-motivated alternatives. At the same time, the preference for conventional explanations is not merely cultural conservatism. It reflects the successful track record of known physics in explaining a vast range of observations and the principle that extraordinary claims require extraordinary evidence. The evidence for exotic physics from cosmic ray observations has not yet reached the level of extraordinary. The muon excess is suggestive, but could be explained by improved hadronic physics models. The GZK suppression is consistent with standard propagation physics. The arrival direction distribution shows hints of anisotropy consistent with conventional extragalactic sources. None of these observations compels an exotic interpretation, though they do not exclude it. The resolution of the source question may ultimately be less dramatic than either the most optimistic or the most alarming scenarios suggest. The sources might turn out to be radio-loud AGN with relativistic jets, doing exactly what AGN jets are expected to do, but in realizations more extreme than the examples we have studied closely. The composition might turn out to be a well-understood mixture of light and heavy nuclei that reflects the source environments in a way consistent with known nuclear astrophysics. The propagation might turn out to follow standard GZK physics with field models that are refined but not revolutionized by new measurements. In that case, the story of ultra-high-energy cosmic rays would be a triumph of conventional physics pushed to its limits, revealing the most extreme astrophysical processes in nature, but not requiring new fundamental laws. The lesson would be about what is possible within the known framework when that framework is exercised at its maximum extent. That would still be a profound lesson about how the universe manages energy at scales we cannot reproduce, and it would have practical implications for understanding the energy budget of the most powerful structures in the cosmos. But the alternative, that something genuinely new is revealed at the highest energies, cannot be excluded and should not be dismissed. The history of physics is full of cases where pushing observations to more extreme conditions revealed genuinely new phenomena that could not have been predicted from lower energy observations alone. Quantum mechanics was revealed by pushing atomic spectroscopy to greater precision and by studying radiation in extreme conditions like the photoelectric effect. Relativity was revealed by pushing electromagnetic theory and mechanics to their logical conclusions. The strong nuclear force was revealed by pushing particle physics to higher energies and discovering phenomena that electromagnetism and gravity could not explain. The energy scale of ultra-high-energy cosmic rays is genuinely beyond any previous observational reach, and there is no guarantee that the physics at those energies follows smoothly from what we know at lower energies. The muon puzzle could be the first hint of something genuinely new. The apparent tension between the GZK horizon and the arrival directions of some extreme events could reflect something unexpected about propagation. The void origin of the Amaterasu particle could be telling us about a source class or a magnetic field structure that we have not yet properly accounted for. The honest answer is that we do not yet know which of these possibilities is correct, and we will not know until the next generation of experiments provides the statistics and the resolution needed to distinguish between them. The "oh my God" particle initiated a question. The answer is still being assembled, piece by piece, from the sparse and precious events that the universe occasionally delivers to our detectors in the Utah desert and on the Argentinian pampas and in the Japanese countryside. The story of ultra-high-energy cosmic rays is not only a story about particles and sources and propagation. It is also a story about how science works at the extreme edge of the observable, where the data are sparse, the systematics are large, and the temptation to overinterpret is matched by the temptation to dismiss. Both temptations must be resisted simultaneously, and resisting them requires a specific kind of intellectual discipline that the field has had to develop over decades of working with events that can be counted on fingers. The discipline begins with honest accounting of uncertainties. Every measurement in cosmic ray physics carries systematic errors that are as important as the statistical errors, and often larger. The energy scale uncertainty, the atmospheric correction uncertainty, the hadronic model uncertainty, the composition interpretation uncertainty, and the magnetic field model uncertainty all contribute to the final uncertainty on any derived quantity. A measurement that ignores or underestimates these systematics will report a misleadingly small error and will draw conclusions that the data cannot actually support. The fly's eye measurement of the "oh my God" particle energy at 320 exaelectron volts with an uncertainty of 90 exaelectron volts is a good example of honest uncertainty accounting. The 90 exaelectron volt uncertainty is large, nearly 30%, but it reflects the genuine limitations of the measurement given the available atmospheric monitoring, the monocular geometry, and the calibration uncertainties of the instrument at the time. A measurement that reported a much smaller uncertainty would have been reporting false precision, and the subsequent analysis of the event's implications would have been systematically wrong. The temptation to report smaller uncertainties is real because smaller uncertainties make results look more impressive and make papers easier to publish. The field has generally resisted this temptation through a combination of community norms about systematic error estimation, cross-comparison between independent experiments that reveals inconsistencies when uncertainties are underestimated, and the experience of watching apparently precise results evaporate when more careful analysis was applied. The AGASA flux excess above the GZK threshold is a cautionary tale in this regard. Results that appeared robust when first announced became less significant when the energy scale was revisited, and the systematic uncertainties were more carefully estimated. The discipline also requires careful statistical analysis that does not exploit the freedom to define search parameters after looking at the data. The correlation between Auger events and AGN positions that was initially reported at high significance weakened as more data were collected, partly because the initial correlation may have been an artifact of the freedom to optimize the correlation parameters on the initial dataset, and then report the result as if those parameters had been chosen independently. Modern analyses attempt to avoid this by pre-registering analysis choices, by separating datasets into training and testing samples, and by applying statistical penalties for multiple testing. The development of rigorous statistical methods for cosmic ray astronomy has been one of the less celebrated but genuinely important contributions of the field to astrophysics more broadly. Working with small numbers of extreme events has forced the development of techniques for upper limit setting, confidence region construction, and hypothesis testing in the low statistics regime where Gaussian approximations fail. These methods are now applied in related fields including neutrino astronomy and gravitational wave astronomy, where similar challenges of rare events and large backgrounds arise. The collaborative structure of modern cosmic ray physics also reflects lessons learned from the difficulties of working with small statistics and large systematics. The Auger collaboration includes more than 500 researchers from dozens of countries, and the telescope array involves comparable international participation. This scale is not primarily about funding or prestige, but about the practical necessity of having enough human expertise to develop and apply the methods needed to extract reliable physics from the data. Any single researcher or small group could make mistakes in systematic error estimation or statistical analysis that would go unchallenged. A large collaboration provides the diversity of perspectives and the internal scrutiny needed to catch and correct such mistakes before they become published claims. The collaboration model does create its own challenges, particularly around the timely sharing of data and the freedom of individual researchers to pursue unconventional analyses. Large collaborations tend to move slowly toward consensus, and the process of reaching consensus can sometimes delay publication of interesting results or suppress minority viewpoints that challenge the mainstream interpretation. The field is aware of this tension and tries to balance it by encouraging internal working groups to pursue different analysis approaches and by providing forums for dissenting interpretations to be heard alongside the official collaboration results. The relationship between the Auger and telescope array collaborations has been an interesting case study in how separate experiments with overlapping scientific goals can interact constructively rather than competitively. The two experiments observe different hemispheres and use partially different techniques, which means their systematic errors are different and their scientific results are complementary rather than directly competitive. Joint working groups have been established to compare energy scales, coordinate analysis methods, and jointly interpret results that span both hemispheres. This cooperation is not obligatory, but has been widely recognized as essential for making progress on questions that require full-sky coverage. The differences in results between the two experiments, particularly on composition, have been a source of productive tension that has driven both collaborations to examine their systematic errors more carefully and to develop better understood analysis methods. When two experiments analyzing the same physical phenomenon reach different conclusions, the difference is scientifically valuable precisely because it forces both to identify the sources of the discrepancy. In several cases, the investigation of discrepancies has led to improvements in atmospheric correction methods, shower reconstruction algorithms, and hadronic model application procedures that benefited both experiments. The planning for the next generation of instruments takes place in this context of hard-won methodological lessons and careful collaboration. The Auger Prime upgrade and the T-Ax4 expansion are not simply bigger versions of existing instruments. They incorporate specific design choices aimed at addressing the identified limitations of the current experiments. The addition of scintillators alongside water Cherenkov detectors at Auger directly addresses the muon content measurement limitation. The expansion of the telescope array surface array addresses the statistics limitation in the Northern Hemisphere hotspot region. The radio antenna deployments at both sites address the duty cycle limitation for composition measurements. The science case for these upgrades rests on specific physics questions that current instruments cannot answer with sufficient precision. Can the composition at the highest energies be determined well enough to use rigidity as a guide to source direction backtracking? Is the northern sky hot spot a genuine source concentration or a statistical fluctuation? Is the arrival direction distribution of the highest energy events consistent with known large-scale structure in the local universe, or does it require sources in the voids? Does the muon excess persist with better controlled systematic errors, and if so, what does it imply for hadronic physics? These questions are precise enough to guide instrument design and analysis planning, which is a sign of scientific maturity. The field has moved from the phase of discovery, where the existence of extremely high-energy cosmic rays was established and their basic properties were characterized, into the phase of precision measurement, where the details of the spectrum, composition, and anisotropy are being determined with enough accuracy to test specific models. The precision phase is harder in some ways than the discovery phase because it requires managing systematic errors that did not matter when the questions were cruder. The next phase beyond precision measurement might be called the explanation phase, where the converging constraints from spectrum, composition, anisotropy, neutrino flux, gamma-ray associations, and magnetic field models finally narrow the remaining possibilities to a single consistent picture. That phase is not guaranteed to arrive on any particular timetable, because it depends not only on building better instruments, but on theoretical developments that connect the observations to specific physical processes in specific types of sources. The theoretical work needed to enable the explanation phase is ongoing across multiple fronts. Numerical simulations of large-scale structure formation increasingly include magnetic field evolution, allowing more realistic modeling of the intergalactic field that deflects cosmic ray paths. The Eagle, Illustris TNG, and other cosmological hydrodynamics simulations produce predictions for the magnetic field in different environments of the cosmic web that can be compared to observational constraints from Faraday rotation surveys. The most sophisticated current simulations can produce magnetic field configurations detailed enough to be used directly as inputs for cosmic ray propagation calculations, enabling predictions of the expected arrival direction distribution for different source scenarios. On the acceleration side, particle and cell simulations of relativistic shocks and magnetic reconnection layers have advanced enormously over the past decade as computational resources have grown. These simulations follow the trajectories of individual particles in self-consistent electromagnetic fields, without the approximations needed for analytic treatments of acceleration physics. The results reveal that particle acceleration in relativistic shocks and reconnection can be much more efficient than earlier estimates suggested, and they show that the maximum energy achieved can approach the Hillas criterion limit in the most favorable configurations. Scaling the simulation results to astrophysical source sizes remains a challenge, but the qualitative picture of efficient particle acceleration in relativistic environments is well supported. Multi-wavelength observations of potential source environments continue to reveal the detailed physics of the most powerful astrophysical accelerators in ways that constrain both the field structure and the particle injection spectra. The Event Horizon Telescope, which resolved the black hole shadow of M87 and the Milky Way's central black hole Sagittarius A star, provides unprecedented detail about the immediate vicinity of supermassive black holes where jets are launched. The magnetic field structure in the jet launching region, which determines the initial conditions for jet acceleration and particle injection, can be inferred from the polarization structure observed by the Event Horizon Telescope and its successor instruments. VLBI observations of AGN jets at high radio frequencies reveal the fine structure of jet knots, standing shocks, and helical magnetic fields that are the likely sites of particle acceleration within the jets. These observations, combined with multi-wavelength spectral modeling, allow estimation of the local field strength, particle density and maximum particle energy at specific locations within the jets. The results can then be compared to the requirements from cosmic ray physics to assess whether specific jets are plausible sources of ZV cosmic rays or only of lower energy particles. The X-ray and gamma-ray observations of nearby radio galaxies and blazars by Chandra, XMM Newton, Fermi, and the ground-based Cherenkov telescope arrays provide complementary information about the radiating particle populations and the field conditions inferred from the synchrotron and inverse Compton spectra. In some cases, the combination of radio, optical, X-ray, and gamma-ray data overconstrains the source models sufficiently that the field strength and maximum particle energy can be determined with reasonable confidence. These cases provide the most direct tests of whether specific sources satisfy the requirements for ZV cosmic ray production. The multi-messenger era has added an entirely new dimension to this investigation by providing neutrino and gravitational wave observations that complement the electromagnetic picture. The association of high-energy neutrinos detected by IceCube with specific astrophysical sources, even at the level of hints and correlations rather than definitive identifications, reveals the hadronic activity in those sources. A source that produces neutrinos must have accelerated protons or heavier nuclei to sufficiently high energies to produce pions through photon or matter interactions, and the neutrino spectrum encodes information about the target density and the proton spectrum. The gravitational wave detections by LIGO and Virgo of binary neutron star mergers and binary black hole mergers have opened a new observational window that is potentially relevant to cosmic ray physics through the formation of millisecond pulsars and magnetars in neutron star mergers and through the environments created by the merger aftermath. The kilonova associated with the binary neutron star merger GW170817 showed that neutron star mergers create environments rich in heavy R-process elements, the same elements that heavy cosmic ray nuclei are composed of. If mergers accelerate cosmic rays in the immediate aftermath of the collision, the heavy nuclear composition of the environment would naturally produce a heavy cosmic ray spectrum. The connection between neutron star mergers and ultra-high-energy cosmic rays is speculative but physically motivated, and it adds another candidate to the already rich list of possible source classes. The rate of neutron star mergers in the local universe is now constrained by gravitational wave observations to a level that allows comparison with the required cosmic ray injection rate. If mergers contribute significantly to the ultra-high-energy cosmic ray flux, the merger rate combined with the typical energy injection per merger must match the observed flux, providing a quantitative test of the hypothesis. The coming years will see an increasingly dense web of multi-messenger observations connecting different aspects of the extreme universe. As gravitational wave detector sensitivity improves with the Einstein telescope and cosmic explorer, the detection rate of compact object mergers will grow from the current handful per year to potentially hundreds or thousands. As neutrino telescope volume grows with IceCube Gen 2 and new radio neutrino detectors, the sensitivity to astrophysical sources will improve dramatically. As gamma-ray observatories extend their reach to higher energies with the Cherenkov telescope array, the connection between gamma-ray sources and cosmic ray accelerators will become clearer. All of these developments will converge on the central question that the Oh My God particle asked in 1991. What are the universe's most powerful accelerators? How do they work? And how do the particles they produce survive the journey through a universe filled with ancient light and tangled magnetic fields to arrive at Earth with energies that stretch our understanding of what is physically possible? The question is deep enough to have sustained 3 decades of intense scientific effort and broad enough to connect particle physics, astrophysics, cosmology, and fundamental physics in a web that grows richer as each thread is followed. The answer, when it comes, will not be a single result from a single experiment. It will be a convergence of many results from many experiments, guided by theoretical understanding that is itself informed by the observations at every step. The Oh My God particle was a provocation, not a solution. It provoked the construction of larger detectors, the development of new analysis methods, the refinement of theoretical models, and the creation of international collaborations dedicated to understanding the universe's most extreme phenomena. It sparked a scientific enterprise that has grown steadily in ambition and sophistication, and that is now positioned to make decisive progress on questions that were barely formulated in 1991. The desert night that produced the event is long past, but its echo persists in every data point collected by the instruments that followed, in every shower reconstructed from the pattern of detector hits on the desert floor, and in every theoretical paper that grapples with the twin problems of how nature builds ZV accelerators and how a particle can carry such energy across a hostile cosmos. The echo will persist until the answer is found, and perhaps even after, because answers in physics always reveal deeper questions beneath them. What does it mean for a particle to have traveled across the universe carrying energy equivalent to a thrown baseball, and what does the survival of that energy tell us about the nature of space between here and there? These are not only physics questions, they touch something about scale and significance that resists purely technical treatment. The particle did not care that it would be detected. It did not aim itself at the Utah desert. It arrived as the result of processes operating on scales of millions of light-years and energies of hundreds of electron volts, and it found our atmosphere by the simple arithmetic of probability extended over cosmic distances. The fact that we detected it, measured it, argued about it, and built better instruments to understand it says something about the kind of creatures we are and the kind of knowledge we seek. We are made of atoms that were forged in stellar interiors and scattered by stellar explosions, the same basic astrophysical machinery that produces lower-energy cosmic rays. In detecting the oh my god particle, we were in some sense matter examining the most extreme version of the processes that created the atoms of which we are made. The universe was briefly examining itself through our instruments. That philosophical dimension does not change the physics, but it gives the enterprise a resonance that purely technical descriptions cannot capture. The cosmic ray physicists who designed the fly's eye climbed to the desert site to maintain it through summer heat and winter cold, and stayed up through moonless nights waiting for events that might never come, were not just collecting data. They were extending the human perceptual range into a domain where our unaided senses give us nothing at all. The neutrinos pass through us constantly, the cosmic rays hit us occasionally, the magnetic fields that deflect them thread through our bodies without effect. None of these are accessible to direct experience, but instruments built from human ingenuity and material craftsmanship make them accessible to human knowledge. The fly's eye itself, with its compound design and its scanning mirror canisters staring at the desert night, has something almost biological about it, as if the physics community had built an organism adapted to see what no organism evolved to see. The subsequent instruments, Auger with its 1660 surface stations spread across the pampa like an enormous circulatory system, and the telescope array watching the Utah sky with cameras that evolved from the fly's eye's photomultiplier tubes, are increasingly sophisticated expressions of the same drive to extend perception into the extreme. The researchers who work on these instruments are a diverse group, united by a specific kind of patience. The patience to build instruments that take years to construct and years more to calibrate, knowing that the events being sought are so rare that the instrument might run for a decade before accumulating enough statistics to test a specific hypothesis. The patience to analyze data sets that are complex and ambiguous, where every conclusion is hedged by systematic uncertainties that resist clean resolution. The patience to have initial exciting results weaken as more data accumulate, and to continue working without the satisfaction of a clean answer. This patience is not passive. It is active patience, the patience of people who are continuously improving their methods, challenging their assumptions, and pushing the analysis further while maintaining the intellectual honesty to report uncertainties accurately even when accuracy is less exciting than false precision. It is the patience of scientists who understand that the universe does not owe them answers on a convenient timetable. The graduate students who join cosmic ray experiments today are committing themselves to a field where the most important results may not come until they are well into their careers, and where the path to those results will involve years of technical work on detector calibration, atmospheric monitoring, and data analysis. They do so because the questions are genuinely important and genuinely hard, and because the intellectual satisfaction of working at the absolute frontier of observational capability is real and sustaining even when individual results are ambiguous. The international character of the collaborations reflects both the practical necessity of sharing costs across multiple funding agencies and the scientific value of bringing different perspectives and expertise to bear on shared problems. Researchers from Argentina, Australia, Brazil, China, Europe, Japan, and the United States, among many other countries, contribute to the Auger and telescope array analyses. The cultural and intellectual diversity this brings is not incidental to the science. Different scientific traditions, different approaches to systematic error estimation, and different theoretical priors contribute to the robustness of the conclusions by preventing any single group's blind spots from dominating the final result. The public engagement with cosmic ray physics has grown considerably since the Oh My God particle's discovery, partly because the extreme energy of the event makes it accessible as a story even to non-specialists, and partly because the broader questions it raises about the universe's most extreme processes resonate widely. The combination of extremity, mystery, and methodological sophistication that characterizes the field is compelling in the same way that black hole physics and gravitational wave astronomy are compelling. It involves the universe doing something extraordinary, studied by humans using ingenious methods, without yet having a complete explanation. The name Oh My God particle captures something important about the human response to scientific extremity that more formal terminology cannot. It is a moment of genuine surprise, the kind of surprise that physicists are trained to suspect and required to investigate, but that nonetheless arrives with emotional force when the analysis is complete and the number is real. The emotional response is not a failure of scientific objectivity. It is evidence that the scientific enterprise, at its best, is connected to the full range of human experience, including wonder and astonishment, and the feeling that the universe is stranger and more extreme than our default expectations allow. Those who detected the event, analyzed it, and eventually published the result were not performing a routine measurement and filing a routine report. They were encountering something that challenged their professional understanding and required months of careful work to verify. The uncertainty and the careful scrutiny are as important to the story as the final result because they represent the process by which human knowledge actually advances, not by pronouncing discoveries, but by subjecting apparent discoveries to sustained critical examination until the alternatives are sufficiently narrowed. The Oh My God particle survived that examination, not as an error or an artifact, but as a genuine measurement of a genuine phenomenon that remains incompletely explained more than 3 decades later. Its survival as a scientific object, as a data point that continues to constrain theories and motivate instruments, is itself a kind of tribute to the combination of engineering skill and scientific discipline that the Fly's Eye team brought to its construction and operation. The Amaterasu particle, detected 3 decades later by instruments far more sophisticated than the Fly's Eye, encountering a field far more theoretically developed than the one that greeted the Oh My God particle, still does not have a clean explanation. Its direction points toward a void, its energy challenges simple propagation models, and its composition is uncertain in ways that matter enormously for interpretation. It would be premature to call this a failure of the field. It is more accurate to call it evidence that the problem is genuinely hard and that the universe is not revealing its most extreme secrets easily. The difficulty is appropriate to the extremity. The universe's most powerful accelerators, whatever they turn out to be, are doing something that took billions of years of cosmic evolution to develop, and that requires conditions of field strength, size, and particle density that are not easily replicated elsewhere. Understanding them requires integrating knowledge from particle physics, astrophysics, cosmology, and in principle fundamental physics in a combination that no single discipline has traditionally attempted. The answer, when it comes, will have contributions from all of these, and it will advance all of them. The instruments being built now, the upgrades to Auger and the telescope array, the new neutrino detectors and gamma ray observatories, the gravitational wave network expanding its sensitivity, are the next installment in a project that began when Victor Hess climbed into his balloon in 1912 and found that the sky was raining charged particles. Each generation of instruments has revealed something that the previous generation could not see, and each revelation has deepened the questions rather than simply answering them. That deepening is the mark of a genuine scientific frontier. The questions being asked today are sharper and more specific than the questions asked in 1991, which were sharper than the questions asked when the Oh My God particle was first processed by the Fly's Eye electronics. The sharpening continues, driven by better data and better theory, and it will continue as long as the universe keeps sending its extreme messengers, and as long as humans keep building the instruments needed to receive them. The quiet night in the Utah desert in October 1991 has been followed by thousands of other nights at detectors around the world, each contributing its share of events to the dataset that will eventually explain what happened on that first night. The explanation is still being assembled. The universe is still sending its messengers. And the instruments are still listening, patient and precise and aimed at the sky, waiting for the next event that will either confirm what we think we know or overturn it in a way that no one has anticipated. That is how science works at the extreme edge, not with sudden revelation but with accumulation, not with certainty but with narrowing uncertainty. not with final answers, but with questions that become progressively sharper as the evidence grows. The "Oh my God" particle asked a question that the universe has been refusing to answer directly for more than 30 years. The refusal is not silence. It is data arriving event by event, shower by shower, composition measurement by composition measurement, building toward an answer that the next generation of physicists will be positioned to find. The story is not finished. It will not be finished for years or decades, but it is being written, carefully and collaboratively and honestly, by researchers who understand that the universe's most extreme phenomena deserve the most rigorous and patient investigation that human science can provide. That investigation is ongoing, and its outcome matters, not just for particle astrophysics, but for our understanding of what the universe is capable of, and what kind of knowledge we can ultimately extract from the sparse and precious messages it sends us across billions of years of space and time. The universe has a budget, and it keeps its accounts with a precision that no human institution has ever matched. Energy is conserved in every interaction, momentum is conserved in every collision, and the symmetries that enforce these conservation laws hold with a fidelity that has been tested in every experiment ever conducted across every energy scale accessible to human instruments. The "Oh my God" particle did not violate these accounts. It honored them completely, arriving with its energy intact and depositing every joule of it into the atmosphere in a cascade that obeyed every known law of physics from the first collision to the last muon, reaching the desert floor. What it challenged was not the rules, but the range of what the rules allow, and the range turned out to be wider than our expectations had prepared us for. Understanding that range requires thinking carefully about what the conservation laws actually permit when they are applied without the implicit limits that everyday experience builds into our intuitions. We are accustomed to thinking about energy in terms of what we can build, what we can measure in a laboratory, what a star produces over its lifetime. These are the scales that formed our intuitions about what is possible, but the laws of physics do not know about these scales. They apply equally at the energy of a thrown baseball and at the energy of the "Oh my God" particle, which are the same number in different packages. The laws do not forbid the packaging, they only require that the accounts balance. So the real question, the one that sits behind all the technical detail of shower reconstruction and propagation physics and hadronic interaction models, is this: given that the laws permit such extreme packaging, what in the universe actually does the packaging? What takes the energy available in an astrophysical environment and concentrates it into a single subatomic particle with the efficiency required to produce what we observe? The answer to this question is the answer to the mystery of ultra-high-energy cosmic rays, and finding it requires understanding not just what objects exist in the nearby universe, but what processes within those objects can accomplish the concentration. The concentration problem has a specific mathematical character that is worth spelling out because it clarifies why ordinary processes fail and why extraordinary ones are needed. In thermal equilibrium, energy is distributed among many degrees of freedom according to the Boltzmann distribution, with exponentially fewer particles carrying exponentially more energy. Thermal plasma at the temperature of the hottest astrophysical environments, perhaps a billion degrees near a neutron star or in an accretion disk, has a characteristic thermal energy per particle of roughly 100 kiloelectron volts. To reach ZV energies from thermal acceleration alone would require a temperature more than 10 orders of magnitude higher, which is not achieved in any known astrophysical environment. This is why acceleration mechanisms are needed rather than thermal processes. The particle must be pulled out of the thermal distribution and accelerated by electromagnetic fields that do coherent work on it rather than random thermal kicks. The coherence is essential. A particle that receives random kicks from a thermal plasma gains energy in some kicks and loses it in others, performing a random walk in energy space that on average leaves it at the thermal energy. A particle that repeatedly encounters a coherent accelerating field, as in diffusive shock acceleration or rotation-driven electric fields, can accumulate energy monotonically up to the limit set by the Hillas criterion. The coherence must be maintained over the entire acceleration period, which for ZV energies can be enormously long in terms of particle gyrations. A proton at 10 electron volts in a microgauss field has a gyration radius of roughly 10 kiloparsecs, comparable to the size of the Milky Way's disk. For the particle to gain 10 times more energy, the accelerating region must be 10 times larger in the relevant dimension, or the field must be 10 times stronger, or some combination that preserves the Hillas product. Maintaining coherent acceleration over these scales requires structures that are stable on timescales much longer than the acceleration time, which places demands on the astrophysical environment that not all candidate sources can meet. The most stable large-scale structures in the universe are the radiolobes of powerful radio galaxies, magnetized structures that can persist for tens to hundreds of millions of years while remaining magnetically ordered on scales of hundreds of kiloparsecs. These lobes are inflated by the jets of active galactic nuclei, and they confine the jet plasma against the pressure of the surrounding intergalactic medium. Inside the lobes, relativistic electrons spiral in the magnetic field and emit the synchrotron radiation that makes these objects radiobright. Protons in the same environment would spiral without radiating significantly, because their much larger mass makes synchrotron radiation negligible at the same energy. Lobes could therefore be efficient proton accelerators even while being inefficient proton radiators. The acceleration within the lobes would not be a single coherent process, but rather a combination of shock acceleration at the hotspots where the jet terminates, stochastic acceleration from the turbulent magnetic field within the lobe volume, and possible reconnection acceleration at current sheets where oppositely directed field regions meet. The cumulative effect of all these processes over the long lifetime of the lobe could in principle push protons to ZV energies, and the large size and moderate field strength of the lobes place them comfortably on the Hillas diagram for ZV proton acceleration in the most powerful examples. The challenge is observational. Radio lobes are extended diffuse structures that are bright in radio waves but faint in other wavelengths, and the detailed field structure within them is difficult to determine from Earth. The internal magnetic field can be estimated from the radio synchrotron spectrum and the X-ray inverse Compton emission, but these give volume-averaged quantities rather than local field strengths at specific acceleration sites. The turbulent spectrum of the magnetic field, which determines the efficiency of stochastic acceleration, is even harder to determine because it requires resolving structure on scales much smaller than the overall lobe size. The nearest example of a powerful radio galaxy with well-studied lobes is Centaurus A, and it has been analyzed in detail as a prototype for the lobe acceleration scenario. The inner lobes of Centaurus A have magnetic fields of order a few microgauss, inferred from the combination of radio and X-ray observations. The lobe size is roughly a few kiloparsecs. The Hillas criterion for a proton at these parameters gives a maximum energy of order a few exa-electron volts, below the ZV range, but at the level where Auger has reported a mild excess from the Centaurus A direction. The outer radio lobes, which extend to much larger scales, have weaker fields, and the Hillas product does not obviously reach ZV for protons in those regions. Higher energies might be achievable if the acceleration is occurring at the jet termination shocks, which have stronger local fields than the volume-averaged lobe field, or if the particle is a heavy nucleus with higher charge that extends the Hillas limit by a factor of the charge number. An iron nucleus at the same Hillas limit as a proton has 26 times higher total energy, which could push the ceiling well into the ZV range, even in environments where proton acceleration falls short. This is one of the reasons why heavy composition at the highest energies, if confirmed, would be consistent with radio galaxy lobe acceleration as the dominant mechanism. The jet itself, rather than the lobe, might be the primary acceleration site for the most extreme energies if the jet's internal conditions are suitable. Relativistic jets carry strong magnetic fields, and the regions near the base of the jet, within a few parsecs of the central black hole, have the highest field strengths in the entire AGN system. These inner jet regions also have the smallest sizes, but because the field strengths are so high, the Hillas product can still be large. The acceleration efficiency in the inner jet depends critically on whether the particle can be confined near the acceleration site long enough to gain energy without being swept along the jet at the bulk flow velocity. In a relativistic jet with bulk Lorentz factor of 10 or more, a particle gyrating in the jet magnetic field sees the jet flowing past it at relativistic speed. If the gyration radius is smaller than the jet cross-section, the particle can remain in the jet for many gyration periods and be accelerated at shocks or by turbulence. If the gyration radius exceeds the jet cross-section, the particle effectively escapes the jet on a single gyration and cannot be further accelerated. The condition that the gyration radius be smaller than the jet cross-section is another way of stating the Hillas criterion for the jet geometry, and it limits the maximum achievable energy in the inner jet in the same way that any other accelerator size limits the maximum energy. The relativistic bulk motion of the jet introduces a complication and an opportunity for the Hillas argument. In the jet's rest frame, the gyration radius condition must be satisfied for the particle's momentum in that frame, which is related to the lab frame momentum by the jet's Lorentz factor. A particle that would escape the jet in the lab frame might be confined in the jet rest frame if the Lorentz factor is large enough, effectively extending the accessible energy range by the jet Lorentz factor. This relativistic enhancement is one of the features that makes AGN jets particularly attractive as ZV accelerators despite the apparent smallness of the inner jet cross-section. Detailed physics of particle acceleration in relativistic jets has been studied extensively through both analytical models and numerical simulations. Particle-in-cell simulations of relativistic jet shocks show that particles can be accelerated to hard power law spectrum, extending up to energies comparable to the Hillas limit, with the acceleration occurring primarily at the shock front and the downstream turbulence keeping the particle in the acceleration zone for multiple shock crossings. The simulations also show that heavy nuclei can survive in the jet environment without photodisintegration if the photon field is not too intense, which depends on the jet power and the distance from the central engine. The photon field in the inner jet region is produced by the jet's own synchrotron radiation and by the accretion disk luminosity that illuminates the base of the jet. For powerful AGN like those detected by Fermi and gamma rays, the photon density in the inner jet can be high enough to photodisintegrate heavy nuclei efficiently, limiting their survival to lower energies or to larger distances from the central engine where the photon density is lower. This environmental constraint on nucleus survival adds another dimension to the source identification problem, because the same objects that have the strongest fields and largest sizes for acceleration also tend to have the most destructive photon environments. The balance between these competing factors, acceleration efficiency, photon field intensity, magnetic field confinement, and size, defines the operating envelope for each candidate source type. Mapping this envelope across the parameter space of AGN properties, including jet power, black hole mass, accretion rate, and jet Lorentz factor, allows predictions of which AGN populations should contribute most strongly to the ultra-high-energy cosmic ray flux and at what energies. These predictions can then be compared to the observed spectrum, composition, and arrival direction distribution to test which parameter space region is actually being sampled by the detected events. Most powerful AGN, the high-frequency peak blazars and the most luminous flat-spectrum radio quasars, turn out not to be the best candidates for ZV proton production because their intense photon fields make the inner jet environment too destructive. The better candidates for proton acceleration to extreme energies are the moderate-power radio galaxies with less intense photon fields, where the balance between acceleration and loss favors particle survival to the highest energies. Centaurus A and similar FR-I radio galaxies sit in this moderate-power regime, which is one reason they remain favored candidates despite the apparent shortfall in the Hillas criterion for their measured field strengths. For heavy nuclei, the situation is somewhat different because the Hillas criterion is extended by the nuclear charge, but the photon disintegration cross-section is also larger. The net result is a complex dependence on the specific AGN environment that requires detailed modeling for each candidate source. The general trend is that heavy nuclei can survive in environments that would destroy protons at the same total energy, because the relevant threshold for pion production is above the relevant threshold for photodisintegration, and an iron nucleus with the same total energy as a proton sees a much lower photon density in the nucleus's rest frame than the proton does. This difference in rest frame photon density allows heavy nuclei to escape environments that trap and destroy protons. The escape of accelerated particles from the source environment into the intergalactic medium is not instantaneous even after the particle exceeds the Hillas radius for the primary acceleration site. The particle must diffuse through the surrounding medium, which is magnetized at levels that depend on the local environment. Around powerful radio galaxies, the intergalactic medium near the galaxy and its halo has magnetic fields that may be substantially stronger than the cosmic average, enhanced by the galaxy's outflows and by the compression of gas in the cluster or group environment. A particle leaving the jet or lobe must diffuse through this enhanced field region before reaching the less magnetized intergalactic medium farther out. This near-source diffusion extends the effective confinement time and increases the path length the particle travels before escaping, which increases both the energy loss to background photons and the angular deflection from the source direction. The near-source magnetic field environment is poorly characterized observationally for most candidate sources because it requires measuring the Faraday rotation of background radio sources seen through the magnetized environment, and the number of suitable background sources is small in most cases. The uncertainty in the near-source field contributes to the uncertainty in the effective confinement time, and therefore to the uncertainty, in both the maximum achievable energy and the expected directional accuracy of the arriving cosmic rays. The intergalactic magnetic field beyond the galaxy and cluster environment is better constrained on average but highly variable in detail. In the cosmic web filaments, where most of the intergalactic baryons reside, the field can be tens of nanogauss, enhanced by the compression and shear of large-scale structure formation. In the cosmic voids between filaments, the field is much weaker, perhaps sub-nanogauss or even undetectable with current techniques. A cosmic ray propagating through the cosmic web encounters this highly inhomogeneous field structure, with periods of strong deflection in filaments alternating with nearly straight-line propagation in voids. The inhomogeneity of the intergalactic field is not just a technical complication. It has physical consequences for the backtracking problem. A particle that travels partly through a filament and partly through a void will be deflected more than predicted by a homogeneous field model with the average field strength along the path. The filament contribution to the deflection is concentrated in a small fraction of the total path length, but can dominate the total angular change. If the filament is between the source and Earth in a direction that is not along the direct line, its contribution to deflection appears as an inexplicable rotation in the apparent source direction. This is potentially relevant to the local void direction, indicated by the Amaterasu particle's arrival direction. If the particle traveled from a source in a nearby filament and passed through a magnetized filament on its way to Earth, the deflection from that filament could shift the apparent direction from the true source location to an apparent location in the void. The required deflection is a few degrees to tens of degrees depending on the assumed composition, and filamentary fields of tens of nanogauss over path lengths of tens of megaparsecs can easily produce such deflections. The void direction would then be a magnetic mirage, not a physical void containing the source. Testing this scenario requires improving both the measurement of the cosmic ray arrival direction and the modeling of the intervening magnetic field structure. The arrival direction uncertainty can be reduced by accumulating more statistics and by improving the reconstruction methods, but there is a fundamental limit set by the shower geometry reconstruction accuracy of roughly half a degree for individual events. The magnetic field modeling can be improved by incorporating more Faraday rotation measurements from radio surveys like those being conducted by the Square Kilometre Array precursor instruments ASKAP and MeerKAT, which are measuring the Faraday rotation of thousands of background radio sources and beginning to map the magnetic field structure of filaments and voids. The Square Kilometre Array itself, when fully operational, will transform the observational situation for cosmic ray propagation modeling by providing Faraday rotation measurements for millions of background sources across the full sky. From these measurements, the three-dimensional magnetic field structure of the nearby universe can be reconstructed with enough detail to reduce the uncertainty in cosmic ray backtracking from the current level of many degrees to potentially a few degrees for proton primaries. Combined with improved composition measurements from Auger Prime, this would allow the first genuine cosmic ray astronomy with multiple events pointing to the same source region rather than just statistical excesses in broad angular bins. The synergy between cosmic ray physics and radio astronomy embodied in this program is one of the most productive interdisciplinary connections in contemporary astrophysics. The cosmic ray physicists need the magnetic field maps that radio astronomers can provide, and the radio astronomers benefit from the constraint that cosmic ray backtracking provides on the integrated line-of-sight field that their Faraday rotation measurements cannot fully determine without additional information. The two communities are working increasingly closely together on the joint analysis of their complementary datasets, and the combined results are already providing better constraints than either field could achieve alone. The neutrino connection adds a third strand to this interdisciplinary. IceCube's detection of a diffuse astrophysical neutrino flux and the tentative associations of individual neutrino events with specific sources provide independent evidence about which astrophysical environments are producing hadronic interactions at high energies. The comparison of the neutrino arrival directions with the cosmic ray arrival directions, adjusted for the magnetic deflection expected for the cosmic ray composition and the propagation path, tests whether the two populations share common source populations. This comparison must be done carefully because the neutrino and cosmic ray spectra peak at different energies and might therefore reflect different parts of the same source population or different source populations entirely. The IceCube neutrinos are detected at energies from hundreds of tera electron volts to a few peta electron volts, while the ultra-high-energy cosmic rays are above tens of exa-electron volts. The energy ratio between the two is large enough that different acceleration processes or different source environments could be responsible for each, even within the same class of objects. But if both populations trace the same large-scale structure and show correlated anisotropies at the statistical level, the case for shared sources would be strengthened considerably. The gamma-ray connection is similarly complex because the gamma-ray observations span an enormous energy range and reflect many different production processes. The Fermi lat detects gamma rays from GeV to hundreds of GeV from thousands of sources, most of which are blazars and pulsars. The imaging atmospheric Cherenkov telescopes detect sources up to tens of TeV. HAWC and LHASO push into the sub-PV range. The Cherenkov telescope array will eventually reach hundreds of TeV with better sensitivity than existing instruments. Each energy band probes different aspects of the acceleration and target environment in the sources. For ultra-high-energy cosmic ray sources specifically, the most relevant gamma-ray observations are at the highest energies, where hadronic production of pions and subsequent pi-zero decay produces gamma rays with spectra reflecting the accelerated proton spectrum. The detection or non-detection of multi-TeV or sub-PV gamma rays from candidate sources like Centaurus A, the Virgo cluster, or starburst galaxies directly constrains the proton injection spectrum in those environments. If the proton spectrum extends to ZeV energies as required for cosmic ray production, it should also produce a gamma-ray flux at multi-TeV energies that is in principle detectable by existing or planned instruments. The challenge is that the gamma rays themselves interact with background radiation fields during propagation. Very high-energy gamma rays above a few TeV are absorbed by pair production on the extragalactic background light within distances of a few hundred megaparsecs or less, depending on the gamma-ray energy. The absorbed gamma rays cascade into lower-energy photons through the inverse Compton scattering of the produced electrons on the cosmic microwave background. This cascading redistributes the gamma-ray flux from high to lower energies and produces a contribution to the diffuse extragalactic gamma-ray background at GeV energies that is measurable by Fermi. The measured diffuse extragalactic gamma-ray background constrains the total cosmogenic gamma-ray production integrated over cosmic time and volume, providing an indirect constraint on the ultra-high-energy cosmic ray source distribution and composition. Models that predict large cosmogenic gamma-ray production, typically those with proton-dominated composition from sources at high redshift, are constrained by the Fermi measurement of the diffuse background. The consistency between the predicted cosmogenic gamma-ray flux and the measured diffuse background is an independent test of source models that complements the cosmic ray spectrum and arrival direction measurements. The comprehensive test of any source model, therefore, requires simultaneous consistency with the cosmic ray spectrum, the cosmic ray composition, the cosmic ray arrival direction distribution, the cosmogenic neutrino flux upper limits, the cosmogenic gamma-ray flux contribution to the diffuse background, the multi-wavelength emission from specific candidate sources, and the large-scale magnetic field structure inferred from radio observations. This is a demanding set of requirements, and it is precisely the demand that makes the problem scientifically rich rather than merely complicated. Models that satisfy all of these requirements simultaneously are rare, and their rarity is informative. If only a narrow slice of parameter space is consistent with all the observations, that slice tells us something specific about the sources even before we have identified individual objects. If the consistent slice corresponds to moderate power radio galaxies with mixed proton and intermediate mass nuclear composition, that is a statement about which objects in the nearby universe are doing the ZeV acceleration, even if we cannot point to a specific galaxy and say definitively that it is the source of the oh my god particle. This kind of constraint-based reasoning, narrowing the parameter space without achieving unique identification, is characteristic of how frontier science actually proceeds. It is less satisfying narratively than a clean discovery, but it is more honest about what the data can support and more productive scientifically than forcing a premature identification. The narrowing of parameter space is itself a form of knowledge, and it guides both the design of the next generation of experiments and the development of theoretical models that must fit within the remaining space. The models that currently survive the full set of constraints tend to share certain features. The sources are predominantly in the nearby universe within a few hundred megaparsecs, consistent with GZK expectations. The maximum energy is in the ZeV range, set by the observed spectrum. The composition at the highest energies is mixed or possibly shifting toward heavier, consistent with some combination of source environment effects and propagation. The source class is not yet uniquely determined, but it is constrained to objects with sufficient magnetic field and size to satisfy the Hillas criterion while being close enough to satisfy the propagation horizon. These shared features of surviving models represent the current consensus, to the extent that consensus exists in a field with ongoing debates about systematic errors. The debates are productive rather than sterile because they are anchored in specific physical questions that better data can address. The composition debate between Auger and the telescope array can be resolved by cross-calibrated measurements using identical analysis techniques applied to data from both experiments. The source identification debate can be resolved by accumulating enough statistics to detect or constrain clustering at angular scales smaller than the current search radii. The hadronic interaction model debate can be informed by forward physics measurements at the LHC and by future high-energy collider experiments that extend the directly measured energy range. Each of these resolutions requires time and effort and resources, but they are not in principle beyond reach. The field is not stuck. It is moving, and the direction of movement is toward greater precision and greater understanding. The question of what produced the oh my God particle will have an answer, and the answer will come from the same kind of patient, careful, collaborative scientific work that has characterized the field since Victor Hess climbed into his balloon with his electroscopes and his doubt. The final pieces of the puzzle are not yet in place, but the shape of the puzzle is now clear enough to describe. The picture being assembled is one of a universe that is more extreme, more magnetic, and more compositionally complex than the simplest models assumed. The most powerful astrophysical accelerators in the local universe, operating in environments of strong magnetic fields and relativistic particle flows, are pushing matter to energies that make our best particle accelerators look like children's toys. The particles they produce travel through a cosmos that is filled with ancient light, threaded with tangled magnetic fields, and organized into the large-scale structure of the cosmic web that simultaneously constrains where the sources can be and scrambles the directions of the arriving messengers. Reading the messages requires instruments of unprecedented scale and sophistication, analysis methods that honestly account for irreducible uncertainties, and theoretical frameworks that connect the observations across multiple wavelengths, particle types, and physical processes. The reading is partial and imperfect and ongoing, and the message is richer and stranger than anyone anticipated when the field began. The oh my God particle is still teaching us. Not because the event itself contains more information than was extracted from it in 1991, but because it established a benchmark that every subsequent theory and measurement must address. It defined the upper range of the problem and set the scale for the instrumentation needed to study it systematically. It provoked the construction of the telescope array and the Pier Auger Observatory and the development of the hybrid detection methods that those experiments rely on. It motivated the theoretical work on acceleration mechanisms and propagation physics that has transformed our understanding of both. The Amaterasu particle is adding to that teaching, arriving 3 decades later with better instrumentation and better methods, pointing toward a void that challenges easy explanations, and demanding that the theoretical framework accommodate not just extreme energies, but extreme energies arriving from unexpected directions. Its name, like the oh my God particle's nickname, captures the human response to encountering something at the edge of what physics permits, an event that makes even experienced researchers briefly forget their training and respond with something more immediate than analysis. That immediacy is not a failure of scientific discipline. It is evidence that the connection between the observable universe and human experience, however mediated by instruments and mathematics, is never entirely broken. The particle that hit the Utah atmosphere on October 15, 1991, had been traveling for an unknown time from an unknown source through a universe that does not know we are here. It arrived indifferent to our theories and our instruments, carrying its energy as a simple fact about what had happened somewhere in the cosmos. We measured it, questioned it, and spent decades trying to explain it. The explanation is still being worked out, but the working out is the science, and the science is what we have. Not certainty, not final answers, not a complete theory of the universe's most extreme processes, but a carefully constructed, honestly reported, continuously improving understanding that gets closer to the truth with every new event, every new measurement, every new model that survives the full set of constraints. The universe's most extreme particles are not puzzles designed for our convenience. They are consequences of processes that would operate exactly the same way if we were not here to observe them. The fact that we are here, that we built instruments to detect them, and that we are slowly learning to read what they carry, is one of the more extraordinary things about the universe that we know of. Matter became curious about the most extreme versions of itself, and the curiosity produced knowledge that extends the reach of human understanding into domains that no unaided human sense can touch. That is the deeper story beneath the oh my god particle and the Amaterasu particle, and the decades of painstaking work that connects them. Not just a story about extreme energies and exotic sources in propagation physics, but a story about how knowledge grows at the frontier, slowly and carefully and collaboratively, driven by instruments that extend perception and theories that organize what perception reveals, always pushing toward a more complete and more honest account of what the universe actually does. The desert is still listening. The instruments are still running. The universe is still sending its most extreme messengers, indifferent to our theories, carrying their energies across billions of years of space and time, arriving at the edge of our atmosphere where the air itself becomes the detector and the cascade becomes the evidence. We are still learning to read what they carry. The reading continues. The most persistent feature of the ultra-high-energy cosmic ray mystery is not any individual anomalous event, but the gap between what we know the universe can do and what we can actually observe it doing. That gap is simultaneously the frustration and the opportunity of the field, because it is the gap where new physics and new astrophysics live. Everything we understand clearly is already understood. The gap is where understanding has not yet reached, and reaching it is the work. Closing the gap requires progress on three distinct but interconnected fronts that have been recurring throughout this story. The first is observational, accumulating enough events with enough well-characterized properties that the statistical picture becomes clear enough to test specific hypotheses. The second is instrumental, developing detector technologies that can measure more properties of each event with smaller systematic uncertainties and larger efficiency. The third is theoretical, building models that connect the observations across multiple wavelengths and particle types in a physically self-consistent way that makes specific, testable predictions. Progress on all three fronts is happening simultaneously, driven by a community of researchers who understand that the three fronts are not independent. Better observations motivate better instruments and test theoretical models. Better instruments enable better observations and reveal what theoretical models must explain. Better theoretical models guide instrument design and suggest which observations are most constraining. The three advance together, each informing and requiring the others. The observational situation at the time of writing is richer than at any previous point in the history of the field, but it is still limited by statistics at the highest energies. The combination of auger and telescope array data provides full sky coverage with well-characterized instruments and reasonably understood systematic errors. The spectrum is measured from both hemispheres and is consistent with a suppression at energies consistent with GZK expectations. The composition shows evidence for evolution with energy, though the specifics depend on the hadronic interaction models and the experiment. The arrival direction distribution shows hints of anisotropy correlated with the local large-scale structure and possibly with specific source populations, including starburst galaxies and the Virgo and Centaurus A regions. None of these results is definitive enough to constitute a solution to the source problem, but together they constrain the solution space significantly. The space of models consistent with all current observations is smaller than it was a decade ago, and it will be smaller still a decade from now as the upgraded instruments accumulate data. The narrowing is real even when the final answer is not yet visible. The instrumental situation is also improving in ways that will matter specifically for the hardest remaining questions. Auger Prime will provide composition information on a shower-by-shower basis through the scintillator-Water-Cherenkov ratio, allowing composition-dependent anisotropy analysis that is currently limited by the need for statistical composition inference. The T-Ax4 expansion will resolve the hot spot question by accumulating enough events in that region to determine whether the excess is real, and if so, what its angular structure looks like. The radio antenna deployments will provide continuous composition sensitivity for the largest showers, extending the duty cycle for composition measurements beyond what fluorescence detection alone can achieve. Looking further ahead, the space-based detector concepts being developed for POE-MMA and potential future missions would provide exposures that dwarf even the largest ground-based arrays by observing the atmosphere from orbit over enormous footprints. The challenge of achieving adequate angular resolution and energy accuracy from orbit is substantial, but appears surmountable based on the technology demonstrations of Pathfinder instruments. A space-based detector with 10 times the exposure of the current ground-based experiments would accumulate statistics at the highest energies at a rate that would transform the field within a decade of operation. The theoretical situation has been transformed by computational advances that allow full numerical propagation of cosmic rays through realistic models of the intergalactic environment, replacing the semi-analytic estimates that were the state of the art 2 decades ago. These numerical propagation frameworks, combined with cosmological simulations that provide realistic models of the large-scale structure, magnetic fields, and source distributions, can generate specific predictions for the spectrum, composition, and anisotropy expected for any assumed source population. The predictions can be compared directly to observations through statistical likelihood methods that properly account for the uncertainties in both the observations and the simulations. The development of machine learning methods for shower reconstruction and classification is an additional tool that is beginning to be applied in cosmic ray physics. Neural networks can in principle learn complex relationships between shower observables and primary particle properties that are difficult to capture in parametric reconstruction methods. Applied to X-max reconstruction, muon counting, and composition classification, these methods may extract more information from each shower event than conventional methods and reduce the systematic uncertainty from hadronic model dependence by learning directly from data in a model-agnostic way. The application of machine learning to cosmic ray physics is still in its early stages, and the field must be careful to validate these methods against known physics and to understand what information they are actually extracting before trusting them for discovery claims. But the potential is significant, and as the datasets grow and the methods mature, machine learning may contribute meaningfully to the resolution of the composition ambiguity that currently limits interpretation of the highest energy events. The connections to other areas of physics and astrophysics that have been developed through the ultra-high energy cosmic ray program will continue to be productive regardless of how the specific source question is resolved. The hadronic interaction physics that is being tested by cosmic ray showers is relevant for understanding QCD in the high-density regime. The Lorentz invariance tests that cosmic ray observations provide are relevant for quantum gravity phenomenology. The cosmic web magnetic field measurements that cosmic ray backtracking requires are relevant for understanding galaxy formation and the magnetization of the intergalactic medium. The multi-messenger connections that cosmic ray astronomy is building with neutrino and gamma ray astronomy are relevant for understanding the energy budget of the universe's most energetic processes. These connections mean that progress in cosmic ray physics does not benefit only the field itself. Every improvement in understanding where ultra-high-energy cosmic rays come from and how they propagate improves our understanding of related phenomena across multiple disciplines. The investment in the instruments and the analysis methods and the theoretical frameworks pays dividends that extend well beyond the specific question of what produced the oh my god particle. The scientific legacy of the oh my god particle detection includes not just the event itself, but the entire scientific apparatus that it helped motivate. The Pierre Auger Observatory, the telescope array and its T-Ax-4 expansion, the Auger Prime upgrade, the multi-messenger analysis frameworks connecting cosmic rays to neutrinos and gamma rays, the improved hadronic interaction models constrained by LHC measurements, the cosmic web magnetic field models informed by Faraday rotation surveys, and the theoretical frameworks for composition-dependent propagation and source identification. All of these would have developed eventually as the field advanced, but the existence of an event at 320 exa-electron-volts with no obvious explanation accelerated the development of every one of them. This is how individual observations can function as catalysts in science. They do not themselves solve problems, but they sharpen the problems in ways that guide the search for solutions. The oh my god particle sharpened the acceleration problem by making it undeniable that ZV energies are achievable in nature. It sharpened the propagation problem by demonstrating that particles at those energies do reach Earth from somewhere. It sharpened the source identification problem by providing a specific direction and energy that any successful theory must explain. And it sharpened the instrumental challenge by defining the scale of detection capability needed to study such events statistically. Each of these sharpenings has been productive, driving progress across the field over 3 decades. The event itself is a single data point, but as a catalyst, it has been enormously valuable, and its legacy continues in every paper written about ultra-high-energy cosmic rays, every shift worked at the Auger detector or the telescope array, and every graduate student who enters the field because the question of what produced the oh my god particle is too interesting to leave unanswered. The Amaterasu particle continues this catalytic function for the current generation, arriving with the advantages of better instrumentation and more mature analysis methods, but carrying the same fundamental mystery in a new and slightly different form. Its void direction adds a new constraint that must be explained, its energy refines the statistical picture at the top of the spectrum, and its reconstruction with hybrid methods provides a template for how future events should be analyzed to extract maximum information. Like its predecessor, it will drive progress not by providing an answer, but by making the question more precise. The question, at its most fundamental, is about the relationship between the universe's structure and the extreme events it produces. The cosmic web of dark matter and baryons, threaded with magnetic fields and filled with ancient radiation, is not just a passive backdrop for the drama of galaxy formation and evolution. It is an active participant in the production and propagation of the most energetic particles in existence. The structure of the web determines where the sources are concentrated, how the particles propagate between source and observer, and what energy they carry when they arrive. Understanding this relationship in detail is the goal toward which the field is working, and the tools for achieving that understanding are steadily improving. The coming decades will see the accumulation of statistics, the improvement of composition measurements, the extension of multi-messenger connections, and the refinement of theoretical models in ways that will move the question from the category of deep mysteries toward the category of solved problems. The movement will be gradual and iterative, but its direction is clear, and its eventual completion seems plausible within the career spans of researchers now entering the field. When the answer comes, it will not feel like the sudden resolution of a long-standing puzzle. It will feel more like the gradual dawning of clarity as successive pieces of evidence fall into place. At some point, the parameter space of consistent models will narrow to a single family, and that family will correspond to specific types of objects in specific environments, and those objects will be confirmed by correlated observations in multiple messengers, and the confirmation will be broadly accepted by the community. The oh my god particle will have its explanation, at least in the sense of knowing what class of object produced it and by what mechanism. Whether the explanation will reveal new fundamental physics or will show that known physics, exercised to its limits, is sufficient to account for what we observe is the deepest open question. Both possibilities are scientifically valuable, though in different ways. New fundamental physics would transform our understanding of the basic laws governing matter and energy. Known physics at its limits would deepen our understanding of what those laws allow and would reveal astrophysical processes of extraordinary power and efficiency. Either outcome would be worthy of the sustained effort that has gone into pursuing the question since October 15, 1991, when the fly's eye saw something in the Utah desert that should not exist, and physicists responded the only way physicists know how to respond to the impossible, by measuring it carefully, questioning it relentlessly, and building better instruments to understand it more completely. The mystery persists. The pursuit continues. The universe, indifferent and extreme and endlessly surprising, keeps sending its most energetic messengers to announce that there are things happening out there that we do not yet understand. Our instruments are listening, our theories are reaching, and our understanding is growing, event by patient event, toward an answer that the cosmos has been hiding in plain sight since long before we had eyes to see it. What began on a moonless October night in the Utah desert has become one of the most far-reaching investigations in the history of science, connecting a single anomalous detection to questions about the fundamental structure of the universe, the behavior of matter at energies beyond any human experiment, and the nature of the cosmic engines that power the most extreme processes in existence. The oh my god particle arrived as a provocation and remained as a challenge, and the challenge has been taken up by generations of researchers who built the instruments, developed the methods, and created the theoretical frameworks needed to address it. The particle itself is gone, its energy long since distributed among the muons and electrons and photons of the shower that swept across the desert floor more than 30 years ago. But its legacy persists in every detector station on the Argentinian Pampa, in every fluorescence telescope staring at the Utah sky, in every neutrino telescope buried in Antarctic ice, and in every theoretical paper that grapples with the question of what the universe's most extreme accelerators look like and how they work. The Amaterasu particle arrived in 2021 as if to remind the field that the question is not finished, that the universe has more to say about its most extreme processes, and that the instruments built in the decades since the oh my god particle are capable of hearing it with greater clarity than before. Its void direction is a fresh puzzle added to the layers of existing puzzles, and it will be addressed with the same combination of careful measurement, honest uncertainty estimation, and patient accumulation of evidence that has characterized the field since its beginning. The story of ultra-high-energy cosmic rays is not a completed narrative with a known ending. It is an ongoing investigation at the frontier of human knowledge, where the questions are hardest, the data are sparsest, and the potential discoveries are most profound. The researchers working in the field today are writing the middle chapters of a story whose conclusion is not yet known but whose importance is clear. They are doing science at its most demanding and most rewarding, pushing the boundary of what humanity knows about the universe to places where the view is strange and the footing is uncertain, and the work is absolutely worth doing. The desert is wide, the sky is deep, the particles keep arriving, and the science continues.